इंडोर इंडोर तो ये 90% बाहर एक हाईवे वही यहाँ से 50 किलोमीटर से मुंबई की
Hello.
Good morning, sir.
Good morning. Good morning. Shishir ji,
Good to see you on screen, sir.
yeah, thank you. And so, how many Indian people have joined so far? Good numbers? 30
We have around 31 total participants, sir.
in that. So must be very cold now in Moscow.
Yes, it's very. It was snowing last night, so lots of snow.
Great, great.
We also have Professor Anatoliy Soloviev, who's joined us. He's the director of Geophysical Center, Russian Academy of Science.
Oh,
Good morning to you, sir.
Hello, hello, dear colleagues.
We also have our eminent expert, Professor Vinod Menon, on the screen, sir.
Thank you, Dr. Shishir. Thank you very much.
Good morning, sir.
Good morning. Good morning, Dr. Shishir. This is a very well-organized program, very well-designed.
Good morning, sir.
We're really looking forward to the deliberations.
Same here, sir. It is courtesy. We have our international department expert, leading expert from Department Russian Academy of Science, Ms. Sain, and her team, who have contributed a lot.
Good morning. Good morning, everyone.
Morning.
good morning, everyone. Professor Menon and all other distinguished delegates from Russia. Very, very good morning.
Dr. Sain, it's a pleasure to see you here.
So thank you very much. I think
you
this is
virtually.
first time we are meeting, though not physically, but online.
That's
So
right.
great pleasure.
We will start in 1 minute.
Good morning and good afternoon. Professor Menon, it's great to see you.
Yeah, good to see you, Professor Ravi Sinha. We have a large number of and Russian experts. It's a pleasure to have the collaboration and partnership of the Russian experts along with the Indian experts in disaster risk reduction, civil engineering, structural engineering, geotechnical engineering. With Dr. Sain giving the opening remarks, I think it will be wonderful. Really set the tone.
So good morning and good afternoon to everyone. We are now joined here by all our eminent experts from India and Russia. And I am Shishir, Shrotriya, Counsellor of Science and Technology at Embassy of India, Moscow. May I now request my colleague, Ms. Ina, from International Cooperation Department, Russian Academy of Sciences, to kindly invite Professor Anatoliy for the opening address, please.
Good morning, everybody. I would like to introduce you Professor Anatoliy Soloviev. He is Doctor of Sciences in Physics and Mathematics, corresponding member at the Department for Earth Sciences of the Russian Academy of Sciences, and Director of the Geophysical Center of the Russian Academy of Sciences in Moscow. Please, Professor Soloviev, you're welcome.
Thank you, dear colleagues and esteemed participants. I'm pleased to welcome you to the Russian-Indian scientific webinar on disaster management technologies. And on behalf of the Russian Academy of Sciences and Earth Science Department of the Academy, it is a great pleasure and honor for me to greet our Indian colleagues who carry out studies in different areas of this important and up-to-date subject. Natural disasters are sources of profound social upheaval, which leads to the suffering and even deaths of people, and of course, huge material losses. The increasing number of natural disasters is interconnected with the global processes, such as population and world economic growth, degradation of the natural environment and resources, climate change, and so forth. And it is worth noting that we are exposed to impacts of both intraterrestrial and extraterrestrial origins. A striking example for the latter is the space weather effects, which are extremely harmful for the high-tech infrastructure. Accordingly, disaster management is an important element of the government sustainable development strategy. It should be based on the principles of rational economic use of territories, scientifically grounded forecasts of impending dangers, and taking preventive measures. When developing the technologies of disaster management, it is important to understand that people actually are not able to suspend or change the course of the planet's natural evolution. We can only try to predict its development with a certain degree of probability, and sometimes influence its dynamics. Therefore, at present, the tasks of timely forecasting natural disasters, supervision, monitoring the Earth system dynamics, control and mitigating their negative consequences come to the fore. Over the past half century, the number of natural disasters has increased fivefold, while the material damage from them has increased tenfold. In the global problem of security, natural disasters are considered as one of the strongest destabilizing factors hindering the sustainable development of mankind. At the same time, I'm pleased to note that the Department for International Cooperation of the Russian Academy of Sciences and the Embassy of India in Moscow pay much attention to such an important issue as searching for the ways of international scientific cooperation in this particular area of scientific research. Events such as this one provide an important platform for Russian and Indian researchers to present their work, share their latest achievements and scientific experience with their foreign colleagues. Apparently, there is no doubt that the development of technologies of disaster management is important for both countries. My scientific activity is closely connected to this topic, and I am completely confident in its importance and relevance. I warmly welcome the speakers whom we will have the pleasure to hear and see today, covering various topics in this domain. And I would like to conclude by wishing you a successful event, as well as new achievements and interesting discoveries in your scientific work. Thank you. Sorry, Professor Shrotriya, I can't hear you. Your microphone is muted.
Thank you very much, sir, for your opening remarks, sir. We now have, I have the pleasure of introducing Professor Dr. Kalachand Sain. He is the director of Wadia Institute of Himalayan Geology, Dehradun, India. Professor Sain has received his MTech in Applied Geophysics from Indian School of Mines, Dhanbad, way back in 1988. And he holds a PhD in Control Source Seismology from Osmania University. He has visited Cambridge University, UK, Rice University, USA as a postdoctoral fellow, and he's worked as a visiting scientist at US Geological Survey at Menlo Park, USA. He has earlier been as a very distinguished scientist in many appointments before, as chief scientist and head of seismic group at CSIR-CSMCRI and many other institutes. He has been recognized by a number of awards, fellowships, and honors. Notable amongst them are Fellow of National Academy of Sciences, India. He has also worked very, very diligently right from his early days and was honored as the Young Scientist Award in 1998 by CSIR. He's a member of numerous committees like Bureau member of International Lithosphere Program under IUGG and many other committees. He's a guest editor and very active researcher. So may I now request you, sir, to give your opening remarks, please.
A very good morning to all the Russian delegates and very good afternoon to our Indian delegates. Thank you, Dr. Shrotriya, for introducing. You have said a lot about me. I'm not up to that mark. Anyway, Professor Menon, Professor Soloviev, all the distinguished delegates and members from Russia and India. And first of all, I thank Dr. Shrotriya for considering me as one of the speaker from India, as well as giving an opportunity to share my thoughts and views in the opening remarks. This Indo-Russian scientific webinar on disaster management technologies is very, very important and apt in the present scenario when in India we are experiencing, because of these extreme climate events, a lot of landslides, earthquakes, as well as avalanches. So I am sure that in the 2 days deliberations by the Indian scientists, researchers, and the Russian scientists, researchers will be presenting different aspects of the disasters, how we can evolve strategy for solving those scientific challenges so that both countries can get mutual benefit from the deliberation by creating a network of having their collaboration whatever way possible. So this gives a very unique opportunity and platform to come together and share the thoughts of views of respective countries, whatever research they have been pursuing depending on the countries in challenges, countries problem. And if we can have 1+1, I think Professor Menon in the beginning also mentioned that if we have the collaboration, 1+1, it will make 11, and we can see there are a lot of benefits for both countries. I would like to take few minutes to describe what the challenges India faces. Basically, if we look into the Indian geography, India cannot escape from different sets of threat we are experiencing almost every year, or national calamities or disaster caused by earthquake, landslides, avalanches, globs, lobs, debris flow, flash floods, even forest fire in the Himalayan region. And in the plains, we are experiencing droughts and floods. And in the coastal region, we are experiencing cyclones, tsunamis, erosion. So you can see that not a single part of the Indian subcontinent, starting from the Himalayan region to the plain region to the coastal region, everywhere we have some natural disasters. So we need to understand all these phenomena in a holistic manner, and we also understand Russia also have similar situations and problems, and if we can understand each other and evolve some sort of strategy, whatever we are following to mitigate all these disasters, that will be enhanced. It is true that these natural disasters cannot be stopped. These are all natural phenomena. But only thing what we can do by adapting a different type of strategies towards the mitigation, towards the risk reduction, we'll be able to save a lot of properties, we'll be able to save a lot of structures, infrastructures. This way, economically, if we can save all of this, we'll be having some sort of implications to the country's economy. So I will give you, maybe I will take a few examples what exactly happened in 2004 tsunami. That time, what we experienced into our country, all of us know that in Andaman region, there was a sub-sea 9.3 magnitude earthquake due to megathrust. And that caused around 230,000 8,000 people dead in the countries into the Indian Ocean. And that earthquake generated huge ocean wave, 30 meters to the tune into the coastal region and caused damage, devastations. After that, India developed an early warning system, tsunami warning system, by integrating data from different observations like seismic stations, tsunami buoys, tidal stations, and ample scenarios of different earthquake, different magnitude were created based on the numerical modeling. And that gave some sort of forecast using WIHG-based services at inquests run by Ministry of Earth Sciences. So this needs to be further strengthened. How we can strengthen the early warning system of the tsunami into the 14 rim countries into this region. This is very, very important phenomena, number one. Number two, in Himalayan region, in 2013, we have experienced a Kedarnath flash flood caused by glacial lake outburst with rainfall, and there was some sort of debris flow, and Chorabari catchment, that lake got burst. So we have in our country high altitude lot of glaciers, and that have a threat. And because of that particular flash flood that caused 600 people dead, 5,500 villages inundated, as well as 2 lakh around people pilgrimages are trapped. So this type of scenario in our country is there, and we need to strengthen our activities such a way that we'll be able to mitigate, we'll be able to reduce the risk involved in certain scenarios. And that can be done. And if we look into, so that happened into 2013 summer. But if we look into recent phenomena in Dhaliganga and Rishikesh, that happened in peak winter. So the situation of the disaster is throughout the year. And here it took place avalanche of a huge mass of glacier as well as underlying rock. And that caused again a flash flood. Around 200 people feared dead. There was a lot of hydroelectric power project damage, and a lot of bridges connecting roads into the villages all got damaged. So we are having that scenario of avalanche and glove, not only in one time in the summer, in winter both. This is second phenomena. Third phenomena, in Himalayan region, always we experience that there is a landslides, and particularly this time in Uttarakhand and Himachal Pradesh, because of this excessive rainfall. Still rainfall is going on, and we are having that damage due to the landslides. So the time has come, we can understand how we can improve our map related to the vulnerability, susceptibility of the landslides, related to the hazard assessment of the earthquake, related to the avalanche. So all sort of things is possible only when we have some sort of automatic weather station for the hydrological data, automatic water level recorder, automatic weather station, so that meteorological data, and some sort of broadband seismometer. I'll come back after 2 minutes. That broadband seismometer study into the Dhaliganga, Rishikesh has helped us to understand the entire sequence of the avalanche, starting from the nucleation creeping to that rock mass detachment from that high altitude 5,600 meter to 3,600 meter, then debris flow, then damage to the hydroelectric power project. So entire sequence that took place was 20-25 minute time. So we got good amount of time when it nucleated and caused the damage in between 20-25 minute time. And that time is sufficient for generating or giving early warning, evacuation of the people. It is not like earthquake. Even for the earthquake, we understand when it has taken place and the damaging earthquake comes, there is only 20-second, 25-second time. That time, and here in the case of landslides or avalanche, time is quite large in terms of 20 minutes and 30 minutes. So if we have all these stations into the respective basins and get the data automatically through FASc or other, and we have some sort of mechanism for processing and analysis of the huge volume of data based on artificial intelligence, machine learning, will be able to alert the people and save the structures and properties. This is the only way we can go ahead, because all these natural phenomena cannot be stopped. So this is the third important thing. Fourth important thing, that in our region, we have the lot of coastal vulnerability. So we need to look into that, how the shoreline is getting changed, how the sea level is rising, how the coastal slopes, how the wave height, tide range, coastal topography. That study help us for preservation of the coastal zone. And in the coastal zone, we have a lot of people go to the fishing, etc. So hourly and daily basis forecast, if we can make of the ocean waves or currents or SST or MLD, that will help us, or issue warning to the fishermen, or as well as for the resource exploration and exploitation for the sustainable development. It will add a lot of value to the people involved into this. In the Himalayan region, particularly our institute is situated in Uttarakhand state, and Uttarakhand and the Himachal Pradesh during the last 200-300 years have not experienced any earthquake bigger than 7.5 magnitude. But if we look into the northeastern part, there are Assam earthquake in 1950, 8.6 magnitude, 1897 Shillong earthquake, that 8.4 magnitude, 1934 Bihar Nepal earthquake, 8.1 magnitude. Then there again 2015 Nepal earthquake. And if we go to northwest, again we have Kangra earthquake, 7.9 magnitude in 1905. And 2005 we have Kashmir earthquake, even 7.9. But in between zone, we have not experienced any earthquake of big magnitude. But based on the GPS study, based on the seismological network, it is envisaged that this region is having capability of generating an earthquake of 7.5 magnitude. So if it happens, it will not cause damage to our Uttarakhand state or Himachal state or all the state associated with the Himalaya. It will cause huge damage to the Delhi and NCR region, which is just 275 kilometers away. So we have to have a network of the seismometer, GPS, and accelerometer, so that even we cannot predict, but we will be able to understand the most vulnerable zone, so that we can have some sort of precautionary measure for mitigating if some sort of situation happens, or implementing some sort of guidelines towards the building code and towards the any other earthquake resilient structures, etc. All these things, I think, when we work together, we are doing based on the availability, based on the challenges existing in our country, and your challenges is something different. So if we understand each other, all these phenomena of disaster, then we'll be able to manage in a better way. So I will not take much time. I will just say that we can study and we can understand. There are a lot of methodologies, approaches, and technologies are being applied in both countries to understand, and both countries have the capacity in the modern facilities. And if we have that expertise at one place, just like this platform, definitely this will help us to mitigate our challenges, to mitigate our disaster management in a better way. I'll just say a few lines that if we have this interaction, if we have this collaboration, if we have this networking, this will help us to do some joint work. And ultimately, at the end of the day, this will strengthen, number one, the disaster research and management capabilities of both countries, number one. Number two, this will also help prepare improved maps of vulnerability and risk involved in different sets of disaster. And third thing, this will also provide some critical parameters for the planners, city developers, civic authorities, decision makers, so that they can take appropriate steps to reduce the disaster. This is the third point. Fourth point also, I can say that we have built some sort of expertise, our trained manpower. So if we have collaboration, we can build manpower or expertise into their domain of research, and they can also understand our domain of research. So if we can marry them, then our understanding of the disaster will be much more better way we can understand and give the mitigation to the people. And this way, definitely it will fill the gap in our understanding and evaluation of the multiple hazards, cascading effects, all these things. And I'm happy to say over here that the Indian government has established a well-structured disaster management and risk reduction initiative. It has defined role, responsibilities, and guidelines and procedures for different stakeholders, both at the national level as well as the international level, so that we can make our country disaster resilient through proactive planning on disaster risk reduction and resilience at proper places and proper time. And Prime Minister's 10-point agenda for disaster management is one of that agenda where we can understand all these important issues. So I will not take much time. I wish that the deliberation of these 2 days will give a lot of important inputs to both delegates from both countries, and all success to this Indo-Russian scientific webinar. And still we are going through this pandemic, and wish all of you to stay safe, stay healthy. Thank you very much.
Thank you very much for a very elaborate and wonderful remarks, sir. I request all the eminent colleagues who have joined, experts who have joined, to kindly switch on their camera for the inaugural group photograph, which we will take now. And thereafter, I'll introduce our eminent moderator for the first session. So may we have a group photograph, please?
Владимир Николаевич, включите камеру, пожалуйста. И Виктор Александрович тоже, если можно.
Thank you. Thank you very much. We are indeed privileged to have all these experts online today. And we have extensive discussions now following these 2 days, today and tomorrow. The themes are, of course, known to the experts, but this webinar is also being streamed online on the YouTube channel of Russian Academy of Sciences. So many other audience are listening to it live, and the recorded proceedings will also be available to them. Of course, all the experts know, but I'll just repeat the 4 themes, sub-themes. The first is disaster risk reduction and resilient technology-enabled infrastructure. The second theme, sub-theme for today, is integration of multiple sensors, weather sensors and satellite imagery, and improving disaster forecast. The third is big data integration, crisis analytics, and scientific methods to improve disaster mitigation and prediction. And the last theme is use of drones, IoT, and other scientific methods for collecting and processing, improving the disaster response. So all these areas need collaborative effort, and we request all these experts to come together and formulate scientific interventions into these areas of disaster management related to disaster mitigation, prediction, and disaster response. So now I have the proud privilege of introducing our eminent expert who will moderate the first session on disaster risk reduction and resilient technology-enabled infrastructure. Professor N. Vinod Chandra Menon, he's an alumnus of Kerala University and Jawaharlal Nehru University, New Delhi. Professor Menon has over 37 years of working experience, of which more than 2.5 decades have been in the field of disaster risk reduction, climate change adaptation, and public policy analysis. He has worked as Professor Disaster Management at the Yashwantrao Chauhan Academy of Development Administration. We call it Yashoda. It's at Pune. He has also worked as in charge of emergency preparedness and response in UNICEF India Country Office at New Delhi. In 2005, he was nominated by the Prime Minister of India as the founder member of National Disaster Management Authority, an apex body of Government of India, and he held the status of a Union Minister of State in the Government of India, and he worked in this capacity from 2005 September to 2010, almost 5 years. He is on the governing board of several organizations, and he's co-founder of many new initiatives. He's also a member of peer committees on technological preparedness to deal with national disruptions. He's also helped startups and tech SMEs through his initiatives of India's Excellence Forum and has acted as advisor and mentor to many of the institutes and many of these agencies. Professor Menon is now an independent consultant in the field of disaster risk reduction, climate change adaptation, and public policy analysis. He has been a consultant to UNDP, UNICEF, UN, World Bank, and many other global organizations. So I have the privilege of requesting Professor Menon to take over as the moderator of the first session, sir. Sir, kindly, please.
Thank you very much, Dr. Shishir Shrotriya. It's a great pleasure and a privilege for me to be, having this opportunity to moderate the session with the distinguished delegates from Russia and also the distinguished experts from India. And some of them are my very close friends, good friends like Professor Kapil Gupta, Professor Ravi Sinha from IIT Bombay, Professor Rathod is there, Mr. Pravir Roy is there, and many other friends. It's a great pleasure for me to be available, to have this opportunity to also address this webinar on disaster risk reduction technologies, the role of technologies in disaster risk reduction. And this is something which is very close to the heart of the Russian experts and also the Indian experts. And not only that, globally, there are a lot of initiatives on international cooperation. And so we're very happy that the Russian Academy of Sciences, the Department of International Cooperation, is leading on this with the Government of India's Indian Embassy in Moscow and also the External Affairs Ministry. It will be very useful to have the deliberations on the role of technologies, because we know that technology plays an extremely important role to save lives and to protect livelihoods. And we have seen that now, especially in the context of COVID-19. We have seen that 221 countries have been impacted, millions of lives have been lost. And this time, in the last 2 years, almost 20 months, we have seen the role of technology. We have seen artificial intelligence, robotics, machine learning, big data analytics, IoT, and many other tools and from the toolkit, whether it is geoinformatics solutions, which are actually able to map clusters of the caseload occurrence which are happening in different places, and then to really look at addressing that. We've seen the role of technology in helping better decision making, informed decision making by policy analysts, by decision makers. We have really seen that. So if you really look at disaster typologies, whether it is geological hazards, hydrometeorological hazards, chemical, biological, radiological, or nuclear and explosive emergencies, we actually see the role of technology. And so we have very distinguished experts from Russia and India speaking on disaster risk reduction and the technology-enabled solutions. So I feel that actually, whether it is earthquakes, now we will have some very interesting presentations from very distinguished experts who will be addressing. But specifically, I would like to mention the role of technology, whether it is sensors, Doppler radars to look at cyclones and landfall, exactly predicting the landfall of cyclones. And we see the role of the Doppler radars, which are able to track that. We have seen the saving of lives in Orissa, in India, where the cyclone Philin was actually predicted by the IMD in terms of exact landfall, precise locations, and then more than 1 million people were evacuated, and the number of lives lost was reduced to 23, compared to almost more than 10,000 in 1999. So we really feel that there is this opportunity to look at technology, whether it is the persistent scatter interferometry using synthetic aperture radars, to look at deformations before, during, and after disasters, so that critical infrastructure can be mapped. We see the PS-INSAR coming up as a technology solution. We see, like Dr. Sain was mentioning, GNSS stations, can also look at what is the ionosphere. And we will have some very interesting presentations when people can actually explain that earthquakes can also be predicted with precision in terms of both the epicenter and also the depth and the magnitude. We will have some presentations by Professor Sergei Polinets, who also holds a patent from Russia. So we will actually have discussions, and we have distinguished experts from India who will be making presentations. So I'm sure that all this will actually help us to prepare for, respond to, and recover from emergencies, and how technology can help us. So I'm sure that these deliberations will be very helpful in understanding how different sciences can actually help, whether it's a multidisciplinary field, and India has an extensive history of collaborations with the Russian experts, whether it is in planning. India started the planning exercises with the Russian support and guidance, and we have seen that over the last several decades the collaboration with Russia has been very extensive. And I'm also very happy to mention that I had the opportunity to visit Russia through an Indo-Russian exchange program with the Russian Academy of Sciences and the ICSSR, the Indian Council of Social Science Research, about 20 years ago. And I had the opportunity to visit EMERCOM and have interactions with the distinguished experts from EMERCOM. So there is a lot of opportunity of collaboration, and I'm very happy that this opportunity is there, and we have very distinguished experts addressing the first session. So I will conclude by thanking Dr. Shishir Shrotriya and also the Russian Academy of Sciences, Department of International Cooperation, and people like Professor Anatoliy Soloviev and Professor Kalachand, Sain, who spoke in the opening remarks. We look forward to the presentations by the distinguished experts, and I'm sure that you will find this very rewarding experience. So we would look at scenario analysis, modeling, big data analytics, and also the role of IT-enabled solutions, because that will actually be the future. And look forward to the collaborations with the Russian Academy of Sciences and assuring all support and cooperation. Thank you very much for this opportunity. Now we have very distinguished scientists speaking on the first topic. We have Mr. Sanjay Patil and Dr. Shobhit Singh Chauhan and Mr. Rishikesh Chormore from the CSIR's Central Salt and Marine Chemicals Research Institute in India. And I'm sure that these presentations by them will be extremely useful. And I request the team from CSIR's Central Salt and Marine Chemicals Research Institute to start their presentation. Thank you very much. We look forward to the first presentation.
So I'm just sharing the screen, just a minute. So am I audible, sir?
Yes.
Okay. Honorable delegates, eminent scientists, all my colleagues and speakers from India as well as Russia, a warm welcome to this session. And as I am opening speaker, I would like to thank all the organizers from India as well as Russia and the eminent scientists for giving us the opportunity to present our work and our technology, which is actually related with the disaster management. So we at CSIR-CSMCRI Bhavnagar, we are working in the area of desalination and water purification since many decades. And we are working on the membrane-based desalination technologies, basically in RO, ED, and thermal technologies such as solar steel. Just as my senior delegates and dignitaries have already said, right from Professor Anatoliy, Professor Sain, and Professor Vinod Menon, I am just continuing on that line in the prospect of Indian conditions. So CSIR has given more impetus on water as a research priority and has developed state-of-art brackish water reverse osmosis TFC membrane technology. This thin film membrane technology is basically the hard core of water purification, as it has a very low compaction rate and ability to work under wide pH range, which has resulted in a longer membrane life. So this developed technology, which is robust in nature, can handle any sort of feed water, which may be seawater, mine water, harmful contaminated arsenic, fluoride, nitrate, brackish, turbid. So any nature of feed source water can be handled by our technology. So CSMCRI has made a foray into this seawater desalination also, based on two-stage desalination design, utilizing its indigenously developed brackish membrane technology. Just as my senior colleagues and eminent scientists have already stated, Professor Sain and Professor Menon has already stated that India is highly vulnerable to floods and cyclones. So floods are a recurrent phenomenon and which causes massive losses of lives and damages to. Now, having this technology, how we can apply this technology on ground to the people when they actually need it. Now, this was the basic aim of our directors and scientific staff, that how this membrane technology, which is developed in the lab level, can reach the people when they actually need it during the times of disaster. So as I have already stated earlier, that our desalination, we do work in other areas like salt, seaweed and other areas, but this is also one of our core areas of our research, that is the desalination. So we have a wide array of desalination system, work in pressure driven, ED, thermal steel, just as I've stated. Now to apply it on ground, what we have actually done for societal benefit is that we have already developed and designed a van. Initially, a bus was to take the social responsibility of providing safe drinking water, especially to the peoples who are affected by the calamities. Calamities may be any sort, like Sir stated, right from lower Himalayans, like Uttarakhand floods, to Odisha floods like Phylline, Fani. We use or apply our technology when the disaster has occurred, and to provide the drinking water solutions, which is the best we can do with the technology we already have. So we are already into this work since decade or more, and we have already served people who are affected by the various disasters, like in Orissa super cyclone, you can see Kutch earthquake, tsunami in Tamil Nadu, cyclone Ayla in West Bengal. From coastal areas to Himalayan to plain areas, we have already served people and will continue to serve in much better fashion, and how it can be bettered. So based on that, what we have done is that we have developed a van, a compact and energy efficient unit without compromising much on the capacity of the RO plant. So first, a mechanically suitable van is being developed, in which we have installed our water desalination technology, so that this a complete package of mechanical as well as indigenously developed membrane technology module can reach the people on ground as and where they are affected by any sort of disaster, so that the potable water solutions can be provided to them. So keeping this motto in mind, initially we designed a huge bus which was having a capacity of 4,000 liters per hour, capacity of ultrafiltration, 4,000 liters per hour, capacity of brackish water desalination, and seawater reverse osmosis technology. So this, as we all know, that reverse osmosis technology basically is a pressure driven technology. So pressure driven technology obviously requires external power, and whenever an area or a state which is being affected by the disaster, generally we come to know that availability of power in these areas which are affected by natural calamities is probability is almost nil. More than 95% of the cases, the electricity is not available. You can provide the food via various medias, packets, even you can throw it from the air by helicopters, but to provide the drinking water solution becomes a huge challenge, since the groundwater is contaminated, the floods, due to floods. So the water which is basically available from wells, ponds, sea, or any resource is not at all feasible for drinking. So we generally target these areas and see that our module, this bus, reaches to the affected area and provide people hampered by the drinking water solutions. So just as I said initially, we have designed a huge bus, which you can see in the present slide, which has served in the various areas. But since you can see the module is quite lengthy, means at least 37 to 38 feet of length was there, and it has served in various parts, but it has a limitation of moving into the terrain areas. As Professor Sain will agree with me, in Uttarakhand, there is a limitation by a road transport department that the certain length and width vehicle cannot reach a particular area even if it is affected due to the dimensions. So we at CSIR-CSMCRI has worked recently on the technology just 3 years back, and we have developed a small van, which you can see on the right side, the new van, without compromising with the capacity of the desalination of the water, which is almost at par with our initial module. And you can see even the power developed is more. So we have worked on the mechanical engineering part, developed the power from the van, which can reach to the narrow roads and terrains and reach the affected area more conveniently compared to the initial module. And we have also executed this van in the recent disasters which has happened in India. So the unit is a mobile unit housed in a body container, which is mounted on a van and can be taken at various places as per requirement. We hardly use chemicals. This is the beauty of our technology, that the desalination part, which we carry out, our membrane technology is such a robust and efficient in nature. We hardly need any chemicals except for washing of the membranes and also. The unit is fitted with a generator or alternator, which is directly coupled to the van engine part. So the power developed from the engine itself is utilized using a power takeoff and alternate. I will come to that slide. So that the energy developed from the engine is utilized via generator, and we have designed it according to the requirement of the power for our desalination plant. So for example, our desalination plant is 15 kilowatt. So accordingly, we have the power alternator system, which we have developed. Just so you can see the complete working working I have shown just by a ray diagram, that the main engine of the vehicle, the main shaft, generally it goes to the rear differential, so that whenever we don't want to use a desalination plant, we want to run the van on the road, it will run by disconnecting the power takeoff from the alternator generator and just having a regular line of power transmission from center bearing power takeoff to rear differential gear. But when it is stationed at an affected place at disaster management, finding the resource may be a well, pond, sea water, or a river, any sort of feed source, wherever available, we can station this vehicle over there, just have this mechanical lever arrangement and disconnect the rear differential shaft, take it the auxiliary shaft to the alternator, then to the control power, so that the power desired is available at the control panel. And using this power, we can run our desalination system, which is very self-explanatory if you see the power transport flow chart. So this is the core of what happens inside. You can see the yellow part is the alternator generator. This is this portion. This is where the engine power is being drawn via this propeller shaft. So this is the power takeoff unit. This is a differential shaft, and we transfer the unit using the belt and pulley arrangement to the generator, from where electricity is being drawn into the control panel. But the beauty of this van is that even if the power is not available, you can have this sort of mechanism to get the desalination plant driven. But if the grid power is available, we have the flexibility to withdraw the grid power and operate the vehicle based on grid power. So the flexibility is for any sort of calamity or challenge which is being posed to us, and we can take it and move forward in any adverse situations. Just this is a technical part of the power take-off system, which disconnects the differential shaft and takes it to the power alternator. Since the driveline design torque is very high, we require hardly 25 to 30 kilowatt of maximum power available at our alternator generator. So the PTO auxiliary transfer torque is around about 72 kilogram meter, and the gearbox ratio we have designed as 1:1, so that the total power is RPM. The desired RPM we can adjust as per the requirement of the electricity voltage at the output. And this is what the system we have installed inside the van. Generally, as you can see, the vehicle engine power is drawn alternator. If grid power is available, we can draw it to the electrical panel. But in such cases, as everyone will agree, we hardly have any electricity available. So we draw it from here. If the source, whatever source is available, we use a submersible pump and then push it to the booster pump, water of any contamination of any nature, and via that we pre-treat it.
Mr. Patil, another 3 minutes, please.
Yes, sir. Yes, sir. So this is a robust pre-treatment system we have, and from here, looking on the fluid source, we can use it for ultrafiltration. If it is only turbid and TDS is not an issue, we can simply control the walls and pass it through ultrafiltration and get the product water. If it is brackish, we will just close the control valve, to which you see on your screens, and pass it to the high pressure pump. And as per the osmotic pressure, we can have the operating pressure through these pressure vessels, which you can see. We have the 8-inch module, 1 meter length. So 2 pressure vessels are used in series, and we can also use the reject so that there will be zero liquid discharge. You can again send back the reject to the resource and have the product water at the rate of 4,000 to 5,000 liters per hour. So this is a complete unit line diagram you can see, which is installed inside the vehicle and which has been effective, and we have already tested it on field during calamities. This is just a miscellaneous solar power also available on the van, which we use to run various electrical units. As you can see, the glimpses of desalination van serving on the film during the disaster. We have served right from Himalayan tsunamis to Odisha Phylline, Fani, Kerala floods recently. And these are some glimpses of a recently Tokte cyclone, which affected, as everybody is aware of that, which was very severe, and its center point was Jafrabad in Gujarat region near Diu and Daman. There, we have taken this van and served the community which was affected to larger extent for at least 8 to 10 days and solved the potable water solution unless the electrical power was restored in the affected areas and the water supply was restored. Similarly, you can see recently Maharashtra was affected by floods in Konkan region. So we have reached, and this design development and our technology has yes, sir. So these are the advantages of our unit, the complete technology package which serves on the ground and also almost works on plug and play configuration. And we have also served some villages which are affected by drought and having groundwater available but not drinkable. There also we have served. So not only the disaster of this sort, but also disasters of like drought sorts. So this is the uniqueness of mobile. It's compactness, supplementary power, and to handle the water of any TDS and of any nature, and it can reach the almost remote places affected by the disaster. This is the initial one which I was talking about, and we have made modifications. You can clearly see the technical changes without compromising with the capacity of our potable water delivery. And this is our technology which has been serving, and we will continue to serve with whatever modifications we can make for the betterment of the people and for providing solutions. Thank you, sir.
Thank you very much. I'm sure that this presentations will be available to the participants who are registered, so it will be helpful. Thank you very much. We also seen the way in which desalination has been done in Lakshadweep Islands also, and how water has been, ocean water has also been made available for drinking. So these are some of the solutions which can also be. I hope that the technology is also patented, and then we'll be able to also share it with other countries who are interested in collaboration.
Absolutely.
Thank you.
Thank you, sir.
Thank you very much.
Thank you.
We now have Dr. Viktor Novikov, who will be making his presentation. I request Dr. Novikov to initiate his presentation, please.
Okay. Good morning and good afternoon at the same time. My name is Viktor Novikov. I'm working for the Joint Institute for High Temperatures of Russian Academy of Science, and my laboratory of pulse power systems for geophysics studies the electromagnetic triggering phenomena in seismology in cooperation with the Institute of Physics for the Earth, Institute of Dynamics of Geospheres, and Research Station of Russian Academy of Science located in Kyrgyzia at the Tian Shan Mountains. The motivation of this research today I will talk about application of our results on electromagnetic triggering phenomena for possible earthquake control. The motivation is clear because the over 25,000 people are killed by earthquakes annually, and nearly 60% of all fatalities due to natural hazards in the 21st century were caused by earthquakes. In the last century, more than 2 million people were killed by catastrophic seismic events, and the forecast for the current century is very sad that in spite of success of seismology, in spite of earthquake engineering, over 3 million deaths is anticipated for the current density. And you know that the earthquakes, strong earthquakes, are accompanied by indirect and direct huge economic losses. And according to conclusion of, for example, China Earthquake Administration, the earthquake begin to danger of sustainable development of national economy. When we look to the landscape of the battle against earthquake, we see the three main directions to solve the problem of earthquake hazard mitigation. First, the earthquake prediction, then earthquake engineering, of course, and I will talk about the earthquake prevention. At first, I'd like to say that earthquake prediction is the blue dream of in seismology, because to predict means to be prepared. And it is based on the supposition that impending earthquake should be accompanied by precursors, some physical phenomena before the strong shock. And the problem will be solved when we can answer the question when, where, and how strong will be impending earthquake. Nevertheless, you know that today there are no reliable method of earthquake prediction. Only two examples of the success and failure of short-term earthquake prediction. At first, you remember that in 1975, the strong Haicheng earthquake hit the city of Haicheng the magnitude was more than 7, and fatalities were over 1,000 people. But due to prediction, due to short-term prediction, many people were saved because estimation of the death toll was more than 150,000 people. Nevertheless, at the just after the year in China, in Tanshan province, the earthquakes with a similar magnitude hit the region around Tanshan in Hebei province, and it occurred practically without the precursors, similar to Haicheng earthquakes, and fatalities in this case were at least more than 200,000 people. So I'd like to show another example of failure of earthquake prediction, namely at the Parkfield area in the United States, California, where the earthquakes, moderate earthquakes with magnitude about 6, were occurred at approximately similar recurrent intervals. And they anticipated the next earthquakes in 1998, sorry. And in this connection, in this area, the United States Geological Survey concentrated the all known the method of earthquake prediction. But the anticipated earthquake occurred only in 2004, practically without any known precursors. Keeping in mind that earthquake engineering, of course, this direction is very promising because the building the strong structure will provide their resistance to strong earthquake shocks. And we see the impressive results when the success in earthquake engineering allows to build the very high buildings in seismic prone regions like in Los Angeles, in California, and in other seismic prone areas. Nevertheless, there are impressive results, but after the earthquake, you see that very strong buildings simply fall to the side, and the economic losses are inevitable. So, I'd like to remember this forecast for the current century. Of course, maybe in the near future, the methods of earthquake prediction will be developed. But at the same time, we propose to consider another approach, namely to consider the possibility of earthquake control by man-made impacts on the earthquake source. It is well known that earthquake may be triggered by physical impact on the earthquake source. In this paper, this is a global review of human-induced earthquakes by human activity, various activity, injection of fluid, for example, into the Earth's crust, which may provide the triggering earthquakes. And there are many examples of induced seismicity in different areas of the globe, and this is well known and well established fact. And it was supposed that artificial variation of the Earth's crust stresses may be used for earthquake control. I'd like to remember the results obtained in the liquid during the injected liquid waste volume into the well at the Rocky Mountain Arsenal in Denver, Colorado State in the US, and earthquake activity. You see the good correlation between the volume of fluid injected into the crust and the number of earthquakes. After that, there were some proposal on application of this phenomena for earthquake control. But in the United States, there is some skeptical view on this problem. And at the site of the USGS, you can see that this impression that we cannot prevent natural earthquake from occurring, but we can significantly mitigate their effect by identifying hazards, building safer structures, and providing education on earthquake safety. The first question: is it possible to manage of so huge energy accumulated in the Earth's crust, which is suddenly released during the strong earthquakes? But the mankind has the experience on managing of the huge energy. I mean the nuclear energy, which is comparable with the energy released during the atomic bomb explosion and the Earth's energy released during the catastrophic earthquakes. But you know that the mankind have the experience in managing and of the nuclear energy, and this is the way how we can manage the energy of the earthquake accumulated in the Earth's crust. In the former USSR, we carried out the electromagnetic experiments with pulsed MHD power systems when we injected the electrical current into the Earth's crust for deep electromagnetic sounding of the Earth's crust in various areas of the former USSR for scientific research, for oil and gas electrical prospecting, and the very interesting results were obtained during electromagnetic monitoring at Pamir and northern Tian Shan, where we carried out the experiments with MHD generator, which was connected to the emitting dipole, and we injected the pulses of electricity into the Earth's crust. And for two different geological regions of Pamir and northern Tian Shan, we obtained the similar results: sharp increase of seismicity after injection of electrical current into the Earth's crust. So you see here the picture of local seismicity, the number of earthquakes per day. 0 is the injection of electrical current into the Earth's crust. You see a sharp increase of local seismicity in the kind of weak earthquakes, and then it returns to the previous level. That means the part of tectonic stretches were released by weak seismicity. At the Garm test site in Tajikistan, at Pamir Mountains, we observed the activation of unknown fault. You see here before electrical pulse injection, and this is after. So we activated the unknown fault. So these results were confirmed by laboratory experiments at the different press equipment when we apply the electrical pulses to the samples of rocks. And you see that when the electrical generator was on, when the electrical current flows through the sample, it is increase of acoustic emissions recorded from the sample. That means that after under the injection of electrical current into the rock sample, the crack formation is increased too. So this is another press equipment and another example of behavior of acoustic activity before and after the electrical processing of the rock sample. In our institute, we developed a special press equipment to avoid some additional noise, acoustic noise from hydraulic equipment, and we obtained the similar results. So this is quiescence phase, and this is great area. It is initiation phase when the electrical current was applied to the sample. We see the increase of acoustic emissions during these experiments. The similar results we obtained at the spring block system. It is a well-known model of the seismogenic fault. So this is a platform and the running block. So this is a model fault between the fixed and running blocks, and running block is loaded through the spring by electromechanical drive. And when we apply the electrical pulses into the simulated fault, this is the pictures of this experimental facility. So you see here, so when we apply the DC current, very low, 3 milliamps, this is electrical pulses with the frequency of 200 hertz. With some delay, we observe the laboratory earthquake, sharp moving, sharp slip of the running block along the platform. So this is the view of moving block with electrodes, which is turned to the side for clarity. So after that, we continued the experiments, and these experiments, these tests are still underway. The northern Tian Shan near Bishkek city in Kyrgyzia, when we employed the electrical pulse facility ERGU 600, which is three times, which generates the electrical current 3 times less than a pulsed MHD generator, and we observed a similar picture. So before it is the number of earthquakes of different magnitude before electrical current injection and after. So you see here for different areas, you see the increase of number of earthquakes which are initiated or triggered by electrical current supplied by this facility. So this is the picture of epicenters of earthquake. This is before electrical current injection. So this is location of ERGU system. And after injection of electrical current, you see that occurrence of, in this area, occurrence of a weak earthquake, which are triggered by this electrical current. When we consider the behavior of microseismicity, so this is a great area. This is the series of electrical current injection into the Earth's crust at the different distances from the electrical dipole. We observe the increase of microseismicity for various seismic stations, and now we may conclude that this electrical processing of area resulted in a decrease of number of strong earthquakes here in this region. So that means due to triggering of weak seismicity, we practically eliminate the strong earthquakes in this area. I mean the area of the Bishkek test site. It is 100 per 100 kilometers square. So within the last 40 years after starting these experiments, we don't observe the strong earthquakes in this area. So this is another example.
Dr. Novikov, another yes. three minutes.
Okay, I'll finish. So we observed the similar geoacoustic emission increase during the session of ERG system. You see here the blue lines. This is injection of electrical current. You see that crack formation in the Earth's crust is increased like in laboratory experiments. Of course, after publication of the first results, there was some discussions in the New Scientist, and there was some skepticism. For example, to release the energy stored in the potential magnitude 7 quake, for example, would take about 30 earthquake of magnitude 6 or more with the less magnitude. So, and when we will try to reduce the magnitude for safe level, so we should trigger about 10 quakes a day for 300 years to drain off the stress. But today we consider not the triggering earthquake and to release the tectonic stresses by weak seismicity, but just now we consider the way to transform the normal earthquake to the slow earthquakes, because you know that there are several types of earthquake. For normal earthquakes with the velocity of fault rupture about 3 kilometers per second. Then there are low frequency earthquake, very low frequency earthquake, and slow earthquake, or so-named silent earthquakes, which occur with a velocity of rupture less than 0.01 meter per second, without radiation of seismic energy in the type of seismic waves. So, and this transformation, just now we checked the possibility of this transformation of stick slip behavior of the fault and transformation to slow slip events or creep in the model fault. We have the machine which simulate the stresses in the fault similar to natural conditions, and we observe that it is possible when there is a variation of the fault material, the simple stick slip behavior will be transformed into the creep. So the similar results were obtained. So this is laboratory earthquake, and when we injected the water into the contact area, this behavior is transformed to the simple creep. So, and the concluding remarks. Of course, today it is too early to speak about results obtained and ready for application for development of a real technology of earthquakes. But we see that example of seismic activity variation by the man-made impact on the Earth's crust in various regions of the globe confirm the possibility of earthquake control. The results of the earthquake control should be the transformation of the stick slip mode into slow slip events or creep. And in our opinion, it is possible. The most flexible method of artificial impact on the seismogenic fault is an application of electrical pulses injected into the Earth's crust, taking into account the possibility of changing their parameters in a wide range, as well as mobility, compactness, and environmental safety of the electrical current source and its relative low cost. For example, this comparison with the injection of fluids into the crust through the deep wells. When choosing a method of impact on a local zone, it is necessary to take into account the possibility of initiation of strong earthquakes due to the redistribution stresses in the fault caused by artificial impact. So the reliable models describe this phenomena are required, and we are working on development of this model. And after that, in the new field experiments, the electrodes of emitting dipole should be installed directly into the fault in the zone of repeated weak earthquakes, analogous to the Parkfield region in the USA. And just now we know some areas in the northern Tian Shan where these experiments may be continued. So thank you for your attention, and if you have any questions, I'm ready to answer it. Thanks.
Thank you very much, Dr. Nabokov. We now have Dr. Kapil Gupta of IIT Bombay, the Indian Institute of Technology, Bombay, and he will be speaking on urban floods. And he has been one of the pioneers working on the National Disaster Management Authority's urban flood management guidelines, and also the flood management guidelines during normal situations. And we see a lot of floods happening in many parts of the country and also in many parts of the world. So we would really benefit from this intervention by Dr. Kapil Gupta on urban flood risk management, disaster risk management. Urban floods and urban disasters are increasing. And so he'll be making a specific reference to the case study in Mumbai, 2005, and also later, repeated in many years. Dr. Kapil Gupta.
So thank you, Professor Menon, and good morning to all the distinguished scientists from both India and Russia. I had the honor of visiting Kazan in 2019 for the formulation of the IPCC guidelines on sea level rise and cold climates. So beautiful country. And I hope to be collaborate in future as well. So I will now share with you some of the works which we have done for Mumbai after the 2005 floods. So Mumbai is located on the west coast of India for the benefit of our distinguished Russian scientists, as you can see here. And Mumbai was basically an island, and it was gradually filled over. And now we have around 437 square kilometers with a population of 12.48 million in 2011. And we have a high population density of 20,000 people per square kilometers. So in 2005, on 26 July, Mumbai received the highest rainfall of 944 millimeters within 24 hours. And all communication and transport failed. Public transport came to a halt. People were stranded. There were several loss of lives of both human and animals. And so this is the rainfall distribution as recorded by the Indian Meteorological Department. As you can see, we had 190 millimeters in just 1 hour. And in 4 hours, we had 481 millimeters. And total of 865 millimeters in this 24-hour period. So as you can see, this is more than the annual average rainfall of many of the cities in India and abroad. Even London gets only 611 millimeters per year. And this was one of the biggest events in terms of flood disasters. So at that time, the IMD did not have automatic weather stations. They had only 2 weather stations which could monitor rainfall only in 24 hours. So there was no way of knowing what could be done. So I will briefly describe to you 4 of the main studies which we did for the Mumbai city and the authorities in the next 15 minutes. So we made use of technology and software for finding the solutions. So, we will quickly review the real-time flood alert system which we developed for the municipal corporation. Then how we use this to develop the decision support system for flood forecasting. And the airport was shut down for 3 days. So we also looked at modeling the Methi River flowing under the airport runway and determining the size of the increased culvert below the airport runway. And finally, we also developed the flood risk assessment for the disaster risk management master plan of Mumbai. So after, as I mentioned, there were no real-time weather stations at that time. So immediately after 2005 floods, we surveyed the city, we located, identified spots for installation of the automatic weather stations. And in the first phase, we chose 30 fire stations within each sub-catchment of the Mumbai city. And in the first stage, we were able to mount 30 automatic weather stations all over the fire stations. Fire stations were chosen because the fires are the people who are going to be rescuing the people anyway, and they are the first responders. And subsequently, all these automatic weather stations were connected by internet to the central control room. So as you can see, this is the automatic weather station having the recording all parameters of weather, rainfall, wind direction, temperature, humidity, and so on. We also installed a ultrasonic flow gauge on the downstream of the Methi River to measure the water levels. So this shows more details. So the data can be seen on the console. There is no need for a UPS or electricity supply. Everything is managed through the force of the falling water and the batteries within the console, which last 4 months. And this was kept in the central disaster control room with all hotlines to the various Army, Navy, Chief Minister, and other personnel involved. So this is the laptop, and you can get an idea of the console that gives you all the weather parameters. We also installed the flow gauge at the Methi River. As you can see the installation here. This is the ultrasonic flow gauge. So this is within the municipal corporation premises so that the safety of the equipment is ensured. And this is the console and the water level that was measured in the river. Subsequently, the system has been updated, and now all the weather parameters such as temperature, humidity, wind, pressure, tide timings. We are a coastal city, so tides have a great role in influencing the outflow of the water. And this is the display on one of the days when we had rainfall in Mumbai, 23rd September. And anybody with access to computer can see this. And now a mobile app has also been developed. So the data is immediately available on the mobile to anybody who sees it. Now from this data, second part was to develop a flood warning system based on real-time rainfall data and issue the water level forecast. So now the flow times in an urban area are less than 45 minutes. And so we use support vector machine for rainfall forecasts and for forecasting 1 to 2 days ahead to 1 hour. So this shows the location of the Methi River. This is the Methi River catchment. It is a small river, about 15 kilometers in length before it joins the Mahim Bay. And the catchment area is around 7,200 hectares. And this is the profile of the Methi River. As you can see, in the first 8,000 meters, it has a rapid fall. After that, it is almost flat because of the tidal interactions between the sea and the river. So we had the 5-minute rainfall data from the automatic weather stations. And we also installed one in IIT so that we could get real live data inputs. The water levels were known at the Kantinagar gauging site on the Methi River, and the longitudinal section and profile of the river known. So we put all this data into the software. This is public domain software, the HEC HMS and the HECRAS river geometry. So after putting the data into the software, we were able to simulate the flows from the rainfall and get the observed and predicted water levels from observed data. So we actually had our students sitting at the site measuring the water levels during the tidal flows, and we were able to calibrate the model. Successively, we also got the runoff and rainfall were calculated for various combinations without overflows and with overflows from the 2 dams upstream. And we also got a rating curve for the discharge and the gauge height. So once the model was calibrated, it takes less than 5 minutes to run the simulation and forecast the value of rainfall and water level. Down of concentration to the most critical low-lying areas is 30 minutes. And so with a lead time of 20 minutes for rainfall forecast, and 45 minutes would be available for the evacuation of relief once the simulations are done. So this is a summary of the method. This has been published in the ASC Journal of Hydrological Engineering. So those interested can look at it in detail. So we have the recorded rainfall, we put it in the hydrologic model. We have the catchment runoff. This gives the rainfall runoff curves. We have the river geometry. We put it in the RAS model. We get the water levels. We get the depth discharge curves. Subsequently, we have the rainfall runoff curves. Then from our rainfall data, we use the support vector machine to generate the 15-minute ahead rainfall. And this goes into the model. We get the runoff. And once we have the runoff, we can correlate it and predict the water levels. We issue the flood warning, flood alert, and the dissemination system. So in 2013, we had the opportunity to actually use this, and the people were evacuated from the low-lying areas because our model was predicting that the water level is going to go up and submerge the people. So with this simple tool, we are able to alert the authorities, and the authorities are able to put the machinery in motion to evacuate the people from the low-lying areas to a safe area. Then the second thing which I mentioned was that we also carried out studies on the Mithi River, which passes below the airport. So before the floods, only these 3 culverts were existing. So after carrying out the study, we determined the size of the additional culverts that would be required to go under the main airport runway. And when you come to Mumbai, you'll find that your airplane actually goes over this both while landing and during takeoff. So it will give an opportunity for you to see the widened culvert. So quickly describe what we did. So again, this is the Mithi River. The airport is here, and Mithi River goes under the airport runway at this point. So this is how the Mithi River flows under the main runway of Mumbai Airport. So as already mentioned, we had so much rainfall on 24th July. Entire airport was submerged, and traffic was suspended for 48 hours, and the Mithi River overflowed. So what we did was, again, we had the data, we put in the data, we modeled the system of, we also put in the river data, we had the river hydraulics, we got the water levels. So we calculated the peak flows for the rivers, and we also put in 20% additional rainfall, design rainfall for climate change. So we have designed it for 120 millimeters per hour for 3 hours. So it can withstand 360 millimeters of rainfall happening in a period of 3 hours. And so initially we had proposed that we will widen the river from under the runway, but this reduced the takeoff distance from the runway, and this was not feasible. So subsequently we revised the study. We carried out the study for a different configuration, and ultimately it was decided that 2 culverts of 12 meters each width would be provided. So ultimately we had this curved portion which changed the hydraulics of the system due to the curvature, and we had to resize the systems, and ultimately we had a bigger system and safer system which enabled the flights to take off even during the construction of the additional culvert. So this was an open cast excavation, and the flight operations continued from this end. If it had been done from here, then this would have not been possible, and we were able to do with the remodeled hydraulics. The works were carried out without disruption to the normal operations of the airport. So this is how it looks in the Google Maps. So this is how the 2 culverts go from under the airport in a diverted manner. So it provides enough taxiway space, etc., for the planes to take off. And now this airport has been functioning since 2016 without any overflows from the river. There have been no disruptions due to the flooding of the airport, although weather conditions do necessitate closure of services for some time due to high wind speeds and cyclones. The other measures which we have designed for the Mithi River are the sizing of the walls, flood walls for the Mithi River. So in the downstream, 6-meter high flood wall has been constructed. And in addition, since there was no space for providing...
Dr. Kapil, yes, another please? 3 minutes, 3 minutes.
Oh yes, I will finish, don't worry. So we had no space for providing holding ponds. So we actually provided a weir cum orifice on the river itself. So during normal flows, the water could go under the orifices here. And when there was heavy rainfall, the weirs themselves acted as a barrier. So we could have 3,000 cubic meters of capacity beyond these walls. And similarly, we had another weir on the upstream on the Jogeshwari Vickery node. So another 3,000 cubic meters here. So this delayed the flow time to the low-lying area by 10 to 15 minutes, providing additional time for recovery and rescue for the low-lying areas. Now, presently, we are working on improving the flood resilience for the Mumbai suburban railway network. So this is a work in progress, and hopefully we should have a draft plan out by the end of the year. and the implementation would of course be undertaken by the Indian Railways based on the logistics. We also developed the flood risk assessment for the disaster risk management master plan for the Mumbai Municipal Corporation. So we had the SRTM, DM of the Mumbai at that time. We generated the contours, we delineated the catchment, and we identified what is the inundation depth and what is the flood spread for each of the wards. So for all the 24 wards, we did this. This shows the inundation levels for Ward A. This is for 50 millimeters and this is for 100 millimeters. So we calculated the number of population affected for each of the wards. And this shows that from the studies, for 100 millimeters, the Ward E would be having the maximum flood spread, whereas the number of people affected would actually be in the other ward. They would not be in the other ward. So this study identified that enabled the corporation to prioritize the wards which would be affected and the people who need to be evacuated. So to summarize, we have used technology in terms of rain gauges, flow measurements, software, detailed hydrologic procedures to improve the urban disaster resilience to floods. So resilient cities should have an automated real flood warning system for flood alerts, an integral part of the master plan. This should use inputs from all available technologies, satellite maps, radars, automatic registration, smartphones, and we should use information technology to disseminate the information real time. So, and of course, enhance the flood resilience through improvements in the existing infrastructure based on sound scientific studies. So thank you for your attention. Otherwise, one can enjoy the flooding as shown in this figure. Thank you very much.
Thank you, Dr. Kapil. This is a very useful and very interesting presentation. I'm sorry that I have to, restrict the time, because we have several presentations and we have another session following. So we now have Dr. Alexei Liskin and also Dr. Alexei Brixin from Russia, speaking on monitoring the physical condition of buildings, structures, and operating equipment by seismic methods to reduce the risk of sudden collapse in buildings. Liskin, please.
Hello, dear friends, but please give me an opportunity to demonstrate a screen. It is busy now. Could you hear me?
Yes, Dr. Kapil, can you?
Yes, I can hear you, and now it is opened.
Okay, I'll try. I'll try one more time again. No, so now screen is busy by other. Okay, maybe right now. Oh yeah.
Thank you.
Just a moment. Cannot find. Oh yeah. So do you see my screen?
Yes.
Okay. From the beginning. So good morning, dear colleagues, ladies and gentlemen. Today we are going to present a report named Monitoring the Physical Condition of Buildings, Structures and Operating Equipment by Seismic Methods to reduce the risk of sudden collapse.
I'm sorry. I fear we see something wrong.
What do you mean?
The Sain's original software Spectrum Seism.
Oh, okay. Let's try one more time again. And now, do you see the first slide?
No, sorry, we see nothing.
Okay, one more time again.
Yes, monitoring the physical condition. Yeah.
Yeah.
Thank you.
And is it now full screen mode?
Yes. Thank you.
Okay, thank you. So it's the title of our report, and our institution is a part of Geophysical Survey of Russian Academy of Sciences. It is the biggest geophysical budgetary organization in Russia. And the next slide will be, sorry. Yeah, write it. So there are several ways how we can study buildings and construction using seismometers. As a source, we can use maybe explosion or vibration source, or just a seismic noise. Anyway, to have an uniform mesh of points over the building, we need a lot of units, a lot of seismic instruments, seismometers. Okay, but we developed a technology in our organization, and now it is possible by using several seismometers, say from 5 up to 10, to make a measurement of the whole construction. Here is the example of studying the standing wave field on the Sayano-Shushenskaya Dam. It's a Sayano-Shushenskaya hydropower plant. And at figure A on right, you can see the measurements which are performed using only by 5 seismic instruments. And then these units are moved over and over to different points on the dam. And after the calculation on figure B, you can see the whole standing wave field over this dam. And at figure C, it's just the same thing, but after some filtration process. As a result, we can map natural frequencies of the dam in such a two-dimensional picture. And what is the difference between A and B? It is a different headwater level. So here it is 539 meters, and here only 500 meters. So the difference is clearly would be clearly seen here. So also we can study high buildings. Say it's a high building airship in Moscow, and we performed measurements using our technology. You see a number of points. Just moving our instruments from point to point, but we have some control points in red. And actually, we have, after all processing moments, we have a real data of standing wave approach, and it is theoretical modeling result. As you can see, it is a difference, not very much, but okay, we see it. So our method, our technology works. And what is important? Here you can see a record at Novosibirsk seismic station, and here at the upper part of the screen, and you see this is a kind of earthquake record, but all other hour, it's an hour, other hour, and then an hour, and so on, and go further. But it is a seismic noise, and we can use an information from this noise to understand how different oscillating systems like dams or different plants are working. What is the idea to operate, to monitor and operating equipment? So you know that the human brain is able, when we are listening to orchestra, our brain is able to make a difference. It hears different signals from, say, violin or claviolin or, say, piano, and we are able to make a difference by using only our ears. The same thing we can do with our seismic equipment, say, in order to investigate, to study their dam, a huge construction. And then we have original software developed in our organization named Spectrum Seism. The idea is quite easy to understand. We use a Fourier transform to construct a two-dimensional picture. On axis X, it is the frequency in hertz, and axis Y is devoted to the time. And then we can analyze any fragment of this record, of this amplitude spectra. Then you know that powerful plants such as hydroelectric power station, so it produces vibrations itself. And there is a difference between standing waves in open pipes and standing waves in closed pipes. It depends on the length of the pipe, and at the left you can see where seismometers are placed, and so they recorded all information about the water in this pipe. And when we perform a calculation of amplitude spectra, so we can see the dependence between the modes of working equipment, different modes, how it works. So we maybe personnel of this plant increase power, decrease power, change some operational modes, and all these things we can clearly see on amplitude spectra. This is the moment of accident at Sayano-Shushenskaya hydropower plant, and it is so our amplitude spectra, and we can see that first of all was okay. Then between these two blue lines, something has gone wrong, and this is the moment when the accident happened. It is there is no record at seismic station because there was no electricity. Accumulators, then power loss, accumulators, power loss, and here all reserve system are switched on, and personnel of the station is going to stop the water flow, and so you see stops and stops the last hydro unit. So we have a full picture of what has happened on the hydropower plant, and our next task is to analyze it and to interpret all the data from this spectrum. Again, it's another example. we have a vibrational source in Academy Town in Novosibirsk, quite powerful vibrational source. And here is a house, living house, where one of our seismic stations is situated. So when this vibrational source began to work, we can see the increase of natural frequency of this house. So maybe it is a resonant frequency for this vibrational source or something like that. But anyway, we can register this signal at the distance about 1.5 kilometers, and we can study it. Okay, on this slide, you can see the difference between old hydro unit and new hydro unit placed on Sayano-Shushenska power plant. And it is the difference. You see, a set of natural frequencies is quite great. And here we can see maybe one natural frequency. And we think that this effect is because of damage, continuous damage that water made to the blades of turbine by the time during the time. So this is not good situation, and maybe it is the reason why the accident has happened more than 10 years ago. Anyway, when we are speaking about turbines or about ventilation units, this is a scheme of ventilation unit. It's a very huge ventilation unit. But anyway, we cannot understand, we cannot study vibration of blades using the direct way. But we can put a kind of seismometer here, maybe, or maybe here, and we will see the full picture of standing waves, and not only standing waves, also with natural frequencies of this equipment, and how these natural frequencies change in the time. Here, when okay, there are two ventilation units, one and first and second, and from time to time they are switching from one to other. And on this picture, it is we can clearly see the moment when the first unit, ventilation unit, is stopped, and the second ventilation unit is switching on. So we can see everything, and using geophysical seismic methods, and this is great. We think so. Also, the next slide is devoted to comparison of remote recording of monochromatic signals. So we have a seismic instrument in 1 kilometer near the hydro unit of Novosibirsk hydropower plant. And we have another seismic instrument at the distance about 16 kilometers. But we can see that here it is the frequency. It is a record from station Kluchi from here, and this is a record spectrum, amplitude spectrum of a seismic record near hydro unit. So we can see it, amplitudes are weaker, but we can see them. And we accumulate.
Dr. Selesnev, another 3 minutes, please.
Okay, So the main idea is when we accumulate our signals, we can see our natural frequencies. So it depends how long is our seismic record. So this graph is for 5 minutes, and the last one is for 5 days. But we clearly see it. So we can use it in everyday monitoring of the operational equipment. Maybe I will proceed to the end and thank you for your attention. And what I want to say that we are open for an international cooperation, and we will be glad to have united projects with partners from India. We have the successful experience of cooperation with Taiwan and seeing in future to have the same experience in India. So thank you very much, dear friend.
Thank you, Dr. Selesnev. I'm sure that the Geological Survey of India and the scientists who are working in the field of structural and civil engineering, structural engineering, geotechnical engineering, and others, like Professor Ravi Sinha and Professor Kapil Gupta and others. And, we have Dr. Sain and many others, from the Wadia Institute of Himalayan Geology. Dr. Perumal is here. So they will be very happy to collaborate in terms of the international cooperation between the Russian scientists and the Indian scientists. And we can look at that as part of the recommendations. Now we have the next presentation, which is by Professor Ravi Sinha. Look forward to Professor Ravi Sinha from IIT Bombay. Is one of the leading, civil engineers and also actively involved at the national and international level, advising national government and also the government of Maharashtra, the provincial government, and many other state governments. And he's also been advising the World Bank through a primer which is prepared on climate change and many other documents. He's one of the leading scientists in India in the field of civil engineering. And he's also been very closely associated with the Earthquake Engineering Research Institute in many mega disasters and many earthquakes in the past. And we are very happy that he's here, and request Dr. Ravi Sinha to initiate his intervention. Thank you.
Thank you, Professor Menon. I would just share my screen. Is my slide visible?
Yeah, can you put it on full screen?
Yes, thank you. So I'm going to in a very short way discuss the whole nature of risk reduction and resilience. And the work which I'm presenting is along with a couple of my students. So the first question is that what is the risk landscape? Why should we worry about it? Is this the biggest problem, or is it one of the biggest problems which is facing mankind today that we should pay so much attention and devote so many resources for it? So in order to understand that better, let us look at our cities. So I'm just showing India's cities, and in many of the other countries, particularly developing countries, situation may be similar. So I'm showing as per the 2011 census of India. The 2021 census data is still not out. So as per the 2011 census of India, I'm showing the population of the 10 largest urban agglomeration. Mumbai, where I'm based, is the largest urban agglomeration as per that. And the key point I want to show are not just the population, which are quite large, but the last column, which is the population density, the number of people per square kilometer, because this is intricately linked to the disaster profile of our cities. So how do these numbers, 15,000, 20,000, even the lowest number is about 6,300, how do they compare with the global large cities? So if I look at New York, for example, then the population density is 1,800 per square kilometer. Tokyo, Yokohama urban agglomeration, which is the world's largest urban area, is 4,400. London is 5,900. So it's a totally different class of population densities we are dealing with in the Indian urban areas compared to the global cities. And so that is not the only issue of concern or issue of difference. If you look at the population increase in India, and this is again from the last 2 census data over 10 years, then we can see the kind of population increase in 10 years, which is unthinkable in many other parts of the world, where population increase over 10 years is of the order of 1% to 2% or something like that. Here, the cities' population are growing so fast, means the cities are densifying so fast that itself has an implication in terms of the disaster profile. Then we have other problems or other characteristics. In India, it is not uncommon for cities to be largely unplanned, to have large slum population because it's unplanned. The implementation of the building bylaws is insufficient. And all of these result in large proportion of non-engineered buildings or facilities. And also the infrastructure to the people is not keeping at par with the needs of the population. And also other issues are there. We see incremental growth. So buildings and infrastructure expand over time. So this, for example, is showing a building which seems to have grown over time, that there was a brick earlier, and then on top of that, there is flimsy metallic sheet. So mixed constructions also take place. Then insufficient maintenance of older buildings and infrastructure is also seen because of lack of resources. And also quite frequently, the construction materials which are used are not keeping with the building standards. So the key characteristics then are very densely populated, large cities with very dense population, which are rapidly growing, which experience poor compliance with the bylaws, have large proportion of non-engineered constructions, and even the engineered constructions may not be well maintained. So any initiative or effort to reduce disaster risk and improve resilience has to take this into account. And if we don't do that, then there's going to be a critical, you can say, impact on the effort of sustainable growth in India. So the question again is, how do we enhance the city's resilience, keeping these things in mind? So if you look globally, what we find is that there is hardly any success story of enhancing resilience in any major city of the world. There's a lot of investment in many cities, but we cannot really say that they are the success story. And even the few available examples, let us say partial success stories, they are relevant to cities with much smaller population, with much lower density, and with much smaller growth rate. So India does need to learn from these cities and from these examples, but we also need to take into account the unique characteristics of our cities that affect our resilience. So keeping all this in mind, we have initiated a research approach in India to ensure enhancement of resilience. And for our work, we consider primarily the resilience to seismic risk or earthquake risk for a variety of reasons. The main reason is that the risk of earthquake is so large compared to the risk of other factors from a resilience point of view, that if we are able to understand the impact on resilience to the earthquakes, then that would be also taking into account the smaller loss of resilience because of the other factors. And also the work which we do, we ensure that the resilience strategy is based on the Sendai framework of disaster risk reduction. Now, what is the Sendai framework? So Sendai framework, amongst other things, has articulated 4 priorities for action. The first is understanding disaster risk. So Sendai framework is very clear that that disaster risk management or disaster risk reduction is now a reasonably mature field, having been formally in existence for several decades. And a lot of the common knowledge, a lot of the observations from the field have already been built into the efforts which have been implemented so far. So we need to move forward. And the way to move forward is to increase the understanding of disaster risk in a more rigorous way. Then for the case of resilience, also priority 3 is very important because it clearly states that investment in disaster risk reduction should be for resilience. So they are recommending that you look into all parameters which may affect resilience and how that can be enhanced should be the primary framework under which the investment should be made. So obviously this again means that resilience or lack of resilience should be understood first before we can go to the next step or next generation of the quality of disaster risk management programs. So let's look at understanding disasters. So for example, here I have shown the map of India and the earthquake records or the earthquake locations of earthquakes which are there in our seismic catalog. And so it's not just the earthquakes which occurred in India, but also around India which were felt in the country. So you can see that the number of earthquake events in the map are well in excess of 60,000. And also you can see that earthquakes are spread all over the country. So there's no part of India or no city of India which we can say is perfectly safe from earthquakes. And in fact, if we look at the areas where the earthquake shaking is strongest, then the population of the country which lives in those areas, which is known as seismic zone 4 and 5, is in excess of 1 billion people. So which means that 1 billion people in just our country live in areas which has a high probability of damaging earthquake occurring. Now, how do we use this information for understanding risk? So the traditional approach is a probabilistic approach, of course. It considers the fact that earthquake risk is not deterministic, and risk depends on 3 main parameters, what is known as hazard, which is, for example, the location, size, and other characteristics of future earthquake. The vulnerability, which is looking into the ability of the structures to resist the shaking due to earthquake. And lastly, exposure, which is the location of the structure, whether it is located in area of strong shaking or not. And all these factors are probabilistic. So that is why the traditional approach of earthquake risk assessment is also a probabilistic approach. And broadly, the way it is done is that hazard, vulnerability, and exposure, under some probabilistic framework, they all combine together to get a probabilistic assessment of risk. So how likely and what is the probability of occurrence and so on. Now, the risk assessment for resilience also should be under a rigorous probabilistic framework while taking this forward. So the question is that, is this traditional framework sufficient to understand whatever information we need for resilience? And it turns out very clearly no. The resilience requires additional dimensions, so not additional parameters, additional factors. It needs additional dimensions which have to be understood. And there are 2 ways in which additional work has to be done. First is that elements of resilience are more expanded. So for normally risk assessment, we consider robustness and redundancy. Now, in addition to that, we also have to look at resourcefulness, how much resources can be devoted immediately after a disaster, and rapidity, how quickly are the functions required to be restored. And we have to look into dimensions of resilience, so technical dimensions, where are the capacities available to carry out technical tasks, organizational dimensions. This is related to the organizations which are running the government in their ability to take decisions on time. The social dimensions, the impact of those damages, economical dimensions, what happens to jobs and so on. So all of these factors also under a rigorous framework have to be a part of resilience framework. So the resilience framework under our group is actually under development, but this is just giving you a snapshot of what it is going to look like. And this is the part of the work which is already completed, but it is being expanded to also include other factors. And the key point is that that resilience framework will provide information not just on likelihood, but also on probability of certain events or certain consequences to happen. And also, so which means that we can go not just to the most likely occurrence, but also probability of more rare occurrences. And some of the preliminary results are already quite revealing. First of all, we find out that design standards which are used in India are not conservative for certain types of structures if they are located in high seismic regions. So we are actually finding that the design standards in the high seismic region needs to be revised the way the earthquakes are specified for design. And also we are finding that the use of probabilistic seismic hazard assessment, which is the benchmark or the rock for most of the international standards in the world, does not assure safety or resilience. So there would be a massive retooling of the design standards required all over the world once the resilience framework is completed. And the thing which we are finding is that the framework permits us to simultaneously target several performance dimensions at the same time. So which is what we want in resilience. So to conclude, I would again like to reiterate that India's urban areas have very high population, are densely populated, and have several undesirable features. And the infrastructures of the cities are also insufficient. And several cities of India have very high risk because even the earthquake hazard is so high. And all of them make the resilience very far away from where it should be in order to safely and quickly recover from earthquake disasters. So, so obviously more has to be done, but we are recommending that disaster resilience in India should be improved on the basis of science and should be driven by knowledge and not just perceptions. And recent research to develop a framework to assess multi-performance resilience uses a consistent mathematical framework, and we have shown that it is possible to do that. Even though the problem is so complex, it does not mean that mathematical frameworks cannot be used for that. And what we are recommending is that such consistent framework should be used to understand the risk and use that to enhance resilience in future. So that's all I would like to say. Thank you very much.
Thank you, Dr. Ravi Sinha. This, I'm sure that there will be many questions which, the distinguished delegates will be sharing in the chat and also in the panel discussion, which follows after all the presentations are made. Given the IPCC recent report that, many of the cities which are actually on the, coastlines, would be very vulnerable to sea level rise, and especially Mumbai and Calcutta have been specifically mentioned that they're at high risk of sea level rise and global warming, and also possible impacts of cyclones, where we are actually seeing that. So anyway, we will have these discussions in the panel discussion, and I'm sure that there'll be more questions. Now we have Dr. Roman Krasnoporov, from Russia, who will be speaking on monitoring of geomagnetic activity in Russia and applications of historical data for spatial weather events. Dr. Roman, please.
Dear friends, do you hear me?
Yes.
Yes. I would like to thank our colleagues for organizing this meeting and for the honor to giving my talk. Comprehensive studying of the Earth
can we have the presentation on full screen, please?
Yes, it is in full screen. Do you see it?
Боковую панель, если можно, выключите. Мы видим с левой стороны все ваши слайды. Как-то ее можно убрать?
Знаете, я так.
Да, так лучше.
А вот полный экран видно?
Да.
Ага.
Роман, полного экрана не видно.
Ох. Так.
F5 попробуйте нажать.
And now, do you see the full screen?
No, we don't.
Oh, okay. I think that I will do it in this way. The comprehensive studying of the Earth can't be implemented without relevant and up-to-date data on our planet. The latter is provided by networks of stations and observatories that perform complex geophysical monitoring. And among them, it is worth to distinguish magnetic observatories that are currently one of the main sources of high accuracy time series that are used both for fundamental and practical tasks, including mitigation of risks caused by geomagnetic activity. A couple of words of the Earth magnetic field observed on our planet. So, the observable magnetic field has several sources. The main field induced by processes in the Earth's liquid core, it is 95% of the observable magnetic field. It changes in time on decadal scale. The anomalous field is caused by magnetized rocks on the Earth crust, and it generally does not change. And the outer field, caused by electric currents in the near-Earth space due to solar-terrestrial interaction, changes very rapidly. And this field, so these currents and solar-terrestrial interaction can cause some problems, which I will speak about a bit further. And in the right image, you can see the decomposition of the full vector of the electromagnetic field, F, into several components, orthogonal components, X, Y, Z. These components are actually measured by magnetometers on observatories. And another additional thing is that distinguishes a magnetic observatory from a magnetic station is that a magnetic observatory provides a full time series of the components of the full vector of the Earth's magnetic field. Hence, it provides the most valuable geophysical data on the changes of the Earth magnetic field. And why should we bother with this? So the relevance of geomagnetic data. The first thing is that geomagnetic data are still used in some practical areas. The axis of airstrips have the azimuth, for example, you see 27, this is the azimuth of the airstrip, and this azimuth is actually the magnetic one. Magnetic compasses are still used for navigation in the oceans and for aircraft, and also geomagnetic data are used for navigation of drill strings during the directional drilling. The point is that in northern regions, due to the proximity to the North magnetic pole, the disturbances of the Earth magnetic field can cause severe errors in navigation of borehole drilling devices, and that is why correction based on data provided by geomagnetic observatories is required. Another thing is the solar-terrestrial interaction. Coronal mass ejections from the sun interact with the Earth's magnetosphere, and hence the changing magnetic field can cause the so-called geomagnetically induced currents. So currents that are induced in long technological objects such as power lines and power grids, railroads, underground and surface pipelines. And speaking about geomagnetically induced currents in the power lines, it should be noted that during severe magnetic storms, it can cause to failure of transformators. For example, such a thing occurred in 1989 in the Quebec province, when due to a severe magnetic storm, the whole province had a blackout for more than 24 hours, and this was caused by the failure of transformators at power stations. And speaking about this, I want to say that data provided by geomagnetic observatories are very crucial for prediction and assessment of risks of the influence of geomagnetically induced currents in technological infrastructure. And what is done by our organization and by organizations abroad in order to provide sufficient data for the scientific and professional community. The development of the observatory network in Russia that has been performed for a couple of decades includes several directions. It is upgrading and existing the observatories toward the intermagnet standards. What is intermagnet? It is an international network of observatories which produce the most accurate and the most reliable geomagnetic data, which are used by in different ways. Moreover, this organization provides standards of performing measurements on observatories and standards on the construction of observatories. Hence, inclusion of observatories into this network is very crucial and very important. Another thing is construction of new observatories, because the current network is not extremely dense and we need to fill the gaps. And another thing is technological and methodological support of operational observatories in Russia and near abroad countries in order to be sure that all the data which are produced there are accurate and their quality is sufficient. Our organization, the Geophysical Center of the Russian Academy of Sciences, is deeply involved in this activity. Let's look at the map of active magnetic observatories in Russia. As we can see, the most of the observatories are located, the most dense network is located in the European part of Russia. Several observatories work in neighboring countries. For example, in Armenia, one new observatory, I will talk about it later. In Belarus, one certified observatory in intermagnet, and 4 observatories in Ukraine, including 1 Antarctic observatory. Speaking about the Russian network, currently we have 16 continuously working observatories. 10 of them are certified, and 1 of them is located in the Antarctic region, Antarctica, at the Vostok station. As we see at the map, there is a huge gap in Siberia and the Arctic region. These observatories, Snowflake, Sabeta, Samoilov Island, they are on the stage of deployment and they currently do not produce data. And the efforts of our organization, in collaboration with other institutions of the Russian Academy of Sciences and in Ministry of Science and Education of the Russian Federation, are aimed at filling this gap. A few words about the new observatories which were deployed not very long ago. One of them is located 600 kilometers to northeast from Moscow in the region of Arkhangelsk. This is a completely new observatory. It is located in a safe and magnetically calm region. and currently it produces the full spectrum of geomagnetic data, which are required by the intermagnet standards. Moreover, the data are assigned DOI, so they can be freely used by the scientific community and cited in literature. Another observatory is located not far from Moscow, 80 kilometers south of Moscow. It is on the stage of construction. Works started at 2019, and it should be mentioned that this observatory is located in a natural reserve. Hence, the data produced by this observatory would be free of technological interference. Unfortunately, the previous observatory, which served the Moscow region, the Moscow Observatory, which is also to the south of Moscow, the data from this observatory are interfered by the growing city. And that is why there is a need of new points of observations. Another observatory was deployed on the banks of the White Sea in the north of Russia, near the Kola Peninsula. This observatory is equipped with experimental magnetometric equipment. It works since 2018. The data are continuously measured and provided. And we hope that in several years, this observatory will be upgraded to the full-scale one, thus providing very specific and valuable data for the Arctic region. And speaking about Arctic region, another point of interest is the delta of Lena River in Yakutia, where the Samoilov Island Research Station was deployed several years ago, and as part of its scientific infrastructure, the project of a new magnetic observatory there was initiated in 2020, despite all the constraints of the pandemic. The pillar foundation for pavilions was installed. So this project is one of the most valuable, and we also hope that that the deployment of this observatory in this region will also give new data on the magnetosphere, which could be used by the community. A part of this, we also work with the neighboring countries and with institutions of the Republic of Armenia. And here, in collaboration, a completely new observatory was installed. It is called Gilagarak. As you can see on the map, it fills the gap in the Caucasus region. It was fully deployed in 2019, and now it provides data of sufficient quality, and we hope that this data would be also valuable. Another ambitious project is the Snowflake International Arctic Station, located not far from the Yamal Peninsula. This station is on the stage of design, and the most peculiar thing about this station is that it will be fully self-sustained, so it won't use fossil fuel for producing electricity and heat, but only the renewable energy sources, solar, wind, and hydrothermal. And one of the parts of its scientific infrastructure would be a new magnetic observatory. And I wanted to say that this project is of great importance great importance for the government of the Russian Federation, and this project is unique, and so it also will fill the gap in the Arctic region of Russia. And several words about the dissemination and provision of data. In the Geophysical Center, the Regional Analytical Geomagnetic Data Center is being developed. It was deployed here, and the core of this data center is the system Magnus, monitoring and analysis of geomagnetic anomalies in unified system. This is a hardware-software system, and the point of this system is to acquire data from the network of observatories, some of them I mentioned earlier, and from geophysical satellites, store this data in a unified geomagnetic database, perform its preliminary analysis, provide instruments for modeling and for visualization, and the main thing is giving online data access for end users without any serious restrictions. So all this data from the observatories which have been mentioned on the territory of Russia and neighboring countries are available for the scientific community from using this system. And as we started talking about data, we should mention the usage of historical data. Since stationary geomagnetic observations started in the 19th century, it is highly crucial and vital to use this data again in using modern methods. And several institutions of the Russian Academy of Sciences started the program of digitalization of old and archive geomagnetic data. And the Geophysical Center is deeply involved in this activity, and we hope that providing information on changes of the magnetic field for the 19th century could be used for the scientific community for better understanding of the nature of our magnetosphere and the magnetic phenomena. A small example of digitized magnetograms, one of them of 1869, as you can see, 1982. So all this data can be visually, manually, and digitally processed and analyzed. And another thing, apart of the data produced at observatories, there is also huge sets of data produced by early magnetic missions, magnetic satellite missions. For example, a couple of years ago, we performed a project of digitalization of data produced during early Soviet satellite magnetic field measurements. There were two missions in 1964, 1970. These data were obtained just as paper catalogs, and then they were digitalized, processed, and all this data was published as data sets. They are freely available using this DOI. Anyone can use it, and these data are valuable for those investigators who deal with the long-term evolution of the Earth magnetic field. And having so much data for the 60s will also improve this activity. And going to conclusion, I wanted to say that geomagnetic observations are required for assessment and mitigation of risks caused by space weather phenomena. Hence, the development of the observational network in Russia and abroad is a crucial and pivotal task. And our organization is working on this. We support existing and deploy new observatories with special focus on the Arctic region. We we actively search new possible locations for observatories in Russia and neighboring countries. And another thing is digitalization and dissemination of historical geophysical data for comprehensive retrospective analysis. Thank you very much. I have finished.
Thank you. Thank you, Dr. Krasnoporov. This is a very useful presentation, and I'm sure the Ministry of Earth Sciences, the Department of Science and Technology, DST in the Government of India, CSIR labs, all of them would be very interested to collaborate with the kind of work which is being done by the Russian experts in both the geological disasters as well as hydrometeorological disasters. And we could make that as one of the recommendations of this webinar. Now we have Dr. Manasranjan Behra of IIT Bombay, who will be discussing on the management of coastal and ocean disasters through the resilient infrastructure. Dr. Manasranjan Behra, can you, yes, thank you. Yeah, it's full screen.
Okay, good afternoon and good morning to everyone. So thank you, Professor Menon, and also my wishes to all the dignitaries and all the members present here. Thanks to the organizers for this opportunity. It is an excellent opportunity to interact with so many people from both these countries. Now let me proceed with the talk, which I am going to talk on the resilient infrastructure for the ocean and coastal disasters. So as we know that India as well as Russia, we do share a huge stretch of our coast with the ocean bodies. And in India, we have more than 7,500 kilometers of coastline, and that including a lot of islands and mainland coastlines. So we have a lot of coastal disasters which are approaching every year or multiple times in a year, which already it has been mentioned that number of cyclones are hitting. There are impacts of sea level rise and waves, there are perennial impacts. So we'll discuss a couple of them in this presentation. So what I'm going to basically talk first is the coastal vulnerability, and then I will also talk slightly on how we are basically preparing to have resistance on the coastal disasters. So coastal vulnerability, when we talk about, first of all, it comes the wave impacts due to which we may get a lot of erosions along the coast. And then we have also the effect of sea level rise, which is due to the climate change. And further, we have the cyclones, which are affecting the coast in terms of the winds as well as the storm surge that is affecting the coast. And further, we have tsunamis, sometimes due to the underwater earthquakes and possibly some other reasons, which can also come and affect the coast. So we need to also be prepared how we can handle these situations. Further, we have coastal infrastructures which is going to be facing the brunt of all these different disasters, and we need to really design or plan our infrastructure to basically resist or reduce the impact to the extent possible. Further, which I am not going to talk about, but yes, the water quality is also another factor in all these processes, which are another important factor in this whole scenarios. Now, looking at the cyclones, which we talked quite a lot, if we see this map on the left, so it shows that we have number of cyclones which are actually hitting the Indian coast, and we can see that whether it's Bay of Bengal or Arabian Sea, both the coasts are vulnerable to cyclone impacts. Bay of Bengal is more. In this scenario, we did a study and we found that there are a number of events which are occurring, and the damages are quite huge, as you can see in the photographs, starting from 99 to 2019 in this, but there are also a number of cyclones recently. They have all damaged the coast to a great extent, and still, although we have projected or forecasted our cyclone track and we predict it well before, but still we need to prepare the resilience and the protection measures for such kind of disasters. Now, in this line, we looked at the past cyclones, how they have been occurring and what are the intensities. and we looked at the power dissipative index of the cyclones, which is basically a function of the velocity, maximum wind speed that occurs during a cyclone. And if we look at that, we see that in the last decades or so, the intensities have aggravated or increased substantially, and that people are assigning to some extent to the climate change, and there is also some impact which is going to happen due to the localized features. Anyway, now we wanted to understand it further, so what we did, we tried to understand the various cyclone prediction models. Basically, these are the storm surge models. Cyclone model is the one that is going to predict the atmospheric condition, and it will predict how the cyclone is going to hit the coast. But when we are looking at the storm surge or the water that is inundating towards the land, that we are interested in. And what we did, we looked at the models that are predicting. We found that the models can capture up to a wind speed of something around 40 meters per second. But beyond that, the models are actually not representing the conditions properly. So what we did, we took number of cyclones which have different wind intensities or wind speeds, and we tried to simulate and understand how we can improve that. If you look at this slide, you can see that there are a number of models which are listed on the top 3, and they are not representing the actual condition, which is being measured by this measurement by Powell. And they have shown that the wind drag, which is going to act on the sea surface, is not linearly increasing or not being cut off at a particular point. Rather, they follow some kind of pattern which is going to increase up to certain distance, and then it is going to reduce. So what we did, we really implemented a wave boundary layer model, which is basically representing the physical process that is taking place between the ocean and atmosphere, and representing all the features. We did the modeling, and we found that this third order fit, which is going to be, which is obtained from these numerical models, and we obtained more than 1 million of data points, and that gave us an equation which is suitable for wind speed all the way up to almost 90 meters per second, which basically caters to the super cyclones, what we call in Indian context, and the cyclone or the Hurricane 5 that we also talk. So all these different wind speeds can be catered, and the modeling can be done more precisely. And this is what we have used, and we have also predicted the possible flooding scenarios for various regions. So this is a coastal region along the east coast of India, which is along Odisha coast, is a province. And if you see, if the cyclone makes landfall at a particular location called Gopalpur, which is a very prone location for the cyclone landfalls. So if it hits, how the flooding is going to take place, and that we have predicted. Also, we have simulated the conditions for future scenarios, because now the impact of climate change is being looked at, and we have looked at the moderate scenario, that is RCP 4.5. Also, we have looked at RCP 8.5, which is the extreme scenario, and we also found out how the flooding is going to be in such scenarios if these cyclone intensities are going to increase in future. And similarly, for other locations, you can see we have estimated the flooding levels. So basically, these maps are showing you the flood depth. So flood depth means it is the water depth that is going to be standing on the land. It is not from the mean sea level, it is from the respective or from each land elevation. So that means it is really important information for the local public, where they can decide whether it has to be evacuated or the location needs evacuation, or it can be managed, what is going to happen. And even it will be also useful for planning for various coastal protection measures in such scenarios. So further, we extended this study and we carried out a cyclone shelter location identification and design analysis. So this is a project which was given by one of the government of Odisha. So it's a provincial government, and they basically asked us to find out which are the cyclone shelters locations that they can go for, because the population is completely scattered. There are a number of factors we considered: the road network, the drainage network, the cyclone flood inundation, how it is going to come. In fact, we also included the tsunami flooding in this. And in addition to that, we went all the way up to the village levels. We evaluated all the cyclone shelters which are currently present and their conditions. And then we used a numerical modeling technique, mathematical tool to find out the suitable locations. In addition to this, we also considered all the guidelines of NDMA. Based on the NDMA guidelines, we decided where the cyclone shelters can be located. So finally, we gave them a list of all the cyclone shelters that are required. And in addition, we also gave them a priority list based on different vulnerability index. We also suggested which cyclone shelters can be constructed first and then next. So basically, this is going to be useful for the administrators in planning and managing the cyclone shelters, as well as in future, if they are going to construct, where they can construct first and how they can construct. So in addition to this, we also designed, based on these new parameters and new guidelines from NDMA, National Disaster Management Authority, we also gave them a new design which can cater to more number of people in a cyclone shelter with all the safety precautions. So that is something which has already been implemented and shelters have been constructed. Now further, coming to the impact of waves, which I also talked about, we looked at this as a part of a project where National Coastal Center for Research wanted us to investigate the impact of climate change on waves and further its impact on the shoreline stability. So what we did, we investigated various scenarios. So basically, as you can see here, we considered the complete domain. This is only part of the domain. We considered up to south, minus 60 south. And the complete domain we really simulated and found what will be the wave heights in 2040 and 2070. So as you can see, we have designated as near term and mid term. Obviously, someone wants to go for 2100 can also consider it as future term. So we first looked at these two scenarios. One is near term and mid term. We found there is a substantial increase in the wave heights that are going to happen along various locations along the coast. So as you can see, different points we have just listed here, and all those points, it is shown how the wave heights are increasing. In addition to wave heights, we also looked at the wave directions and wave periods. Periods I have not shown here, but wave directions, as you can see, the blue lines and red lines are showing you the near term and future term directions. And it's clearly evident that there is a slight shift in the directions. And it is very, very important because these directions are going to drive the current along the coastal regions. And these currents are going to drive the sediment flow as well as the erosion and deposition pattern. So that is why this is very important. And using this information, what we did, we calculated the net sediment transport that's going to happen. So we calculated the sediment transport rates along the coast, east coast as well as west coast. As you can see, the mid-term and near-term and mid-term scenarios are shown here, and it is clearly seen different locations how the erosion or deposition is going to take place. So wherever you see the negative values, they are basically showing the erosion. Now, using this information, we prepared vulnerability maps. Basically, this is a map which is coastal classification for erosion index. So you can see here, this is the map, left side map, which is prepared by CCC, considering the past data collected from various sources and various agencies. And based on that, we can see how the coastline is behaving. The red line shows the erosion sections, the yellow line shows accretion, whereas the blue line shows the stable portion. Similar manner, we have also prepared the maps for 2040 and 2070 scenarios. So we are now in the process of looking at in a higher detail. So we have looked at in a coarser resolution. Now we want to look at each state, possibly at every few kilometers. So in that sense, we wanted to evaluate whether the models that we are using, climate model data output, are they giving us the correct result? So in that process, what we have done, we have used a mathematical analysis using a total relative score, which is kind of performance, or by this score, we are evaluating the performance of each models. So in that process, we are using various statistical indices. And based on that, we have evaluated which model is going to perform. There are a number of models available for each region. So for Indian Ocean region, we have considered all the models that are available, and we found that there are some models which are performing better. And in addition, we also looked at, if we consider some of the top performing models, in this case, we have considered 3 top performing models, model number 27, 10, and 13, and we took one ensemble model. And from this analysis, we found that considering these 3 top performing models is giving us the best performance, and that can be possibly used for this further analysis. So similarly, we also did for the codex data, which is basically available for the South Asian domain. And considering both of this analysis, finally we arrived at a conclusion that there is this set of 30 or 3 GCMs what we have found is going to give us a better result. And same analysis we also carried out for the Indian Ocean region, and that we will be using. So now this is a better wind field which we will be using for the similar analysis which we have done, and we will find out the very fine resolution information in terms of wave heights, wave directions, and further the sediment dynamics. So this is another aspect which we have worked on. Further taking you forward to the coastal structure side, we have also worked on extreme wave impact forces on offshore and coastal decks. So I will focus on coastal decks more. So if we look at the damage can happen to the structures when there is a strong wave which is going to hit during a cyclone or storm. And in such scenarios, we have to really estimate what will be the wave loads. So current codal provisions which are available around the globe are not considering this extreme wave impact. So what we did a thorough analysis, and we carried out the extreme wave forces. We found out the extreme wave forces based on the numerical modeling and some of the experimental literature that we have validated. And finally, we found that this is how the force is going to behave. And from these forces, we have formulated the coefficients which can be directly used by the field engineers, and they can compute. So the advantage in this thing is we have considered the wave height, which is h, and the s, which is the air gap or the gap between the mean surface and the deck. So whenever somebody is talking about the sea level rise, obviously it is going to change the air gap or the freeboard between the structure and the sea. So the existing structures, we can actually further evaluate how the force is going to vary over a climate change scenario, considering the future wave heights and sea level rise. In addition, the design of structures for the future can also be taken care by considering these parameters. So that is what we have done for different waves. This is what is shown for non-breaking solitary wave, which is a kind of impact of tsunami. So further, we have considered non-breaking focused wave, which is mainly going to happen during storm surges or some kind of rock waves or freak waves which are going to come. And also we have considered the breaking wave forces. So sometimes the wave is going to break right on the structure. So in that case, the maximum force is going to come. And that also we have evaluated, and we have given the formulation. And these are already digitized. We have prepared a GUI portal where one can simply go there and input all the values and get the outputs. So that is something from this work. And further, just to again add on what we have done for the coastal protections, there are various coastal protection structures in terms of sea walls people implement, or sometimes on top of the sea walls they put crown walls. So the purpose is to reduce the wave energy that is going to come, as well as the wave inundation in the inland portion. So in this case, what we did, we carried out this work to ensure that there is no inundation, which was required for a nuclear power plant. And we did the study. We took all the various profiles that are available along the globe. And you can see here different profiles that are available, including the vertical profile. We implemented all these things in the numerical model. As you can see here, this is basically a sloping profile. On top of that, we have the crown wall. And that we implemented in the model. And with the modeling study, we could find that there are different performances, but none of these profiles are giving us zero inundation. So there is overtopping. So then we actually worked on various profiles. We changed different dimensions, as well as we looked at various scientific analysis, how the wave is turning back and which point of the profile can be effective in reflecting the wave back into the ocean. So finally, we ended up getting this profile, which is basically a 2 curvature profile. And with that profile, we just implemented on the seawall as a crown wall. When we implemented this and studied, we found that this 2 profile which we developed is going to completely reduce the inundation, because you can see in this picture, the wave, although it is coming, the surge is so much, the water is gushing in, it is reflecting, it's reflected back by this curved profile. So now this profile is found to be more efficient and which has been suggested for implementation. So further, the coastal protection can also be done in a bioshield ways, that is hard protection. There are soft measures of protection which also being looked at. So what we did, we looked at various damages that has happened along the coast, and we saw that the places where there are vegetations, we have a lot of... Yes, sir.
Another 3 minutes, please.
I will finish it in another 2 minutes, sir. This location, we can see that there are damages, but there are no protection. But wherever there are protections, we could see that a lot of houses or infrastructure have been saved. So what we did, we wanted to remodel that. But the problem was, we didn't find any suitable modeling tool or any method where we can simulate the floating debris. Because whenever there is some kind of flow that is going to happen, it will also carry the debris that is lying around. So we did a modeling study which is present. We also considered multiple debris, and then there is a structure, typical structure, which we have considered to calculate the kind of force that's going to come on that. We also carried out experimental studies just to validate first our model, and then took the model for further implementation. You can see that we have carried out this work and then implemented the vegetation. And finally, we found that with vegetation, with different debris types and debris mass and other parameters also we varied, and how the force is going to vary. And that suggested us where this vegetation can be located, where the structure can be located from this coast, which can be much safer, and there can be reduced impact on the structures. So these are various different works, although I have other things to talk, but I will not be able to talk. So this is the group which worked. I would first thank them, who are the people who have done the work. And thanks everyone for giving me the opportunity and listening. Thank you so much.
Thank you very much, Dr. Berra. Very useful presentation, and I'm sure that there will be more questions coming up in the discussions. So we now have the last presentation in this session from Dr. Vladimir Kusabakov and also Dr. Anastasia Nekrasova. They will be speaking on the non-deterministic seismic hazard and risk assessment based on the unified scaling law for earthquakes. Request them to initiate the presentation, please. Thank you.
Hello, everyone. Can you hear me?
Yes, sir. Yes, sir. We can see you, sir.
Okay, great. So thank you, the organizers, for this wonderful gathering of interested people. I'll be talking about non-deterministic seismic hazard and risk assessment based on the United Scaling Law for Earthquakes. This year, our institute, and not only our institute, are celebrating the centennial of Vladimir Isakovich Kelly's work. We managed with a seismologist and volcanologist from Italy and disaster management manager from Israel to publish this book. The title is Earthquakes and Sustainable Infrastructure, and subtitle is Non-Deterministic Approach Guarantees Prevention Rather than Cure. Many authors who participated in writing this book keep being inspired by the innovative research by Vladimir Isakovich Kelly's work, and in particular by his ability to find simplicity in complexity, active style, scientific intuition, exceptional warmth of soul and humanity. here's his words. My main trouble, he says, is feeling of responsibility. Borak had founded a unique institute in Moscow where pure mathematicians work jointly with physicists and geologists in collaboration with the world-famous experts from mathematics, physics, economics, social sciences, law enforcement, environmental protection, disaster management, and the government. You can see here in the middle of—
I'm sorry, Vladimir Grigorievich, we don't see your presentation.
Oh.
Am I right?
Yes.
Could you please share it?
Share the screen.
I was, okay.
Try it once again, please.
Can you see it now?
Yes.
Oh, great. So maybe I should just come back for,
You're on the G-sharp slide.
Yes, but I wish to start with, probably I have to just to go back. Okay. Anyway, so let's continue. So I just wanted to show the panel with people whom Borak met during his career, including the Pope Johann Paul II and the director of International Center for Theoretical Physics, Professor Shrotriya. So I start with this probabilistic product, which is the global seismic assessment hazard map of big ground acceleration. And it was launched the program was launched in 1992 by International Lithosphere Program with support of respected international organizations, including the United Nations International Decade for Natural Disaster Reduction. The project terminated in 1999. The declared legacy of Global Seismic Hazard Assessment Program is to establish a common framework to evaluate the seismic hazard over geographical large scales. Its main product, the Global Seismic Hazard Map, was meant to be a milestone, unique at that time, and to serve as a main probabilistic seismic hazard assessment reference worldwide. Today, for most of the Earth's seismically active regions, the G-sharp hazard map is proven outdated, very often wrong, as it has been shown on many occasions. So, right after the Haiti earthquakes in 2010, we made a comprehensive analysis and found that about 50% of about 1,200 strong magnitude 6 earthquakes, the map was surprised by unacceptable difference in the expected and real ground shaking. Moreover, each of about 60 magnitude 6.5 or larger earthquakes in a decade past publication of the GSHAP seismic hazard map. The deviation was about ground shaking was about 2 units of macroseismic intensity. Note that 2 units bring strong shaking with light damage to severe shaking and moderate heavy damage to the buildings and the infrastructure. So, moreover, after the Tohoku disaster, in Japan, we found that all top 12 deadly earthquakes were also surprised for the map. And again, the deviation of the observed and expected ground shaking intensity was 2 units. Moreover, this list is continued to expand. Here is another example when the magnitude 7.5 earthquakes happened in north of Palu in Indonesia, and it brought about 2,100 people, and it was the deadliest earthquake in 1980. Of course, these numbers are nothing compared to the numbers we get each day from the COVID-19 pandemic. Nevertheless, as shown by Victor earlier, this is a significant part of disasters on the global scale. Thus, some 20 years after its launch in 1992, it has been possible to prove that GSHAP final product is totally unreliable. In fact, several are the evidences of how useless and misleading can be most of its published results. PSHA is unreliable as witnessed by the more than 700,000 lives lost between 2000 and 2011. Of course, it is not comparable with even just a single day in a country of losses in a single country, or say 5 million, more than 5 million fatalities over the year of COVID pandemic. Regretfully, the next generation of PSHA, with the general philosophy of GSHAP plus some cosmetics, is at the base of the ongoing international project Global Earthquake Model, which was launched some decade ago. Evidently, GEM is on the wrong track if it continues to base seismic risk estimates on a refined standard method to assess seismic hazard. How long it will be necessary to wait to prove that GEM products are as wrong as those of GSHAP? Should science community wait for a decade to find GEM is as wrong as GSHAP? We don't think so. Neo-deterministic seismic hazard assessment dates back to the turn of millennium, providing an alternative to probabilistic seismic hazard approach. It represents the innovative scenario and physics-based multidisciplinary approach for the evaluation of seismic hazard, proven reliable by 20 years of experiments in many countries worldwide. In 30 chapters of the book, you can find evidence from many countries, including India, Pakistan, Burma, Indonesia, and countries of Europe and the United States. Evidently, the results of NDCH-SH NDMA applications outscored the widespread PSHA results by taking advantage of a synergy between to date available pattern recognition for prone areas proved by post-publication events in the areas considered, by intermediate term earthquake prediction of different spatial accuracy proved in the global and regional test, which now is about more than approaching 3 decades. Scenario-based seismic hazard analysis, which takes advantage of digital revolution we experience this nowadays. Maximum credible seismic input method based on historical, paleo, and other evidence of ground shaking. Unified scaling law for earthquakes that accounts for fractal distribution of seismic sources, and I'll be talking about it a bit later. And the geodetic data analysis of GPS, GSSN, and other reliable determinations. Oops. The synergy of PREPA, USLE, ETAP, GDA, and CSI-SSHA implies to a pretty wide spectrum of geophysical observation and allows us to deliver user-specific products which are tested to be reliable, realistic, and useful evaluation and mapping of apparently type-dependent seismic hazards and associated risks. Of course, although each member of the synergy is relevant in seismic hazard assessment, it is the last two, which is the maximum credible seismic input and seismic scenario hazard analysis that provides a quantitative output of seismic input for the structural engineer community at the final stage of NDSHA. So here is an example that was obtained by an international team of authors, which show that specifically the number of unexpected unacceptable errors when big ground acceleration on a map at the epicenter of real earthquake is less by factor 2 or greater than attributed to this earthquake is several times larger for G-sharp map than for the one based on unified scaling law for earthquakes. In particular, it is factor of 11.4 for Indian subcontinent, and it's about 1.7 in the Lake of Baikal, and it's about 2.5 for Central China region, respectively. So what is this unified scaling law for earthquakes? In fact, this is a generalization of fundamental Gutenberg-Richter law, and it simply adds the scaling, so the third term, scaling, C logarithm of the length of linear dimension of earthquake-prone area, which is very, very important, as would be shown in the next slide. So here is just the reference to the most recent reviews, including a chapter in the Encyclopedia of Solid Earth Geophysics, edited by Harsh Gupta. So one of the very first practical conclusions drawn from USLE is that we can get underestimation or overestimation of the actual rate of earthquakes. For example, in case of Lake Baikal region with an area of about 1.5 million square kilometers and parameter C equal to 1.25, not 2, the inclusion of seismic areas leads to underestimation of widespread seismic activity measure A10 by a factor of 15, and to its overestimation by a factor greater than 2 when a characteristic of seismic activity over an area of 1,000 square kilometers, which A10 is, when it's computed for a grid cell of 10 by 10 kilometers. So here you can see similar estimations for megacities, and you can see that the factor of 6, underestimation of 6, is for the city of Los Angeles in California. It's 6.4, even larger, for San Francisco. It's 4.6 for Tokyo, 8 for Petropavlovsk-Kamchatsky, and also it is true for mega cities of India. Here you can see how the hazard depends on vulnerability, and here we in oversimplified convolution of seismic hazard map with the observed population density distribution in India. So you can see that depending on vulnerability, which in the 4 model cases is proportional to different power of population density, you can see how the risk collapses to mega cities and their agglomerations. As one may expect, the 13 mega cities and their agglomeration are at the top of the model risk distributions. I should say that here the arbitrary color-coded scale is logarithmic and covers the top 7 decimal orders of risk values. So you can say that the risk number 4 is actually important to consider only in the near vicinity of Himalayas and in the area where the huge earthquake happened in 2008. So conclusions. The USLE analysis is of fundamental importance and should be accounted for in practice of emerging realistic seismic hazard assessment and evaluation of associated primary and secondary risk. The NDSHA estimations addressing realistic and practical kinds of seismic risk should be interpreted by experts in earthquake engineering, social sciences, economics, bringing together their experience and skills. The widespread general level of underestimation of seismic effect rates at exposures on either GSHAP or GEM maps is too large for being ignored in seismic risk and earthquake loss evaluations necessary for knowledgeable disaster prevention and mitigation of losses. The USLE suggests a possibility to prove exposure of different objects at risk by relocating them in a safer place, as was done in Kazakhstan with the capital moved from Almaty to to a safer place, vulnerability of an object could be improved by a knowledgeable choice of appropriate hazard reduction measures, either in advance their design or in case of earthquake prediction alert, after simulating a comprehensive ensemble of earthquake scenarios of realistically distributed sizes, mechanisms, and locations. So the final conclusion. Nowadays, science can disclose natural hazards, assess risks, and deliver state-of-the-art knowledge of looming disaster in advanced catastrophes, along with useful recommendations on the level of risk for decision-making in regard to engineering design, insurance, and emergency management. So you can see a knot that ties together hazard, location, time, exposure, and vulnerability all around risk. And this risk could be risk of disaster after an earthquake, after tsunami, after some other natural or say human-made events. Thank you very much.
Thank you, Dr. Kosabokov. Actually, very useful and very interesting presentation. We've listened to the Indian experts and the Russian experts, and there are several golden nuggets. I'm sure that in the discussion, many of these things would actually become exploratory work based on the kind of guidance which all of you have provided. And we can now open it up for discussion, Dr. Shishir, and go to the panel discussion.
Yes, sir.
Yeah, so I think we can actually have, the discussion by the distinguished experts, both from the Russian side and the Indian side. If there are any questions to the distinguished panel or any of the other distinguished delegates would like to respond to some of the presentations which are made, we can open it up for a discussion.
So I have one question to the Russian side, sir.
Ji.
So I just wanted to find out with respect to one of the presentation which we also made from our side, what are the measures taken in Russia for flood control and rainwater harvesting, especially in big cities like Moscow and all? If somebody can throw some light.
Yeah, any of the experts from the Russian Academy of Sciences or any of the distinguished delegates would like to respond to that question?
It's a lot of space. I have to.
Can you hear me, colleagues?
Yes, please.
Hello.
Yes, Dr. Moderator.
Oh, okay. Yes, thank you. I come from Institute of Water Problems of Russian Academy of Sciences. So by education and background, I'm a hydrologist, but I will be talking in a few moments. I will have a presentation on flood control in Russia. So maybe some of the questions that Dr. Shishir announced might be covered in my presentation. But for now, the question regarding water harvesting for Moscow, as you were asking, is this right, Dr. Shrotriya?
Yes, and how to, what are the measures for flood control?
Well,
so one of our professor from IIT Bombay mentioned, the interventions which they have designed.
Yes,
so
yes.
We would like to hear from you something which you can enlighten us.
Okay, may I then suggest that those questions I will answer in my talk just a few moments later, okay? Because I will be specifically covering the
flood control and flood forecasting issues in Russia, but not particularly in Moscow. Moscow is very resilient in terms of flooding due to, first of all, the specificity of natural water regime, first of all, and secondly, due to very profound water supply structure on the Moscow River. So this is the flood from rivers. So riverine flood is not an issue, but one of the issues that also Dr. Gupta was talking about, the rainfall flood is very prominent in Moscow. So maybe I will answer some questions in my talk.
So we would like to hear some scientific interventions and solutions.
Okay, Dr. Shrotriya, I have one question.
Yes, sir. Yes, sir.
Chairman Saab, I have one question to Dr. Victor. Victor, my question is that.
Yes, I'm here.
You talked about reservoir triggered seismicity. So if we have a reservoir in Himalaya, do you think this will also lead to a lot of seismicity, or it will trigger some earthquakes? Just like what we have into the plain, like Koina?
Yes, I know about your research in the Koina area. And we discussed with Professor Harsh Gupta the possibility of application of our method, not the real application, but for verification of this method of suppression of seismic activity at Koina, because they, according to their statement, may predict some earthquake which occur at this area. And they propose to install this facility, I mean the MHD generator, there for suppression.
Dr. Victor, I'm asking a separate question. I'm asking if we have a reservoir into the plain like Koina, and if we have a reservoir in Himalaya, thrust fold belt, just like Terry, do you envisage that lot of activity, seismic activity will be generated by the reservoir impounded into the higher Himalaya, or only it will impound into the plain area? Am I clear? Question is different.
Yes, sorry, just now I understand. So you compare the impact of Himalaya on the stresses in the Earth's crust, and you try to compare it with the Koina reservoir. But it is different because at Koina, you know that there are some variation, seasonal variation of water in the reservoir. When you are talking about the Himalaya and variation of stress, what do you mean? The variation of stress due to some
dam or reservoir?
It requires some analysis of this phenomenon, because we need to know the variation of water in a reservoir at Himalaya, and after that we should compare the seismicity and try to correlation between the variation of water level with local seismicity. So just now I don't know some results of this analysis.
Okay. And another thing you said, by sending electrical energy into the highly stressed zone for earthquake, you can release that energy in the form of earthquake if you just send electrical current into that stressed region. So do you have any control of the earthquakes, that low magnitude, medium magnitude, or high magnitude? If you want to induce earthquake, you by sending electrical current, they may lead to big earthquake also.
So I showed the slide there in my presentation. When we found that after the starting of this experiment, when we injected the current into the Earth's crust at one point, one emitting dipole, so in the area of 100 kilometers to 100 kilometers, so in this area, this is a test site near Bishkek city in Kyrgyzstan, we found that within 40 years, there is a deficit of strong earthquakes. So we in this fact we consider as a possible result of electromagnetic processing of the Earth's crust in this local area. At first, we demonstrated the sharp increase of local seismicity in the kind of weak earthquakes. But now we are searching another type of seismic events, slow sleep events after the injection of electrical current, because it may be possible as well. But it is just under consideration, and I cannot to report some results of this. But one thing which was found in this area during the very long electromagnetic experiments, within 40 years, we observe the decrease of seismic activity. I mean the moderate and strong earthquake there due to electrical processing of the Earth's crust.
So this can be used as a mitigation tool of releasing lot of accumulated stress in the subsurface.
Yes, we consider as a background for development of new technology to suppress. For example, so maybe we cannot prevent totally the catastrophic event, but we may decrease the magnitude of anticipated earthquake to the safe level, safe for surrounding infrastructure.
Yeah, that's a good proposal.
Here with a remark. You know, once upon a time in Leningrad, the Nobel Prize winner, academic Sakharov, was suggesting American seismologists to make an experiment with blowing up an atomic bomb on San Andreas, so that to release the stresses that are accumulated there. Of course, you know the answer. They say, please do it in any other place. Nevertheless, you know, the blocks and faults of the lithosphere are so complicated, and their mosaic cannot predict with certainty enough for, say, decisions. What will happen when you release one point in this system? So you know, for example, that before the Tohoku earthquake, the ground moving, so the direction of ground movement of the Sindai region was almost zero. After Tohoku, we have a continuing displacement towards east with enormous speed, a speed which is considered dangerous in this low earthquake or silent earthquake, which they observed for decades to the south of Tokyo. So, you know, this is really very, very important to understand the dynamics of the system. And it is very, very difficult.
Yes, I understand. But today we don't say about some technological approaches, but we were considering only interaction of electromagnetic fields with the rocks under critical stress strain state and possible application for mitigation of earthquake hazard.
Chairman, sir, can I ask one more question?
Yes, please.
Yeah. You see that in Victor, I'm asking you, you have shown one 7.5 magnitude Haichang earthquake in 1975. And then in the nearby place, almost same place, 7.6 magnitude earthquake, Tangshan in 1976. We understand whenever there is a magnitude of 7.67, most of the energy get released, and that similar magnitude earthquake may take place after longer time. It needs time for this stress to be accumulated. How did it happen there? Consecutive year. 7.5 magnitude in 1975 and 7.6 in 1976 in the Haicheng and Tangshan.
Yeah. I provided these two cases only for demonstration that the earthquake prediction, exact earthquake prediction based on precursors, it is not so easy task, and it is very difficult problem. So for the first case, they observed many precursors, and based on these precursors, they announced the earthquake alarm. But in the second case, I'm sorry, Victor, please. Okay. And in the second case, this earthquake occurred practically without any precursor, like the Parkfield earthquake series in 2004, where the all known methods were concentrated for observation, for monitoring of earthquake precursors.
That means huge amount of energy was stored there. In 75, some of them released, and then remaining it released in next year.
Maybe yes.
Okay, thank you very much.
Yeah, we have Dr. Perumal wanting to raise a question or comment.
Thank you, Professor Menon. Good afternoon and good evening to all of you. I have some small clarification with Roman Crosspro, Dr. Roman actually. The question is that, or rather the clarification is that, some places we have a lot of lightning followed with thunderstorms in particular states, especially India, we can take some Chhattisgarh. And if you go to globally in America, we have in Cincinnati. So what is this basically the understanding so far? Because you have been studying the geomagnetic variations and their space weather. So I would like to know on that aspects.
So speaking about thunderstorms is a bit different thing. So surely the lightning causes an EMP effect, which is detected by special services, which is called in such a way, so thunderstorm or lightning monitoring system, and this is recorded. The magnetic field that we measure on our observatories is the natural, which is induced by, as I said, the inner field and the outer field caused by solar terrestrial interaction. So the impact of coronal mass injection, of solar flares and particles which interfere with the magnetosphere. The thing that you are talking about is the source of it is meteorological sources. So this is interaction in the atmosphere. And so the thing that we deal with is a bit different.
Thank you. Dr. Harikishan.
Okay, thank you. And can I ask, okay, no problem. Is
Yes,
there
sir.
any Roman, is there any chances of having the variability during the or after the great earthquake, whenever you have such kind of geomagnetic storm? Is there any variability did you see on your data set?
No, generally we do not make any try to connect the earthquakes with magnetic phenomena. As I know that during the earthquakes in certain regions, there are some disturbances in ionosphere, and as I understand, it might be detected.
Yeah.
But you see, you have to have an observatory located in the vicinity of the earthquake zone, because the magnetic observatory can't detect a thing which is located several hundreds or thousand kilometers off it. So you need a dense network.
Thank you. Thank you.
I think Dr. Krasnoparov, in India, we have the GNSS stations and also the GPS stations through a wide network, and it will be possible to really see some of the geomagnetic effects, on like solar flares, for instance. The way in which ionosphere, you mentioned that there could be ionosondes which can actually do the monitoring of the way in which electrons, ions, have deviations. So the kind of deviations which are actually taking place could be monitored, and that could also be suggestive. But one issue is of a series of swarms of earthquakes happening, series of tremors happening. Is there some experience in Russia?
So a series of what? Sorry.
Series of earthquakes, tremors happening in clusters within a geographic area.
Surely there are some geographical clusters where earthquakes tend to occur. So we have seismically hazardous zone in the Far East, in the Altai region, Altai-Baikal, then in the Caucasus region. And unfortunately, in speaking about any connections with geomagnetic phenomena, we don't have magnetic observatories everywhere, but several of them work in the Far East. One of them is located in Kamchatka. But speaking about ionozones, this is a slightly different thing. There is the meteorological state meteorological organization, which is called Roshydromet. This organization is in charge of this phenomena. So they have a network of meteorological stations where they have ionozones, and they detect all the activity in the ionosphere, and they're in charge of magnetic stations which measure variations. Generally, the Russian Academy of Sciences is in charge of observations of that kind that I mentioned. So observations of the full magnetic vector.
Thank you. Dr. Harikishan.
May I add about, say, earthquake swarms? So I'm absolutely sure that a golden opportunity to get another short-term successful prediction was the case of L'Aquila, April 6, 2009 disaster. So the scientists from the L'Aquila 7 were the first authors of probabilistic assessment that was considering L'Aquila as the most dangerous city where a strong earthquake is imminent. Another one was the first author of report concluding that Abruzzi is the region of the most vulnerable infrastructure in the whole Italy. Nevertheless, on the 1st of March 2009, they were to agree with civil defense representative and make absolutely inadequate scientific statement that small earthquake release energy which is accumulated before the strong one, before the catastrophe. So you know the result, you know that there was a so-called L'Aquila trial, you know that they were accused of misleading information in the first stage of Italian judgment, that were finally 6 of them were found not guilty. So only the one representative from the civil defense was found guilty of this inadequacy. Thank you. Excuse me.
Sorry, we'll have to rush now. We have 4 people with their hands raised. So Dr. Harikishan.
Yeah, a very good afternoon to everybody. It is not a question. I just want to add, there are locations where multiple hazards, localities are prone to multiple hazards like northeastern India and Himalayan regions where earthquakes and also high wind conditions. So there is a need for risk-consistent probabilistic approaches so that we contain the risk to a given building or a structure in those localities. And also there are cases where multiple hazards like a cyclone associated with storm surge or earthquake associated with fire accidents and other things also. These are very challenging things, even though single hazard itself is a very challenging thing to address. And the coexisting or same location prone to lifetime of the structure, multiple hazards is still a more challenging job. I just want to add these points.
Thank you. I'm sure Professor Ravi Sinha's resilience framework would be looking at multi-hazard resilience.
Yes.
If needed, because you have cascading disasters,
Yes.
Earthquake triggering landslides, in which we have seen, especially in areas where you have glacial lakes. And this is also related to what Dr. Nobikov was mentioning. When you have a release of the pressure, the stress, by either electromagnetic interventions, you also have very similar situation analogous in the case of glacial lakes, where you can actually puncture the glacial lakes and gradually release the water to prevent a sudden, outburst of a glacial lake outburst flood. GLOF, can be prevented or reduced. Impact can be reduced through puncturing the glacial lake gradually, and that is done in Sikkim and also done in Bhutan, very successfully. So we have Dr. Sunanda wanting to raise a question or comment.
So may I request the further questions, if they can be put on chat, if they are one-to-one, and then the speakers would like to reply them on chat, because we are running about 23 minutes late. So this may be the last question, and then thereafter any more question could be on the chat, sir, with your permission.
Thank you very much. Yes, Dr. Sunanda.
Yeah, this is just a very small question, sir, to Dr. Manas Ranjan Behra. I've been to Odisha and visited this multi-purpose cyclone shelters. So my question is, like, they're very near to the coast. Are they safe enough to to take evacuations for the tsunami? After your analysis, what was your conclusion for that? That's all.
Yes, you actually are correct. there are some cyclone shelters which were constructed immediately after the 99 super cyclones. And there was no time to even think of a scientific study or anything. So a lot of funding and a lot of CSR fundings were also there. So they were constructed. But now something like 1.5 kilometers from the coast, we are specifying it as a no zone. So that means no cyclone shelter is going to be constructed within 1.5 kilometers from the coastline. So that when there is a evacuation, the impact is going to be reduced. So the flooding, storms as flooding will be also very, very less. So that is what already we have recommended. Yes, you are correct. We have observed that and we have recommended remedies for that.
Thank you, sir.
Thank you so much for the question.
Dr. Shishir, then can we conclude the session?
Yes, Dr. N. Kumar, if you have something very important, and Mr. Roy, can the question be asked on the chat? Will it be appropriate?
No problem. I can always ask on the chat.
Yeah. And
just actually, my question was based on what Professor Menon said, that, is there use of drones and IoTs in these measurement of the geomagnetics and the ionosomes and electromagnetic forces to measure them in real time through use of IoT and drones? Is that now accepted practice for landslide areas and potential earthquake areas, or is it the old-fashioned methods are still prevalent in the earth stations or the meteorological units?
Whom do you wish to ask this question specifically?
Anyone, actually. Anyone who has an answer who can give an answer. I'm not specific to any panelist.
I think drones and IoT approaches are actually being used now in many disasters, including wildfires. We have seen the use of drones, but mainly for immediate reconnaissance, where aircrafts cannot actually reach to identify people who are marooned in floods and also in cyclones and in earthquakes. People in collapsed structures. The way to identify, there are many technologies which are being used, so including robos. In fact, Emercom showed the use of robos even in putting out fires. That was the first time I saw a robo trying to put up fire by identifying the source of the fire from the short circuit. This is 20 years ago. So I think there are many possibilities. We have seen a lot of golden nuggets from many suggestions which came. So, Mr. Kumar, would you like to ask any question or comment?
Professor Menon, can you just add one point on that? That the use of mobile phones, the sensors in the mobile phones as earthquake measurement, earthquake recording and measurement instruments is also being looked at very seriously by many, many different groups, including those within Google, those within Apple, and so on. Because these accelerometers which are built into the mobile phones are very sensitive. The question is that they are not in a standard framework, like they're not placed on a firm ground or something. So how can that data be used to get a quicker assessment of the earthquake before the mobile system goes out of order? That is something which is being looked at very seriously by a number of technology groups.
Right.
Right. And in areas where there is no internet access or even possibility for doing a certain crowdsourced data feeds, there is also now cloud computing and fog computing, where wherever the particular device actually reaches a particular internet zone where Wi-Fi access is there, it automatically uploads to a server, and then you will be able to access that. So that information is also available. So these are all possibilities which we need to explore from crowd computing and crowdsourced information feedbacks. So, Mr. Kumar, would you like to say something?
Thanks. Can I have a quick question? Although I put it in chat box. But this is related to that ionospheric magnetic anomaly Dr. Roman Kraspo has obtained. So my quick question is that how much is the magnitude threshold, minimum magnitude threshold for the anomaly, and what is the maximum distance? And then related to that, is there anomaly is observed in other parameter also?
I'm not sure. What anomaly are you talking about?
Ionospheric magnetic anomaly.
So generally the magnetic storms which are detected by observatories are several tens or hundreds of nanoteslas. If the storm is extremely strong, it may be more. So the severeness of a magnetic storm or disturbance, if you wish, they are divided into several groups according to indices. There are certain indices of geomagnetic activity, K index and some others. Another is DST, the disturbed index, the ring current, the index of ring current during the magnetic storm. So a significant storm starts from K index starts from 0 to 9, and a severe storm is, I suppose, 7 and higher. So not long ago we had maybe 2 weeks ago a storm of the rate 7, if I'm not mistaken. So it was severe, and the index of the ring current was about 200 nanoteslas.
Thank you.
Thank you very much. We have really overshot the time. So I would like to thank all the distinguished speakers, and also to the Russian Academy of Sciences, International Cooperation, and the Indian Embassy in Moscow, especially Dr. Shishir Shrotriya. Thank you very much. And all the distinguished speakers and all the delegates. Thank you.
Thank you. Thank you very much, sir, for your very elaborate and very nice discussions which you took forward during the session 1. We now move on to session 2, which is integration of multiple weather sensors, satellite imagery, and improving disaster forecasts. So this is in line with the discussions which we are already having. And may I request Ms. Inna to kindly introduce the chairperson and the moderator for the next session, Dr. Viktor Novikov.
So we move to the second session, and there is no need to introduce Dr. Viktor Novikov, because he has already made his report in the first session, and he will make one more at the second session. So I just want to add that Dr. Viktor Novikov is the head of the Laboratory for Pulse Energy and Geophysics at the Joint Institute for High Temperatures in Moscow. Please, Viktor Novikov, take this session in your hands.
Okay, thank you. The first presentation will be given by Dr. Shrotriya. He is currently the head and outstanding scientist of the Council of Scientific and Industrial Research for the Paradigm Institute in Bangalore. Dr. Jej obtained her PhD and Master's in Engineering from the Indian Institute of Science in Bangalore. For past 3 decades, she is in CSIR pursuing research and development and management roles. She is a recipient of National Mineral Geoscience Award for her contribution in the field of disaster management. She also received Sir C.V. Raman Young Scientist Award for exceptional contribution to Earth science. Her major research area is GNSS-based multidisciplinary research, and has handled several multi-institutional network projects and served on several national and international committees. So I just to point that Dr. Shrotriya pioneered GPS, global positioning system based geoscience research in India since 1994, and is an acknowledged researcher in this field. Please, Dr. Jej.
Yeah. Can everyone see and hear me?
Yes.
Yes.
So, good evening to everyone. because for us it's almost evening 4:30. So I will try to share I'm Sridevi Jade. I'll try to share my screen and PPT and then I'll start talking. Okay. Host disabled participant screen sharing, it is saying. So you have to enable.
Inna, can you help? Can you ask the IT team to enable?
Just a moment. Try now.
Yeah, now it's come. Yeah.
Thank you.
You can see my screen.
Yes. Could you please do it full screen?
Yeah, I'll do it 1 second. So I just make it slideshow. Is it fine?
Yes, perfect.
Okay. So I'm going to talk on natural hazards and real-time GNSS. Just like in my introduction, he told me I am in this field since 1994. That is when actually GPS became fully operational for civilian use. Before that, it was only being used for military use. So actually in the first slide, this is the IGS station, that is the global GNSS station, which we started in 1994 when I was doing my doctorate at IISc Bangalore. So that is this station, and this station which you see is our high altitude station at 4,600 meters at Hanle, where we have an astronomical observatory, and this has been running since 1996. So the rest all, so I am from CSIR, Council of Scientific and Industrial Research Institute, 4th Paradigm Institute it's called. Basically, I just thought I'll just give a slide on 4th Paradigm Institute because people even have difficulty in spelling it. So it's nothing but we are working in the 4th paradigm of science, our institute. As you all know, first paradigm is experimental science. Second is theoretical. That is where and then third is computational. Fourth is data intensive scientific discovery. We also have one of the best supercomputing facilities hosted for the whole of CSIR. We are one institute of CSIR for the whole, but we host the supercomputing facility for whole of CSIR. So, and then now going to my topic. This is what I'm going to talk about, real-time GNSS network, observation network. That is where we measure GPS signals from the satellite. So this you can have it in post-processing on real-time mode. So I'm going to talk about both the modes, though our real-time network is not fully operational, but I just thought we can give the futuristic view. If we have that real-time GNSS network, what all wonders we can do. Whereas, in countries like Japan, they have around 2,000 plus real-time GNSS observatories. But in India, we have few. We have around 10, our institute. But that's really minuscule compared to this thing. So basically, this my flowchart, though. See, I'm not very good at making PowerPoints, so I just made PowerPoints to convey the technical content. So they're not very jazzy. So, so this is the real-time GNSS network. Basically, what all it can give. So it gives you GPS signals, as you all know, because everyone has in their mobiles, which basically gives you your position over a period of time. So that when you use for scientific purposes and then you combine it, so it gives you the surface deformation, that is your crustal velocity. When you combine with geology, tectonic seismology and all that, then you can come out with deformation models using inverse modeling. I'll just talk about it later. The other part of GPS is where you get ionospheric and tropospheric delays, which actually you can extract water vapor and the total electron content in the ionosphere. So this water vapor can be correlated with the rainfall, and it can be used to forecast extreme rainfall and cloudbursts. And the total electron content, it was discussed in the morning, this can be used as a precursor studies for earthquake. Whereas the stress and strain, seismic and all can be used also as a for earthquake studies. Then we also have, along with GNSS network, now broadband seismic network, which is co-located. They are in one place. So we have also done integration of GPS and broadband data. So that gives you ground motion modeling, crustal mantle structure. That separately goes into your earthquake hazard, but it also goes into this. And we can use it in our stress strain map and do composite analysis of geodetic, seismic strain and all that, and deformation models also. And again, it converges in earthquake hazard. And then we can also use the GPS data along with geology, tectonics for landslide studies, which we have done in our institute. It can also be used for glacial and volcano studies. We did initiate this program, but we haven't done much as of now in that. But we did initiate the glacial studies with GP Pant Himalayan Institute and volcano studies in Andamans. So, and all that converges into natural hazard. So what I thought I would talk, give you a glimpse of what we are doing and what can be done, what we are doing in our institute and what can be done using this GNSS network. So that's the idea of my talk. Then going to the next slide, I'll first talk about seismic hazard and GNSS. Then I will go to landslide hazard and GNSS. Then I will talk about GNSS remote sensing. One slide on water vapor and one slide on total electron content. So that is the whole idea. And I would also talk a bit about our Indo-Russian collaboration from our institute. And one of my colleagues will talk about it over 2 slides. So that's the outline of my talk. So now coming to seismic hazard and GNSS, like you can see, this is our observation network. All these triangles are continuous. That is, these triangles which you can see are continuous, that is 365 days a year they run. And all the small circles are episodic measurements, that is we measure them yearly once. And we have been having this network starting from 1994. In 1994, we put it in Bangalore. And then in 1996, we put it in Almora in Himalayas, then Leh in Ladakh Himalayas. And then slowly we started in 2000 in the Northeast Himalayas. So these yellow purple vectors you are seeing, actually, I average the velocities and put one vector. But your GPS data gives you velocities at each of the stations. But here, if I put all that, it looks very cluttered. So I just put approximately to show how our Indian plate moves with our, these are the vectors which we have computed with our data, but these are our average velocity vectors. And the blue dots are the seismic activity, and these are the focal mechanism solutions. So you can see how actively, and this green one is the co-seismic vector of 2004 earthquake, Sumatra earthquake. So it was almost around 6 meters, I think, the co-seismic vector is. See, what GPS signals can do is, if there is an earthquake and you have measurements before the earthquake and after the earthquake, then you get very precise co-seismic slip on the surface, which actually you can model using inverse modeling to derive the map the rupture surface, which we have also done for Sumatra earthquake and Bhuj earthquake. Both the earthquakes we have done. And during interseismic movement, interseismic phase, when you get interseismic velocities. These are also again surface deformation. So using these velocities, we do inverse modeling to find out what is the subsurface slip that has caused these velocities. And we also use these vectors to calculate the geodetic strain. And then we calculate the seismic strain using the earthquake activity in the region. And then we do a composite analysis of both geodetic and seismic strain to give what is the magnitude of the earthquake, probable magnitude of the earthquake in that region, and what is the recurrence interval of the earthquake. So in a nutshell, this is what we do using GPS data for earthquake hazard. So all these areas we have done, and for last 20 years. And GPS data, you at least need continuous data minimum for 3 years to say anything. Since we have a long head start, we were the first to start this program in India. So we had a head start. So we had a lot of data. So we could do all this. We could achieve all this. So this is our what we achieved from GNSS observation network. Now I will go see, these are all the vectors which you're seeing are the global vectors, that is in the global reference frame, which is called International Terrestrial Reference Frame. Our India is moving in this direction, that is in the northeast with an anti-clockwise rotation. But if we want to find out what is the deformation within our Indian plate, then we have to have a pole of rotation for Indian plate. So that also, since that to do that, we need the data from Indian plate, and then we have to compute the pole of rotation. So we computed that pole of rotation. So these, whatever vectors you're seeing here are all global sites, that is international GNSS service sites. So we use these vectors and then our data, and then compute the Euler lat and long and the Euler pole of rotation of Indian plate. So you can see this pink dot is what we have computed. These are all that have been computed earlier using very few stations. We have computed using around 80 stations. So this was published. I've given all the publications also. Whatever I'm presenting is all published data. So once we have the Euler pole of rotation, which we call Indian reference frame, then we can put whatever that purple vectors you have seen earlier into Indian reference frame. So I'm just showing for Himalayan arc. I'm not showing for the whole of India because that becomes too much. And this is a 15-minute talk. So I'm only going to show for Himalayan. This is around 2,500 kilometer arc. But you know, the Kashmir is not covered here because these measurements are till 2014 when we did not have Kashmir measurements. That network started in 2015. So that I'll show you in the next slide. But here, so this is all the velocity, surface velocity of Indian Himalayan sites. So these range from around 12 millimeter per year to 20 millimeter per year till northeast, till Arunachal Himalaya. So this whole thing, this in between one, Nepal is not ours. So that is marked in pink vector. So using this surface deformation and then inverse modeling, we give the slip rate on our main Himalayan subsurface, main Himalayan thrust. So we computed that and we found out that for each segment of India, it is each segment of Himalayas, it is different. So that you can see here. So this is one of our this thing. And for this particular Himalaya, where we have a very dense network, Garhwal Commune Himalaya, we have actually calculated the seismic strain, geodetic strain and seismic strain and did a composite analysis, as you can see here. So our seismic and geodetic principal strain rates, though the direction is same, they match for 700 years of seismic strain. Our current geodetic strain matches with 700 years of our seismic strain. So which basically says that an earthquake recurrence interval for a magnitude 8 earthquake will be around in the order of 700 to 800 years. So according to our study, a magnitude 8 earthquake is anytime due in this region based on the strain analysis which we have done. And the next one is Kashmir. Kashmir we started in 2014. So for Kashmir, this is the first time we have integrated both GPS and broadband data for the Kashmir study. So you can see all these red, this is the Kashmir Valley. These are all our stations. These are all co-located with both GNSS and broadband. And these, that small red dots are all the seismic events picked up with a broadband. So we found a kind of, wherever we had an anomaly in the GNSS data, we found the same kind of anomaly in the broadband data also. So this also, and then here also we gave a slip model and both geodetic and seismic strain and gave a magnitude earthquake 7.3 anytime due in this region. So this is our Kashmir work, which was got recently published. Then after this, I thought I will just give a glimpse. I had this institute of Fourth Paradigm Institute. So we had Indo-Russian collaboration. Most of them are on seismic hazard. Actually, that I think my colleague will speak. But before I hand it over to colleague, we have an ongoing project of analysis of urban heat islands, air pollution, dynamics, and extreme heat wave phenomena in India and Russia, which is right now ongoing with one of our scientists in organization. Now I'll hand it over to Dr. Parvez to talk on his 2 slides are there. Yeah.
Thank you, Sridevi. Good evening to all distinguished speakers and experts. Well, I mean, as just Sridevi has mentioned, we had almost more than a decade long collaboration with our Russian collaborators, and one of my collaborators, Professor Kosobokov, is right here, who has already presented some of our results. So these are the project we have done under starting from ILTP to DST RFBR, and then again one more DST RFBR project we have done. And we have also actually we have submitted one proposal where we are going to apply AI also for our this project, where one of our colleagues from 4PI who is expert in AI is also part of that. So this is something just to have a kind of brief idea that our Indian and Russian collaboration in my institute is more than a decade old. Next one. Well, I mean, this is something which you have heard from Professor Kosoboko. This is a neo-deterministic seismic hazard map of the country, which we have published in 2003, and then a revised version of the same was published in 2017. And also we have given a chapter in the book which was mentioned by Professor Kosoboko. So this is basically, you know, I mean, it is not like empirical relations based peak ground acceleration. It is basically using the dynamics of the earthquake source and physics of the earthquake. We simulate the whole synthetic seismogram, keeping the dynamics of the source, receiver, and the path. And then once you have a kind of synthetic seismogram, you have all kind of parameters which is required for the seismic hazard. So we have similarly, we have a peak ground acceleration, peak ground velocity, and peak ground displacement. And as you know, many of the structural engineers, they are also looking for a peak ground displacement, especially for the long period where you have big earthquake at the larger distance. So this is one of the most cited work for the country, which is done by our institute. And then I mean, I'm not going to show all these maps, just one of the main map, which is peak ground acceleration. And similarly, next slide, Sridevi, we have also started, I mean, we have enough competency on the earthquake hazard, but now as you have heard many of the experts that the main goal is to quantify the seismic risk, because that is where we have to work on that. How can we use our database based on earthquake hazard or vulnerability and population and exposure. So this is the attempt we have made using our Indo-Russian collaboration. And I think one of the figures was already discussed by Professor Kosoboko. This is a similar figure where we have just convolved the neo-deterministic hazard values plus population density and the exposure in terms of vulnerability and different kind of structures. So these are the 4 models we had used, where different A, B, C, and D are basically depending on the vulnerability, how we are using. Somewhere it is, first one is like directly we are using, then the second one is as proportional to the population density, and the third and fourth is based on the parameter which is resulting from the exposure. So this is one of the example, and because of limitation of the time, we cannot show all the examples, but this is what we are working in terms of earthquake hazard and seismic risk, and continue to do so in future. So Sridevi, you can take over from here.
So that ends our seismic hazard. Landslide hazard and GNSS, we actually did real-time monitoring. So this is a landslide in Pipalkoti area. So we use not only GPS, we have also used geotechnical instrumentation, and this is the landslide observatory. We monitored this landslide for 5 years. So this is, I don't know why it went up. So this is our GPS station, close-up view of our GPS station. And this was a very successful project. For 6 years we did. And right now we are not doing, because that was that time. And then we gave really real time, we gave the results how we can show the integration of all the data, the instrumentation data, geotechnical, satellite, everything. So this was something which we did real-time monitoring. And then I can't go much into detail because of lack of time, but you can always, this is published in a book as a chapter. Then coming to water vapor, and that's called remote sensing. So this is what is the water vapor column for all the GPS sites which I have shown in my first slide. Some of the GPS sites, around 15 of them are real time. We get the data in real time. And we also clock the data both at 30-second interval and 1 second interval. So the 1 second interval data, when you plot, you also get something similar to broadband seismic map. So that can be used for real-time. You can give around 3 minutes before the earthquake, some kind of that the earthquake is impending. In actually Japan, they tried doing it. They did it, but then 3 minutes is too less to do any mitigation work as such. So this is our, and I forgot to mention that in the earthquake hazard. So I said that. So coming to water vapor, this is a water vapor column. So what we did, GPS water vapor integrated with both ERA interim, all the satellite data, basically ERA interim and MODIS also. And then this is the MODIS water vapor. And then we gave what is the, if you take GPS water vapor is the most precise, how much, what is the bias and all for the full Indian continent. So it is now very well published. And as I told you, our highest station Ladakh, for that we have correlated water vapor versus precipitation. And we also could catch the 2006 cloud burst in that region using our GPS data. So as you can see in this figure, the 2006 cloud burst, this thing. So we could catch it using the GPS data in this region, in that Ladakh region. That's, you know, that is a cold desert where it does not rain at all. So, but still that cloud burst happened and we could quickly catch it. So we can use GPS data for extreme rainfall events, and also the water vapor which we get using GPS every 30 seconds can be, when that right now we are working, can go into the weather forecast models as an input, and then your weather forecasting improves. So for India, abroad they are doing, for India now we are doing that also in our institute. So that comes under data intensive, under the scope of data intensive research. And then my last slide is ionosphere studies. We have started this around 5 years back. So for all the data we have for last 25 years, we have computed total electron content every 30 seconds for every satellite. So that's a huge data. And then we have used that for several ionosphere variability studies. And our data also shows, the data we had also shows that anomaly in the ionosphere for 2004 earthquake. That also we have published for the 2000, what is the anomaly. And, but we did everything post the earthquake. So, but then we can use as this as a precursor if you have to do. And we have also related it with the international ionosphere that is available, IRI Tech. And then we gave how, this is for one station, that is my Bangalore station, over a period of 20 years. So you can see the plot. So this is my, where I, from where I'm talking, this is where I study. The station is there. So we plotted GPS and IRA Tech, and then you can see how the variation is with solar radio flux, sunspot number, RMS. So this one map I will show, because ionosphere is a very huge topic which needs a lot of time to talk. So I think this is my last slide, basically, and then thank you. I hope I'm on time.
Okay, thank you.
Yeah.
So let's move to the another presentation. I will make it myself. Just a moment. I will.
I think I stopped sharing.
Please stop. Okay, thank you.
Yeah.
Okay. Okay. So in this brief presentation, I will point to another aspect of application of electromagnetic triggering phenomena, namely for earthquake prediction. So the title of presentation is Space Weather and Earthquakes. I will provide you with a brief overview of the problem and future research. This research is supported by Russian Foundation for Basic Research and National Science Foundation of China. This is cooperation project, and I hope if maybe somebody will be interested in this research, we may submit another cooperation project proposal. We carry out this activity with Institute of Crystal Dynamics of China Earthquake Administration, with Izmiran Institute of Ionosphere, Institute of Terrestrial Magnetism, Ionosphere, and Radio Wave Propagation of Russian Academy of Science, and a national research station located at the northern Tian Shan. So motivation is, I told that before in the previous presentation, that the earthquake represents one of the nature's major challenges to humanity, and according to the China Earthquake Administration, the catastrophic seismic events are beginning to threaten the sustainable development of China's economy. So we should say that today there is no reliable method for short-term earthquake prediction based on precursors. I demonstrated the failure of Parkfield earthquake prediction experiment. In this connection, another approach is another concept of earthquake prediction is proposed by Professor Soloviev from the Institute of Physics of the Earth. This concept is based on triggering impacts on the earthquake source, and the following steps towards predictability of earthquakes look reasonable. It is based. This concept is based on the observation of behavior of rock specimens under pressure when they are very close to failure, when the sample is close to failure. So this is unstable area where very small impacts on the sample may provide the triggering effect and the rupture or failure of the rock sample. The external triggering actions may provide two effects. At first, they may provide some additional stresses here in this area, and the shear stresses in the fault may exceed the critical value for this area. Or another effect may be the decrease of under external triggering action, decrease of the fault strength, and so that means the decrease of critical value of shear stress in the fault, which provide the fault rupture. In this connection, we submitted the Russian-Chinese cooperation project, and it was supported from both sides, from Russia and China. And this project is directed to further study the interconnection of processes in the ionosphere, atmosphere, lithosphere system, and seismic-prone regions for solving the problem of seismic hazard mitigation relevant for Russia and China. So the specific objectives of the project are to refine existing models of the relationship between the earthquake source and space weather parameters based on the data of space monitoring by Chinese satellite CSIR-1, as well as to analyze the degree of an influence of variation of the space weather parameters on deformation process in the earthquake source and the possibility of triggering the seismic events by strong ionospheric disturbances. So this is our part, because we carry out the study of electromagnetic triggering phenomena approximately 20 years. The scientific novelty of the project is to obtain new results on possible ionospheric precursors of strong earthquakes according to new data from the CSIR-1 satellite. and their theoretical justification. It will be this part will be made by Chinese team, as well as the physical justification or refutation of the possibility of earthquake triggering by strong bursts of geomagnetically induced currents in the conducting seismogenic fault of the Earth's crust. The project will provide an analysis of satellite observations over the seismic prone regions of Russia and China, the refinement of the model of ionospheric lithospheric relations, and numerical analysis of induction of telluric currents in the conducting zones of the Earth's crust, namely in the poles, by strong geomagnetic disturbances and their effect on deformation process in the earthquake sources. Physical modeling will be performed at laboratory setups located in our institute for a study of generation of telluric currents and their concentration in the conductive model fault, triggering of a laboratory earthquake by electrical pulses at spring block models of seismogenic fault, and rock failure under electromagnetic impact. The obtained laboratory data will be compared with the impact of space weather on the parameters of repeating earthquakes observed in China, Russia, Japan, and in the USA. The results, the results of the project will have a fundamental importance in terms of understanding the relationship between space weather and Earth seismicity, and possibly may be used in future technologies of the short-term earthquake prediction. So I will briefly outline the Chinese part of the project, and further we'll don't touch it. The satellites detected the pre-earthquake signals. You know that the first results were obtained by Menon with the application of intercosmos satellite when in the end of the last century, some ionospheric disturbances were discovered over the seismic prone regions just before the strong earthquakes. There are several satellites for monitoring of the ionosphere, and these results may be used for earthquake prediction, and the most prominent satellite is Demeter, so detection of electromagnetic emissions transmitted from earthquake regions, which was operated from 2004 to 2010. And you see here the example of Demeter electromagnetic observation shows that some disturbances of geomagnetic field were discovered before the earthquake. So China, about 3 years, more exactly on February 2 in 2018, China launched electromagnetic satellite CSIR-1 to study earthquake precursors. So it is a significant complementary to the country's ability in the study of seismic precursors. The specific objects of the project are to refine existing models of the relationship between the earthquake source and space weather parameters based on data of space monitoring by Chinese satellite CSIR-1. So, and to date, they observed some anomalies just before the earthquake magnitude 7.3. So, and they considered this observation, this satellite monitoring, as a promising tool for short-term prediction of the strong earthquakes. But our part is the question of a possible impact of solar processes on the Earth's seismicity. So this history is very long. Even Pliny in the 1st century AD in his natural history noted that earthquakes in the Mediterranean region occur more often at night than during the day. So, and after that, the statistical analysis of Shimshoni and Deshirevsky and Sidorev from the Institute of Physics of the Earth they obtained the results, confirmed this supposition. In 1853, the Swiss astronomer Rudolf Wolf indicated that the sunspots may have an influence on the earthquake occurrence, and you see here some correlation between the sunspot number, which is named just now like as a Wolf number, and number of earthquakes occurred around the globe. So, brief overview of their previous research indicates that at first it was a search of correlation of the Earth seismicity and solar activity by several authors. But the studies completed today on a relation of the Earth seismicity and solar processes provide a fuzzy and contradictory results. I mean this publication. So certain dependence of global seismicity on 11-year solar cycle was noted. Positive correlation of a number of earthquake and phases of 11-year solar cycles. But there is converse proposition that the 11-year cycles of seismic activity have inverse correlation with cycles of solar activity and geomagnetic disturbances. Levin Thomas from the USA and Kozyrev and Pilipenko indicated to insignificant solar terrestrial triggering of earthquakes. But we should note that the results obtained to date are statistical only, without consideration any physical mechanism of possible earthquake triggering by several space weather. And we proposed to start from to clear this problem, to start from the geomagnetic induced currents as a possible trigger of earthquake. You know that today this is a very popular topic of investigation of geomagnetically induced currents and their impact on the infrastructure, like power supply lines, underground cables, pipelines, and so on. But in the fault, in the crust, there are another conductive structures, namely the faults where the earthquake may occur. And the faults have the electrical conductivity in several cases, several orders more than surrounding rocks due to saturation of conductive mineralized fluid. And we developed the model of possible mechanism of stimulation of seismic activity by ionizing radiation of solar flares. And this model was published in the Earthquake Science journal in detail, but I'd like to show only the final results. So when we consider the layered structure of the Earth's crust for this area where we carried out the active electromagnetic monitoring experiment, we have there the conductive layer at the depths of from 10 to 15 kilometers. Just in this area, the most epicenters of earthquake are located, regional earthquakes. So, and according to numerical estimations, so during the strong solar flare of, for example, of X class, we may anticipate the sharp flash of telluric currents in the conductive layer, and this value is 10⁻�6 amps per square meter. So this estimation of electrical current is comparable with the current provided in this area by pulsed MHD generator and current density produced by MHD generator in the Earth's crust is 10⁻⁷ or 10⁻⁸ amps per square meter. So these values are comparable. So we may anticipate that the solar flare flash may produce the current, electrical current in the faults, resulted in the earthquake triggering. So, and we, for supporting this idea, we analyze the global daily number of earthquakes before and after a solar flare of X 9.3 class occurred on September 6 in 2017. It was accompanied, it was followed by strong magnetic storms, is KP index 8. And we attended the next picture. So this is a solar flare. This is a magnetic storm, and we observe the sharp increase of global seismicity, like in the case of current injection into the Earth's crust. So when we consider the time window 5 days, so the number of earthquakes before and after solar flare differs 2 times. So this is increased 2 times of seismic activity. Of course, to consider, it doesn't mean that each solar flare or strong magnetic storm will trigger the earthquakes, because when we carried out the experiments on the spring block model during electrical current injection into the model fault, simulated crust fault, we observed that earthquake triggering by electrical current is possible only when the system is near critical state. So, for example, if we will inject current here, we will not provide the triggering effect here. So, in this case, we need to know the level of maturity of the fault for to the rupture. When we injected the electrical current into the simulated fault, just in this critical area, we trigger the laboratory earthquake, so sudden slip of this running block. And in this case, in comparison with the seismic cycle accumulation and drop of stresses in the fault, we observe when we compare the seismic cycle without electrical action and with electrical current injection, we observe the shortening of recurrent period by 20%. So in this condition, we decided to consider the so-named repeating earthquakes and an impact of strong magnetic storms on the recurrent period of this repeating earthquakes. Repeating earthquakes, there are seismic events which occur in the same point with the same magnitude and with the approximately equal recurrent period between the earthquakes. So you see here that San Andreas Faults, the red points, it is not the epicenters of single seismic event, but it is location of a family of repeating earthquakes. Voy et al. With co-authors published in Geophysical Research Letters the analysis behavior of recurrent period of repeating earthquakes under dynamic impacts of distant earthquakes. So the red line are the dynamic impacts on the repeating earthquake families. We selected from these catalogs only these areas where there were no dynamic impacts, but during these periods were some strong geomagnetic storms with index over 8. So, and we found that the strong magnetic storms which occur in the second half of the seismic cycle result in shortening of recurrent period. So they triggered the next earthquakes. And this shortening is in average by 20 to 30%, like similar to the preview to the laboratory experiments. And we consider that confirms the possibility of earthquake triggering by strong perturbation of a geomagnetic field. So, this is summary conclusions. Of course, they should be continued because the project is underway. So the space weather phenomena like solar flares and geomagnetic storms can generate telluric current density similar to artificial power sources which provide the earthquake triggering. So we observe that behavior of seismic activity after solar flare and geomagnetic storm is similar to increase the number of local earthquakes after injection of DC pulses into the Earth's crust. Of course, we need some reliable physical models explaining the electromagnetic earthquake triggering phenomena. Before earthquake alert after strong perturbation of space weather, we need to select the areas favorable for electromagnetic earthquake triggering from point of view of the fault maturity to the dynamic rupture, its electrical conductivity, and of course, orientation for induction of extreme geomagnetic induced currents, which may trigger the earthquake. So that's all for today. Thank you for your attention. I don't know have we some time for questions. Because the schedule is very tough. Maybe if you will have a question, maybe I will answer at the panel discussions. So let's go to the following presentation, which will be made by Professor Bharat Lohani. From Indian Institute of Technology in Kanpur. The title of the presentation is LIDAR Technology for Disaster Preparedness. I'd like to say that Professor Lohani applies the high resolution remotely sensed data, especially LIDAR data for 3D modeling, visualization, and various other applications. And also he used GIS for innovating application. Professor Bharat Lohani obtained several national awards. Okay, please.
Yep, thank you. Thank you very much, Professor Novikov. And thanks for introduction and thanks for inviting me to talk about this LiDAR technology and how it can be useful in relation to the disaster. So yes, my area of research is in basically geospatial data, particularly the high resolution LiDAR technology and photographic data. And I work in data generation, data processing, sensor calibration, and developing algorithms for data understanding, and finally, application of these data in different domains. So we have been working with applications which are related to the disaster. And so I will be showing you some use cases like that. Before that, I will quickly take you through the technology and what we are doing in India about this. Because till some time back, we didn't have the LiDAR technology in India, but yes, with concerted efforts at IIT Kanpur, and also, for example, you can notice that I will be using a logo of Geono also, because this is a company which was founded at IIT Kanpur in our institute, and I was co-founder in that. So I'll be using the data that is being produced now by this company in India. That's why I'm using its logo, along with the logo of IIT Kanpur. So the basic idea here is, right. So that's my outline. And I know the time is very, very short. I would like to finish within the time. So very quickly, I will go through the things. One thing that we are seeing in the presentation since morning, that the data about the Earth is very, very important, which we call the geospatial data. In absence of that data, we cannot prepare for the disaster properly. So we need that data before the disaster. During the disaster also, we need the technologies which can capture once the disaster is happening or immediately after the disaster. So in order to assess the damage, in order to assess the impact. And then later on also in the post-disaster scenario, we further need to capture the data of the area which is affected by disaster, so that we can have a better understanding how we can minimize the impact of the disaster in afterwards, and how we can go for the rescue and other things, and also the long-term measures that can be taken post-disaster. So we have seen several disasters where, in absence of these good quality data, the preparedness was not good, or during disaster also we are not good. So I'm trying to make a case here, the case for good quality data, geospatial data, which will help in preparing us for disaster as well as after the disaster. So once we say this, the data should be accurate, as I'm writing here. The data should be accurate. Data should be complete also of the area of interest. It should be updated data, and data should be readily available so that I can use the data quickly in the models. And the data capture technique also should be fast. So these are the basic characteristics of the data that I would like to say. And in absence of such data, I could not stop me by from using this cartoon, but this cartoon depicts so well that if we are not prepared, we don't have the right kind of data, in what kind of situation we may end up. Now there are various other ways, the data that we need. We can have the point elevation, we can have some surface profiles, we can have contours, we can have 3D models, we can have building plans. All these are the types of the geospatial data that we need. One more thing that I would like to bring here, that is the difference in 2D data and the 3D data. Because in the case of the 2D, we have got the XY positioning, while in 3D, we have got XYG positioning, which we also call topographic data many times. And till some time back, the more emphasis was on planimetric data, only XY data. The jet data, if at all it was there, was not of good quality. But our disasters are happening in 3 dimensions. So we need also the data of 3 dimensions. So we need the 3-dimensional representation of the Earth, and several phenomena which happen on our surface, they happen in 3 dimensions. So in order to understand them, in order to model them, we need a good quality 3D data. Now there are various methods by which these data can be generated and have been generated, which we know it. But today, because I'm going to talk about the new method of, not new I will say, but the method of LiDAR technology. So I would like to present the advantages of this LiDAR over the other methods. Of course, each of these methods, whether total station, GNSS, whether the photogrammetry from drone camera, or whether the satellite data, they have their advantages. However, the LiDAR data, which can be captured from different platforms, including the aerial, mobile, terrestrial, or the drone platform, each is considered to be the best among all these data for the 3D capture of the Earth terrain. Now, I will quickly go through that because what is the way the data is captured, we understand with the help of a laser transmitter and integrating that with the GNSS, IMU. Once we integrate all of these, it is possible for us to capture a large number of points on the Earth's surface. And for each of these points, we'll have their coordinates determined to certain accuracy. Now, depending upon the method, the accuracy of the coordinates can be up to 1 centimeter to 15 centimeter, 20 centimeter, depending what kind of laser scanning we are using. So once we do that with the aerial platform, that is how the data are generated. And this is an important thing over here. I'm trying to show that currently the available technologies make it possible to measure up to 18 million coordinates every second. So that's a very good quality data. Whatever is there on the terrain, whether it is the transmission line, whether it is the undulations of the terrain, whether it is the road or the building top or the trees, everywhere will have the XYZ coordinates observed. Now, these coordinates, once we have this, we can utilize them for the further work. Now, this is another way of capturing the data, which is the terrestrial laser scanning data. And we have used this scanner also for landslide monitoring. Then we have another way of capturing this data, which we call the mobile mapping. In the case of the mobile mapping, like in case of airborne, we are flying the sensors in an aircraft. Here, in the case of the mobile, we keep these sensors on a car, a vehicle, and that vehicle goes along the corridor, a road, and captures the 3D coordinates of the things surrounding. So over here, the image that we see is a point cloud data where each point we know their coordinates. So the data will look like this. Here is one example of the data, another example. So in order to understand this data or in order to talk about this data to someone, I like to call this data as 3D xerox of the ground. And why I'm saying this, because with capturing the terrain, scanning the terrain, with the help of this technology, it is possible for us to bring the 3D model of the terrain in my computer. Then I can develop models to run on this data. So that is the advantage of this. And in addition to LiDAR data, we also capture now the photographic data. So these two go together. Once we have the data, the photographic data and the LiDAR data, then we develop the algorithms in order to classify the data in different categories. So I'm not making this presentation as the research presentation because we have done the research in this area. We have published papers in this where we write algorithms in order to classify the data in different categories, whether the data are on ground, on buildings, on trees, and so on. Then another step that is done in the data processing is we can separate the points which are on the ground so that the ground or the DEM of the area can be generated. And from there, we can obviously generate the contours and the orthophotograph, which is a very useful product. Whenever people are working in a disaster area, they need a product like orthophotograph where the measurements can be taken as well as the visual details are very, very clear. Finally, this is again one data product that we generated in one of our projects. And this is finally the GIS layers which are required for any modeling. I will show you one video here, and because this will give you the idea of the data that we are generating for the hills in Himalaya in India. So here, this is the data somewhere in Uttarakhand, and the LiDAR data were captured with the help of an aircraft, keeping the sensors there. So the data captures the terrain so well that we can make use of this data. For example, say of course, in many developmental projects, we can make use of this data, but at the same time, we can make use of this data for disaster preparedness. For example, with this kind of the data, we can carry out the dam break analysis, we can carry out the landslide modeling. These are possible with this kind of data. So here I'm showing you the data where it's the raw point cloud, and the way we work in the processing, each point is given the corresponding color in order to have a better visualization of the terrain. I will skip this also. Yeah, that's the output of the data when we do the classification. So the points have been classified here. The ground is being shown by orange color, the buildings by yellow, and so on. And so that we can separate them out later on. Currently, we are working on deep learning based methods for these classification. Once the data above the ground, the trees, the buildings have been removed, this is how the terrain looks like. So this terrain, let me tell you, those who are not initiated in the LiDAR technology, we have the data accuracy in the case of the airborne, what I'm showing you here. Each point there on the ground is accurate to 15 to 20 centimeter in the vertical, and similarly in the horizontal. And we have the data density of around 10 to 15 points every square meter. It can be plus minus in there. Now with this kind of point cloud, the DEM that is being generated is highly representative of the terrain. So if you are going to do, for example, landslide hazard zonation map, this kind of data will become highly useful. Again, if I go further from here, so yeah, the same data, and that's the orthophotograph. The 3D data is wrapped with the corresponding photograph there. And finally, with the contours. So I will skip to the next slide. And here also, again, another video, and that's the different way the data are generated. In this case, the data are generated by keeping the sensors on a vehicle, and the vehicle is going along the road, and the point cloud is being captured. And here also you can notice the colors are given to the points because the data has been classified. Again, for the hilly terrain, for the landslide assessment, and this kind of data becomes very useful. And we did a project in Vaishno Devi area using the laser scanning technology, as I'm showing you over here. So this data has got several advantages if you compare. One advantage that I always like to talk about is in comparison to the satellite data, aerial photographic data, or the GNSS or the total station, the LiDAR has the advantage that LiDAR can capture the data even under the trees. And this is because the canopy or the tree canopy has got the holes, and the laser pulse travels through those holes and can give me the coordinates of the point on the ground, while the other technologies, it is not possible. So here is one example of this. The image on the left, yeah, the image on the left here, this shows you the terrain with high vegetation, so we can't see the ground underneath. However, with the LiDAR data, if we remove the trees or the above ground things, what we get is the actual terrain. So this is the advantage of the data. Similarly, another example of this, here's the satellite image, that's the aerial photograph, LiDAR data. Once the LiDAR data is processed, this is how we can see the terrain. So LiDAR has this ability to see underneath the forest, which is very useful. And of course, LiDAR has this ability to map very fine details like the transmission lines. Now, some of the applications in disaster, flood, because I saw, this morning, Professor Gupta from IIT Bombay, he was talking about the flood modeling. And whenever we talk about the flood modeling, we have very sophisticated models. However, these sophisticated models, they need to be supported with very good quality topographic data. So here is one example. If the flood modeling is done with the poor quality data, the yellow color here indicates the uncertainty, the area of uncertainty. So what we notice, the area of uncertainty in this case is quite large because the data is poor quality. While if you go for the better quality LiDAR data, we noticed that the area of uncertainty has been reduced. So this helps us in taking better decisions in case of the disaster. Similarly, here is one work which we have done in IIT Kanpur for the urban flooding, and we can model now urban areas very accurately for the flooding purpose. Another work that we are doing, and this is for forest mapping. Specifically, I'm not working for the forest fire, rather we are working on mapping each and every tree, isolating that individually, segmenting it, and then for that tree, determining its morphological parameters, and on the basis of that, coming up with the biomass and the carbon stock of the tree. The work that we are doing here, we are trying to make use of our traditional approaches, and as well as we are going for the machine learning and the deep learning approaches now. Now, the same work, because here's an example of this, our study site. So that's the aerial photograph, and this is the LiDAR data, a sample LiDAR data, and a cross section of the LiDAR data showing you how the LiDAR data looks like. And then the data after segmentation, each and individual tree has been segmented. Then this is an schematic of an individual tree that after segmentation of an individual tree, we can determine the parameters of the tree. We can measure those, which will be the tree height, canopy position area, canopy base height, or the tree location, as well as the attempt is being made to determine the tree species with the help of the spectral information. Now, once this information is available for each and every tree in the area, a GIS base like this can be created. So, though I'm not working currently in the case of the forest fire, but this information, along with the DEM of the area, along with the other features, for example, the road network, the water bodies, all these are useful for modeling the forest fire. Similarly, in the case of the urban disaster, urban flood, we talked about emergency route planning, and any pollution movement in the urban area will require a 3D city model. And this is what we are doing. Here is one work that we have done for a part of the city of Chandigarh. We have created, using the LiDAR data, the 3D model of the part of the city. Of course, right now, what I'm demonstrating here is the availability of the sunshine on the rooftops. That is what actually is under the demonstration. But with this kind of the 3D models of the cities, they will be highly useful for before disaster, during disaster, and post disaster. For example, in the case of flood or in the case of the earthquake, this will be useful there. Landslide, yes, as I spoke earlier also, the data can be useful in landslide. So finally, yes, my conclusion, it is important that we should have a good quality geospatial data, and LiDAR technology is highly suitable for creating three-dimensional, good quality, accurate, precise geospatial data. And what I'm trying to make, the case that I'm trying to make through this seminar is on the need of generating these data. Number one, for entire cities, state, and countries, and of course, for the areas which are prone for disaster. So there is a need for that, so that we can use this data in effective management of the disasters. Well, thank you very much. I hope I'm within time. Thank you.
Виктор, вас не слышно.
Thank you for the presentation. We have 1 minute for short question and a short answer. Are there questions? Okay, let's proceed.
Thank you very much.
Thank you. So the next presentation, the next talk will be given by Dr. Vsevolod Maraido, PhD, senior researcher from the Water Problems Institute of Russian Academy of Science. He graduated in 2004 the geographical faculty of the Lomonosov State University in Moscow. The area of research is development of dynamic stochastic models of hydrological processes and the method of their application for analysis and stochastic prediction of hydrological phenomena. Dr. Moderator is author of many papers and 2 monographs. Всеволод Михайлович, please. Please switch on the microphone.
Там в Zoom проблема. Yes, can you hear me now?
Yes.
Good. I'm sorry. I'm sorry for that. So thank you for giving me the opportunity to take part in this absolutely outstanding event. I'm very happy to hear all the presentation from the colleagues. Thank you very much. So for my part, my talk today will be regarding the flood hazards and its opportunities for monitoring, identification, and technology for forecasting. So as it was said, I come from Water Problems Institute, and I would like to acknowledge my colleagues that took part in this particularly case studies that I'm going to be talking about, and creating the technologies that I'm going to be talking about. And so here's the outline of my talk. So I will identify the main problems Russia faces in terms of hydrological hazards, and especially what societal issues there are in Russia that we also trying to assess and address in a way. And then I will show you some technologies that we tested in our institute, and maybe some projections for more studies in this regard. And I will conclude with some take-home messages from my speech. So in terms of flood hazards or hazards that are connected with water, there is a certain outlining of all the what is connected with this topic. So the water security, as identified by the UNESCO International Hydrology Program, is there are 3 main aspects. There resilience from floods and inundations, especially of some human structures like cities and rural territories. Then provision of fresh water to the public, and at the same time preservation of ecosystems. So in my talk, I will be focusing on floods and inundation in Russia. Well, we may say that Russia is a relatively not the world's most prominent countries in terms of flood hazards. However, there are 2 main regions in Russia: the Black Sea coastline over here, and the far eastern part of Russia, that are almost annually facing several severe flash floods due to heavy rainfall of convective precipitation in the Black Sea coast, and to tropical cyclones that are hitting the far eastern part annually. So, as I said, Russia is pretty resilient in terms of flooding. However, only 2.5% of its territory is affected by severe floods. But at the same time, 40% of damage is caused by floods. And of course, a lot of casualties, a number of casualties are attributed to this particular phenomenon. And we can say that in recent future, the causes for flood damage may increase due to climate change and to increased population and human stress on floodplains and channel streams. And it is very outstanding that between 2000 and 2013, there were 3 main events in Russia, main flood events, that are actually responsible for 84% of all casualties from the floods. And these are flash flood associated events. And of those, mostly the flash floods were absolutely responsible as in 2002, the same in 2012. There were contrasting casualties that in 2002 there were mainly outdoors, and in 2012 it was mainly inside structures, so, because the flash flood came at night. So it's absolutely crucial to have a profound forecasting system and to assess where the circumstances that led to fatalities to design the flood prevention for local communities, such as this kind of science or several text messages or general public awareness in terms of flash flood. So after 2012 flood event, in this region where the most severe, this particular severe flood happened, there was a certain flood warning system established that uses more than around 200 automatic ultrasonic gauges. Here you can see my colleague standing at one particular measuring gauge that provides data in real time with 10 minutes time steps, and is used by the local emergency systems to prepare the general public and to issue the hazard forecast. And furthermore, this system is freely available. And for one of our studies, we used this data, this highly frequent data from two these ultrasonic gauges, to treat it as a big data data set and try to model, to set up a machine learning and artificial neural network model to predict the water levels in advance for 1 to 20 hours forecast horizon, which, as you can see in terms of the error and accuracy, turned out to be quite well. So the specific error and accuracy measures show that up to 20 hours the forecasts can be reliable and accurate. So this is one of the methods to provide a short-term forecast, and based on this, the building the capacity in the population or in some special emergency services to provide population with information on forthcoming events. And but if sometimes these simple models are not so good in terms of providing some further information about the system. So moving to another case study, the Amur River Basin over here in the Russian Far East is a very large river basin, nearly 2 million square kilometers, which is transboundary shared by Mongolia, China, and Russia. And it's one of the largest rivers in the world. So in 2013, there was a major flood event, which actually took place all over the basin, and it lasted for about 2 months. So it gradually inundated its floodplain, very large floodplain. And sometimes the characteristics of maximum discharge or maximum reverse discharge are so outstanding, as it is in this particular case, that it overtopped all the statistical records from more than 100 years. So with flood discharge of 46,000 cubic meters per second. So sometimes the statistical measures or some data-driven models are not efficient or cannot be used when the society, when designing the flood control structures or dams, using only this kind of statistical models or data-driven models when this kind of outstanding event is coming. So in this particular case, one option is to, well, one of the best options that is arising is to use the process-based hydrological model, which describes several dozens of processes in the river catchment that starting from precipitation transfer through soil, the evaporation and flow in the river reaches. So the kinematic wave flow, which can be used to identify hydrological state in almost any point within the catchment surface, because it uses specially distributed information regarding the elevation, the soil types, the soil properties, such as infiltration rate. It uses specially distributed weather data from any weather station available, including some gridded products that are available now, the global gridded products. And it can also use information regarding the evaporation from different kinds of landscapes, and it calculates. It can calculate the runoff on a subcatchment by subcatchment scheme. So, thus providing the stream flow in any part of the river, of the stream network, which is here. The shown are simulated and observed stream flow hydrographs for some several year periods that we used to test the model of this particular catchment. And what it showed is that during the particular flood event, it not only could provide the forecast, but what is more crucial, it could provide the insight on flood control capacity of the several hydropower projects, of several river reservoirs that are situated in the catchment. So here you can see the thick black line is the actual flood hydrograph, and the thin black line is the calculated hydrograph that could occur if there were no reservoirs in this particular catchment. And here is almost 6,000 cubic meter per second is the estimate of the flood control capacity of these reservoirs. And of course, these flood control structures are in a way also dangerous for providing the input into occurring floods. So their safety should also be regulated and forecasted. So for several other flood control structures, hydropower dams in particular, the same model was used to calculate, to provide the short-term forecast for 1 to 7 days ahead. And it was tested in these particular reservoirs against the actual inflow hydrograph, so inflow curve. So it appeared to be useful in terms of providing additional controls for the dam control authorities to ensure the safety of this particular hydropower projects and for them to provide flood control capacity. So the same model is used to calculate several other state variables, such as snow height and snow water equivalent at its calculation of subcatchment. Here you can see the snow cover evolution in one particular time range in 2012, the historical evolution of snow cover from November of 2012. And it also can provide this estimates of snow water equivalent of soil moisture and of stream flow discharge in the river reaches in places that are ungauged. So in tributaries that are ungauged, however, they can be modeled to a certain level of accuracy. And when it is combined with the two-dimensional model of two-dimensional hydrodynamic model, it can provide flood inundation maps as for forecast, but at the same time on a scenario basis. And based on these scenarios, the local authorities can assess the extent to which the flood can be threatening the local structures, such as this is the comparison of actual and modeled flood height or flood extent in the same Amur and Zeya River confluence point, where the city of Blagoveshchensk is the large city of Blagoveshchensk is located. And so the same as I've shown you previously, the effect of dam structures on flood control. Here is the same effect shown not in terms of river discharge, but in terms of actual water stage, so water level. So this difference is the difference of controlled and uncontrolled water level by flood protection dams. So it could be 2.5, nearly 3 meters more inundated than it actually happened. And the same hydrodynamic model can also provide the estimate of water velocity in during the flood inundation. So here's the case study of flooding of city of Krimsk in 2012, a flash flood also mentioned earlier. So here is the actual structures shown in gray that are overlaid by velocity vectors from very slow velocities to severe velocities by flash floods. And concerning the previous talk by our colleague regarding the LIDAR technologies that can be used in flood protection and flood modeling, this actual and contemporary LIDAR maps are also very useful when constructing this kind of flood protection or flood velocity mapping for to build up the capacity in emergency services or in general population, to point out the dangerous zones that can be flooded or inundated during these severe flash floods. And scenarios can also be used in this particular technology, which is called the ensemble approach for seasonal forecast. So for flood control structures or for hydropower, this approach can be used, which we also employ in several of our projects, where a hydrological model that I mentioned earlier is pre-calculating the current state of the river catchment, and then it's forced with historical weather time series to produce a set of scenario hydrographs for the future, for several months up to season, to build a so-called ensemble of possible scenarios of how the hydrological situation may develop in the forecast horizon. So, and this could be used to provide probabilistic forecasts of future hydrograph, or to estimate the interval in which the particular stage will be varying, thus providing the actual probabilistic forecast. So to conclude, I would like to formulate several take-home messages from my talk. So hydrological and mainly flood hazards are very crucial for local communities that are very vulnerable especially for flash floods, if they are living in such natural conditions. I know that in India there are a lot of communities are vulnerable to flash flooding, and protection, of course, may use engineering approach, but and for this we can heavily employ the measures of or the approach of hydrological modeling, of multimodal approach to provide inundation maps for local authorities. But at the same time, the local communities should be also aware of the natural hazards that are connected to flood and to river itself. And as I said already, the structural design, the flood design can rely on this very highly developed and state-of-the-art models, multimodal approach that I showed you just a glimpse of, that we use in our work. With this, I thank you for listening to my talk. And also I would like to acknowledge that we have took part with our Indian colleagues from IIT Bombay, Roorkee, and Center for Water Research in Kerala, in a joint call for proposals between the Russian Scientific Foundation and Department of Science and Technology in India, with a project that is focused on artificial intelligence and hybrid models. Hybrid models meaning that we use hydrological models, the process-based models, together with artificial intelligence to indicate and to forecast extreme hydrometeorological events. And well, if we're lucky, I would be happy to work with my Indian colleagues. So thank you very much for your attention.
Okay, thank you. There are no time for questions, and I'd like to present that.
Some technical problems with our moderator. Just a minute. Perhaps he lost connection. Yes, thank you.
I think we lost our moderator chair, so I take lead to fill the gap.
Thank you very
May
much.
I? Thank you very much.
Good idea.
I am Dr. Rathore. I'm former Director General of Meteorology, India Meteorological Department, and permanent representative of India with the World Meteorological Organization, and currently working with the World Bank as a consultant. At the outset, I would like to make two confessions. Number one is that I'm no more an operational forecaster. And number two, that I'm no more an active researcher. I'm just an advisor, and be aware of advisors. They can speak anything and get away with it. And for next 20 minutes, I would be talking about the changing weather and climate scenario and the progress which have been made thus far, and what are the future challenges in terms of infrastructure for forecasting, and then what are the opportunities and challenges for advancement of numerical weather prediction and other new technologies. Now, the changing weather scenario is, as we all know, that weather forecasting is an initial value problem. So you take observations, analyze observations, define the initial conditions, and then extrapolate that initial conditions in both time and space to prognosticate the future weather conditions and whether we define in terms of various meteorological parameters. And it has been greatly benefited by the rapid advancement of science and technology, be it observational technology, be it computational technology and modeling, and so on and so forth. Equally responsible is the changing user needs with evolving user capabilities. User these days is very demanding, and he is able to demonstrate the use of such meteorological information in their decision-making process. And so therefore, a constant feedback from the user is very vital. And there are four overarching components of the entire spectrum, starting from the infrastructure, research and development, and operations and applications. And each of them have their own opportunities and risk and advancement, and a weather forecaster has to take note of that. We have been talking a lot about artificial intelligence, and that is the rapidly advancing technology. And I would start my presentation with the book by Henry Kissinger and Eric Smith and Daniel Houghton-Locher, who wrote a book on the age of artificial intelligence and our human future. And in that, they have listed a lot of dangers of such kind of technology. But weather prediction is making a good use of artificial intelligence, and that is the most benign phase of use of such technology. And be aware that the Los Alamos laboratory, who is considered as father of atomic bomb, had no doubt about the significant negative impact of the weapon they developed. And the bombing also, we knew that, I mean, at that point in time, people knew that humanity had entered in a new and very terrifying age. But the use of atomic energy for the peaceful purposes have really created more opportunities and benefits to the society at large. I won't spend much of time on the history of early history, but basically the progress we categorize in 4 eras. And early 20th centuries, we were working only through maps, and the observations are communicated and then plotted, and you analyze them and prepare the maps. And then synoptic methods are primarily used for preparation of the forecast. And then era 2, just at the time of World War II, we have a lot of more observation started flowing in and improved scientific understanding of the physical processes of weather phenomena. And thereafter, the advent of computing power and the remote sensing have led us to the era of numerical weather prediction. And now currently, if we take the current stock of at where we are in the state of weather forecasting, primarily now we are doing weather forecasting using numerical weather prediction models, where we are solving the various equations to define the atmosphere and extrapolate the atmosphere using hydrodynamics and thermodynamical equations with continuity of the motion. And the models we currently use are high-resolution global deterministic models, and the medium range, that is for about 10 days to 2 weeks time. The horizontal resolution is of about 10 kilometers with 50 to 140 vertical layers and 10 prognostic variables. And these models are run 4 times a day, and model run is for 10 to 15 days, as I said. But we are also making use of ensemble prediction systems for the medium range, which uses more than 50 ensemble members. And the horizontal resolution for that is about 20 kilometers. And for an extended range of about a month and a half, the resolution, horizontal resolution, is about 35 to 40 kilometers. And these models are working in the medium range, but to extrapolate in the seasonal scale, we need to compromise with our horizontal resolution and also the running cycles. But the major updates in these systems cannot be done very fast. It takes a little more time, maybe 5 years or so, with the rate of improvement closer to a week of extra lead time per decade for development of Mendel-Julian oscillation. Now, since major breakthrough technology plays the major role, and there are 3 aspects of technology uses in the weather forecasting. One is the observational ecosystem. Second is high performance computing ecosystem, and also the advancement in other infrastructure, which is leveraged through public-private engagement. And the observing infrastructure is primarily attempting to overcome the lack of observational data and data quality issues. And there is an emphasis on very high spatial observations to address, to further refine the temporal resolutions to describe sub-kilometer scale convective weather systems. And when we talk of convective scale systems, we are not able to go beyond the short range. When we go into the medium range, the convection simulations do not have that kind of skill. So, but more observations will help in further improving the medium range weather forecasting. The evolution of low-cost satellite program and constellations of nanosatellites is the things to come in. Then exploitation of data from observing systems owned and operated by various other stakeholders. Other stakeholders means those who are not under the umbrella of National Meteorological and Hydrological Services. And also the non-conventional observations like cell phone towers and a large number of other sensors which are being deployed these days, which we call as virtual sensors, Internet of Things, and devices like a smartphone sensor, etc., which have been talked by my previous speakers. But important thing is, before we make use of these data generated by these non-conventional observations, and also while exploiting the data from non-NMHS platforms, we really need to carry out a good sensitive studies, ensuring the quality of the data. Otherwise, more harm will be done than the benefits. As regards high performance computing systems, the future of HPC workflow are likely to be distributed across the cloud computing systems. And we have talked about it. And so we are now in the National Meteorological and Hydrological Services, and other players are moving away from single HPC centers toward which are as a federated structure. But we are moving towards the cloud. But there are concerns, and these concerns are to provide access to the remote users, and security concerns are also there. Therefore, a solution is needed to make the data open and accessible for diverse stakeholders from across the globe, and particularly the small countries. In terms of advancement of SNT, the new technologies, that the innovative technological solutions in observations and monitoring, with possible application in weather and climate forecasting by the private sectors. A lot of startups have come up with very innovative ideas, and these are low-cost solutions. And one of the example is miniaturization of the satellites. And the growing amount of data through private sector investment also underlines the data quality standards and also data inequalities, because in order to generate a good data ecosystem and preserving global basic infrastructure data delivery system as a public good, we need to also handle the data sharing policy. There are WMO resolutions 25 and 40, and we need to address issues which are related to that. The remote observing platforms such as autonomous drones and crowdsourced observations, which have been talked by previous speakers, along with public-private partnership in expansion of high HPC ecosystems, and transition to cloud solutions for computing and archiving, and better communication of the weather and climate information are things of the future. Challenges and opportunities for advancement in numerical weather prediction, there are about 5 aspects, starting from predictability to dynamic and physical modeling challenges, model and data assimilation shortcomings, new generation of computational technology, evolution of NWP and weather to climate prediction, that is seamless forecast and high resolution global ensembles. And now, in order to improve the modeling aspects and the predictability and dynamic and physical processes, a lot of research is required to be undertaken on interlinking or teleconnections between tropical and extratropical phenomena, the tropical and oceanic phenomena, and also mid-latitude weather regimes transitions, which is at the week 3 to week 4 time range, and the deep ocean circulations and ice sheet sensitivity to changing climate models, convective precipitation beyond the short range, and large-scale patterns of precipitation and mid-latitude circulation changes in climate change projections. So these are things where a lot of focus is now being given and a lot of research is being carried out. The uncertainties which are related to the data assimilation shortcomings are because major uncertainties are associated with parameterization of the key processes, such as convection and orographic drag and cloud microphysics and aerosol interactions and thermodynamic and dynamic coupling with the land surface, snow, and sea ice and their impacts on global. These are the kind of thing we need to improve the understanding and the feedbacks of atmospheric compositions to these kind of simulations. And also the handling of the errors in the data assimilation and insufficient use of diagnostic methods for tracing the error back to their roots in the models is very important. I think there is some. Now, challenges which are related to the other technologies are innovation through artificial intelligence and machine learning, leverage through public-private engagement, impact-based forecasting, computational challenges and cloud technology, potential breakthroughs from machine learning, verification and quality assurance, and automation of post-processing systems. These are some of the in things. And the presence of big data create expectations for various R&D into new forecasting technology, and the combination of new processor technologies and artificial intelligence methods allowing heavy-duty parallel data processing for various applications. And these artificial intelligence and machine learning will definitely is helping improvement, particularly nowcasting and short range forecasting. But the major working horse remains the numerical modeling. They are able to handle better handling of data and post-processing. But the major breakthrough will have to come through the numerical weather prediction only, because time is running short. Now we are in the era of impact-based forecasting, and therefore it is important to first assess the vulnerability and understand the user needs and user behavior and inculcate the impact-based forecast into our forecasting processes. And also the potential, I have already talked about it. So also the verification is very important. And with the evolution of impact-based forecast and warning, it is necessary to develop the verification methods which are way beyond the evolution of weather parameters into measuring success in predicting their impacts. It is not only verifying the meteorological elements. So impact verification is in thing. And so also the automation. There is always an element of man-machine mix process which we practice in the weather forecasting system. And with the development of decision support tools and post-processing tools and statistical post-processing of the model outputs, we are able to remove a lot of biases from our forecasting systems to improve the skill of forecast, and artificial intelligence and machine learning is going to further help in automation of our forecast products. Thank you very much for patience hearing to me. Thanks.
Okay, thank you, Professor Raptor. And the next presentation will be given by Dr. Nikita Astudin, PhD in engineering area. He is Deputy Head of Department of Special Data, Emercom of Russia, and the topic of his presentation is space monitoring and modern technologies for prevention emergency situations. Dr. Astudin, please.
Dear colleagues, I open my presentation. First of all, I want to say thank you for the previous reports. I think it can be useful for our work. It was very interesting. My report is about the space monitoring system in the Emercom of Russia. Space monitoring system has originated in the Emercom of Russia in 1997. It is aimed at monitoring the emergency situations, control their dynamics, and supervising territories and objects that are exposed to the emergency situations, and then providing the information of the Emercom of Russia. Space monitoring system consists of 6 centers settled on the whole territory of the Russian Federation that received space information, with a center in Moscow. The system received the operative information from 10 space units with a spatial resolution from 1 to 100 meters in visual, microwave, and infrared ranges. Thus, the Emercom solves the following tasks based on the space information: wildfire monitoring, monitoring of the emergencies that are triggered by floods and inundations, the assessment of scale of the emergency oil leak and the dynamics of the spread, the search of the emergency objects in the areas that are difficult to access. Since the beginning of the fire season, we have more than 3,500 satellite images in our base. Wildfire space monitoring is to ensure that timely detection of fire, to report this information to the owners of areas, and measures to protect settlements and critical facilities from the wildfire impact. Every day, 8 times a day, we collect and process the space information through Russia. Already in 60 minutes after receiving information on the location of fire heard and their characteristics, is transmitted to regional bodies of Emercom of Russia and regional agencies of federal executive bodies at all levels, and also to representatives of municipal authorities. Since the beginning of the fire season, the space monitoring revealed more than 240,000 wildfires, which represented a real threat to human settlements. Timely transmission of the information on their locations and timely taking of measures allowed to prevent the advancing fire to settlements and objects of infrastructure. In 2020, the Emercom of Russia developed a mobile application, Thermal Points, which allows simultaneously bring information about the fire to the territorial bodies of the Emercom of Russia and the owners of territories. This year, it is planned to introduce artificial intelligence tools for image analysis to process the constantly growing database of orthophotoplanes and satellite images. This will allow auto detect objects and the emergency zone. At the beginning of the inundation season, the Emercom and the Federal Service of Hydrometeorology carry out the space monitoring for formation of the freezing out of rivers. Thus, the river sections that are exposed to emergency situations, such as ice jams during the spring floods, can be found. These sections are included in the plans of measures to weaken the ice before floods. This contributes to the most effective use of the financial means and good results. Daily space monitoring of the floods on the Russian territory allows to receive the operative information on the situation in emergency areas, ice jams, flood scale objects that are exposed to the flood, destructions of bridges and highways. The received information is used by the authorities during the assessment of situations, forecast of the potential development, and taking decision that allows to avoid the consequence of the financial losses and victims. Areas where flood events they are predicted, Emercom of Russia use unmanned aircraft systems. Specialists in the use of UAS as part of the operational groups of the Emercom of Russia are sent to the zone of possible emergency situations to conduct aerial photography. Based on this data, we make orthophotoplans and digital elevation models, which are used to calculate the consequence of possible emergencies. Based on this, on the results of simulation, a set of preventive measures is carried out. To process aerial photography materials has been deployed a portal. Photos taken by the UAS and sent to the portal via the internet or departmental network are stitched into the orthophotoplane and placed in the geoinformational system. The process of modeling possible flood zones is based on the terrain. It can be made with different water levels parameters. Dear colleagues, thank you for your attention. I'm ready to ask your questions. Thank you.
Okay, thank you. So we have time for some questions. Dear colleagues, do you have the questions? Okay, thank you again. So, and we'll move to the another presentation, which will be given by Dr. Sunanda from Indian National Center for Ocean Information Services. Dr. Sunanda has the research interest in the plate tectonics, earthquakes, and Tsunamis and Disaster Management. She was awarded by National Geoscience Award in 2010 from the Ministry of Mines, Government of India, for contribution towards the National Tsunami Early Warning System. Okay, please.
Good evening to all the eminent scientists here. And thank you, Embassy of India in Russia, giving me this opportunity to talk as part of this excellent webinar on the disaster management technologies. I'm going to talk about the tsunami warning system for disaster risk reduction. What are the infrastructures required? I'll give a brief introduction about what's the difference between the normal wave and the tsunami, a few major historical tsunamis, and what is the threat posed by India for that, and how do we monitor tsunami warning center, tsunami early warning center at the Indian National Center for Ocean Information Services, where I work, and what are the limitations currently we are facing, and what are the new technologies we are looking for to overcome these limitations. And apologies in advance if it looks too basic in the beginning, but I just wanted to start with like what we are looking at. So this is you might be already aware, like 1 in every 3 countries is prone to 1 or more oceanic hazards, like approximately 2.4 billion people, which is about 40% of the world's population, live within 100 kilometers of the coast. So most of the coastal areas are like low-lying and vulnerable to oceanic disasters such as tsunami and the storm surge and the sea level rise. So if we take Indian Ocean itself, like we have around 40 countries. Unfortunately, most of them are developing countries. The 2004 tsunami destructed 14 countries in this Indian Ocean region, and India was one of the most worst hit country after the Indonesia and the Thailand. So what is this tsunami? This tsunami is a series of catastrophic waves, generally generated by the displacement of large volume of water. The major reasons are undersea, are the near coast earthquakes, are near coast are submarine landslides, or flank collapse due to the volcanic eruption and meteorite impact. Though these are all the cases, you see here in this chart, the most common reason for the tsunami generation is the earthquakes. Like 81% of the tsunamis are caused by undersea earthquakes. So what's the difference between the normal wave and this tsunami wave? Is the tsunami waves are long period waves with the length of minutes to hours, and they travel at the speed of 500 to 1,000 kilometers in the open ocean without losing the energy. But when it reaches the shore, its height increases in tens of meters, and it causes the enormous destruction. And annually, there's several thousands of earthquakes of the magnitude less than 4 occur around the world. But we can feel them if the earthquake magnitude is more than 4 usually. So the tsunami-genic earthquakes are usually magnitude greater than 6.5. That's the threshold what we are looking at right now. And they occur approximately around like 20 per year. So as I said, 81% of the tsunamis were caused by the earthquakes. I would like to emphasize that are like not all big earthquakes greater than 6.5 generate the tsunamis. The earthquakes must displace a sea floor vertically in order to generate this tsunami. And such major earthquakes occur usually in subduction zones. As you see here, these are the subduction zones in this map. So mostly like in Pacific Ocean is the most prone to these tsunamis. Mostly 70% of the tsunamis occur in the Pacific Ocean, and 6% of these occur in the Indian Ocean. This is like just a few examples of the major tsunamis around the world and their travel times, just to let you know and have a glimpse on like how much response time we would be left with if same magnitude tsunamigenic earthquakes occur anywhere in the world. This December 2004 tsunami, which had a great impact in the Indian Ocean region, reached Indonesia within 15 minutes with a wave heights of 30 meters. It covered whole Indian Ocean within 11 hours. The other is the famous Lisbon earthquake, which caused multiple disasters, and this is also like reached the nearest coast within 20 minutes with the wave heights of 6 to 12 meters. The next one is the 1960s Chile, the largest earthquake ever experienced, and it had impact even in the Hawaii Islands. It reached the Japan with the wave heights more than 5 meters, and the Chile coast was the worst devastated within 15 minutes. The last example is the Alaska earthquake of magnitude 9.2, which had wave heights of 62 meters at the nearest coast and reached several countries in the southern tip, including the New Zealand. So this is how how fast the tsunami wave travel and how they don't lose energy, even like causing the destruction after several hours of their generation. And in this context, like in Indian Ocean region, we have two subduction zones. This is the Sumatra Andaman subduction zone, and this is the source of the 2004 tsunami. And there's another zone which is the Makran subduction zone in the northern Arabian Sea near to the southern Iran and the Pakistan. So the risk from these zones is analyzed, and we found that if any earthquake occurs in the Makran subduction zone, it takes 2 to 3 hours to reach the nearest Indian coast. That's here. And if we take the Sumatra subduction zone, it takes 20 to 30 minutes to reach this region in Andaman Nicobar Islands, and 2 to 3 hours to reach the Indian mainland. So as you can observe here, the tsunamis are not like any other natural disasters. They give us very less response time, and it is extremely difficult to evacuate the whole Indian coast, which is 7,500 kilometers, like within these 2-3 hours lead time also. And especially if we take the Andaman Nicobar Islands, where they are left with only 20 to 30 minutes. So in order to detect quickly any such tsunamigenic earthquake tsunami, warning system requires a dense observation network with the seismic stations for early detection of the earthquake and the sea level equipment for the confirmation of the tsunami generation. So in India, we have 17 seismic stations installed as part of the tsunami observation network, and we do receive several stations from National Center for the Seismology and from international stations, which are around 400 stations. And this will give us a quick estimation of the earthquake location and the magnitude. But as I said earlier, not all earthquakes generate tsunami. Even if the earthquake is like large magnitude, if its vertical displacement is not large enough to move the whole water column, then it may not generate a tsunami. So in such cases, what we need is a confirmation from the tsunami, whether the tsunami has been triggered or not. So for that we need a sea level observation network, such as the tide gauges or the tsunami buoys. We have 36 such tide gauge stations and 7 tsunami buoys in the Bay of Bengal and the Arabian Sea. So we do share this data with the international partners such as IRIS and IOC Sea Level Stations Monitoring Facility and NDBC. And we receive similarly from other international stations. So after the detection, we issue a bulletin with the tsunami threat information, which consists of estimated tsunami arrival time and the estimated tsunami wave height. So in order to get this in forecast details, we have a pre-computed scenario for the 7.5 magnitude earthquake. And as and when like any earthquake occurs at any of the said 2 subduction zones, we scale up or downscale the magnitude to match with the real magnitude and keep the nearest matching scenario and issue the threat assessment details to the coastal forecast zones. The coastal forecast zones are nothing but like coastal districts in our common language. So to issue those bulletins, we follow a standard operating procedure where we commence our services with a trigger of earthquake magnitude 6.5 in the Indian Ocean or 8 in the other oceans. So as per our SOP, which is uniquely designed, we address both the near source and the far source regions. For example, if any earthquake occurs at the Samudra subduction zone, the Andaman and Nicobar Islands will be very near to the subduction zone. So they will be the first areas would be impacted. So in such case, we directly put them under warning if the estimated wave height is greater than 2 meters. But in case of the Indian mainland, which could be considered like far source, we wait for the confirmation from the tsunami generation from the sea level sensors, those are the tsunami buoys at the nearby tide gauges. And then after the confirmation of the tsunami generation in this location, we upgrade our warning to the Indian mainland. So this usually reduces the false alarms. And there are 3 levels of tsunami threat, like warning, alert, and watch. And when we issue the warning, it means the public must be evacuated from the low-lying areas and the vulnerable coast. If it is alert, the public are evacuated. It's like a marine warning. So we evacuate the people from the beaches and move them to the higher grounds. And if it is like a watch, it's only the heads up message to the disaster management officials to the particular region. So we ask them to be alert, so that maybe that could be upgraded, or maybe they should be watching for the more information from the Tsunami Warning Center. And these are the products we generate at a warning center, like the notification messages with the website link, bulletins with the text information on the threat, and the website, which includes the graphics for easy understanding for the disaster management officials. And we also provide the spatial data if required and requested by the other agencies. And as the Indian Tsunami Warning Center is it not only acts as the nodal agency for the national warnings, we are also responsible for providing bulletins to 25 Indian Ocean rim countries as part of our role as a tsunami service provider in the Indian Ocean region. So nationally, we disseminate this information to several ministries, state disaster management officials, and some important establishments such as nuclear power plants. And this is like in summary. Tsunami warning system is built up by 2 important infrastructures: a system of sensors to detect the tsunami-genic earthquakes, and the tsunamis to monitor the tsunamis at the sea, and a system to quickly communicate to public when any warning is issued. So this slide is a summary of the Indian tsunami warning system. So we are at a warning center receiving the information from the several observation networks. We analyze the data at the various levels to generate the bulletins and disseminate this information to the public. On the other hand, we are also actively organizing and participating in the several tsunami awareness and preparedness workshops and trainings. So this is how we are currently issuing the bulletins to the public. Now I would like to talk about the challenges we are facing at the warning center currently. And as I explained earlier, we do need seismic sea level gauges and the other sensors for monitoring the tsunami, but these sensors come with their own limitations. For example, like this near source broadband sensors will get saturated for the major earthquakes. That means they go out of scale. And so we have to depend on the far field stations for the long period waves to realize actual displacement to calculate the moment magnitude. But and to see whether the seafloor is displaced vertically or horizontally. And there's an example of 2011 Japan tsunami of this, which had an underestimation of the magnitude due to the same reason as I said before. And the sea level sensors such as tsunami buoys are very expensive and they are prone to vandalism. And the tide gauge network is right now very sparse, so that we can detect any tsunami generated at subduction zones. So it takes around, like by one station, it takes less than half an hour. And if it has to be detected by 3 stations, it takes mostly 45 minutes to 1 hour. So that's sparse is the right now the network. And this is another challenge I want to talk about. This is a case of the 2013 earthquake, which was around 200 kilometers away from the coast of the Pakistan, and but it still generated a tsunami. So though it was like a minor tsunami, but the reason was inexplicable. Like after the earthquake, a new island emerged from the sea of the coast of the Pakistan, and this was like a kind of a strange situation for us to deal with. And this is the recent cases of the 2018 of Indonesian tsunamis, the Palu tsunami triggered by the several local landslides in this region, and around 2,100 people were killed. The second tsunami was due to flank collapse of the Anak Krakatau volcano, which caused 430 casualties. The magnitude of this volcanic eruption was, as I say in the Indonesian Warning Center's presentations, it was only the 3.4 local magnitude. So this is not even a criteria for us to look into, not even as an earthquake. So there are like, though there was no regional destruction for these two events, but the waves reached near source regions within a few minutes. Like for Palu case, it was only the 3 minutes. To summarize this, so we have the challenges in both the upstream and the downstream parts of the early warning system. Like in upstream part, we have gaps in the hazard assessments and very high uncertainties for the early warning, and then especially this type of cases, like we call them atypical sources, which are non-seismic. So this is a totally different case where we have to look now. And the downstream part is like the people are still have very less knowledge about the tsunami risk in the coastal communities, and a false sense of security is also a case which we have observed in many cases, including the Palu, like observing the neighbors, how they are reacting if they are not moving, so they feel like they are at a safe location. So this is also now we are giving more emphasis. So to fill these gaps in the upstream part in the beginning, so I would like to tell you what at the Tsunami Early Warning Center of India we have started. We have started installing the GNSS and the strong motion accelerometer sensors in these Andaman Nicobar Islands. And they measure the displacement. So we are currently like establishing this network so that we could receive the data and estimate these seafloor displacements directly and have the information of which kind of displacement has taken and estimate the moment magnitude. And we are using another technique, which is inversion of the sea level data to characterize the tsunami source. So which is to see what extent the rupture has taken and what is the possible source for that kind of a tsunami. So this is an example of 2013 earthquake, which I have explained just before, where we were unaware of where was the source of the tsunami but that generated. So this is the technique we have used to find out the source. And it is like not only important to characterize a tsunami with limited data and with many uncertainties, which has like a tremendous pressure during that very limited time. So this is the reason we have created a pre-computed scenario database for early forecast. But now we have a high performance computing systems. So as part of new research, we are developing realistic data models which can run on real-time model. And this is an example of the 2004 tsunami simulation, which we have run in the real time. And several other major earthquakes we are trying now. And these are a few emerging technologies to improve the tsunami early warning as kind of like a science monitoring. As part of this is the science monitoring under reliable telecommunications cables, smart cables we call them. This is like in collaboration with the industry partners, like the telecommunications providers. We post several sensors on these cables. So this is the emerging technology. Right now, many countries are looking forward. Like considering a vast network of undersea cables around the world, we can improve our observation network tremendously. And to improve the observation capability in Japan after the 2011 tsunami, like the construction of the sea floor cabled network along the Japan Trench is being implemented, and they have the dedicated cable systems for science such as ASNet, DAWNet, and Neptune. And I won't give much, I won't go much deep into the GNSS observation technology advantages, as Dr. Sridevi Jara, she has been working in this area, and she has explained very nicely how it is very useful for Tsunami Early Warning Center and other important applications also. And this is an example of other emerging technologies we are currently looking at. This is like a way to have a low-cost dense network where we'll equip the ships with the GNSS receivers like at any time. At least 15,000 ships will be active on the ocean. So if we equip at least like even only the 10% of the ships, so we can increase our observation network to the 1,500 additional GNSS stations. And this graph is it's a very minor picture I have put there. This is an example of ship Kilomona, which could detect a tsunami in open ocean, which was only 10 centimeters of height. With one ship, we had come up with such a kind of nice result. So we can just imagine with the 1,500 dense GNSS stations, how dense network we could have in the open ocean. And the other way is we have many oil platforms around the world in the open ocean. So these are really very useful for mounting the ocean monitoring sensors, such as shown in this picture. Like in partnership with oil and gas industry, we can achieve ocean monitoring capabilities at a very low cost compared with our own deployment, which usually costs us a vast amount. And the other technologies include satellite altimetry, airborne observations, ionospheric observations, infrasound equipment, and high frequency coastal radars. And keeping this time constraint, I'm not going in detail for all these individual technologies in detail information. I'm just giving a brief about all these things. So so the warning center's major tasks are as an upstream part, so which is like a scientific part. We have to monitor, identify, detect, and provide the forecast tsunami information. And the second most important task is to raise the awareness in tsunami risk communities. So this is a quote which our director, Dr. Srinivas Kumar, usually says, like in his own words. I just wanted to say that, like, even if we have the most advanced technology which can provide 100% accurate forecast, if the people are not aware what to do in case of an emergency, so our total effort will go in vain. So it is equally important to create the awareness and preparedness in the communities at risk, so that we can have the tsunami resilient communities wherever possible. So this is how we concentrate on the both and upstream part equally to build tsunami resilient communities. So this is my last slide. I hope I didn't exceed my time. Thank you very much for your kind attention.
Thank you, ma'am, for very interesting and informative report. I'm sorry, I have to say that the moderator of our session has some technical problems. So I announce the next presentation This is Dr. Kirill Khalatkov. He has his PhD, senior researcher in Schmidt Institute of Physics of the Earth of the Russian Academy of Sciences. Please, Kirill, take a floor.
Can you hear me? Hello?
Yes, we can.
Wonderful. Dear participants, in my short speech, I will reveal some technical details of how...
I'm sorry to interrupt you, but it is something wrong with your presentation. We can't hear, we can't see it correct. Try to load it once again. Yes, this is better.
So
yes. Thank you.
You can see.
Continue, go on. Mm-hmm.
Okay. In this short speech, I will talk about technical details of the Russian node of the Global Space Weather Center for Aviation. So what are Global Space Weather Centers for Aviation? They provide advisories for airmen and ground crew about space weather phenomena that can affect both the aircraft, ground systems, landing system, and so on. The international organization, ICAO, International Civil...
I'm sorry to interrupt you again, but I think we don't see your presentation correct.
What are you saying?
Could you please, we see the slide with the sign risks for civilization, civilian aviation. I'm sorry.
So that is correct.
Yeah, this is the first slide.
Yes, it is.
This is the beginning.
Really, it is.
Then I'm sorry. I'm very sorry.
So there is an international civil aviation organization that regulates weather services for international air navigation. And since 2017, it mandates the provision of space weather advisories for aviation. So what are the risks for aviation? First is the degradation of or even blackout of high frequency communication. Today, many aircraft uses high frequency, say 30 megahertz communication with other aircraft and ground structures, and it is often used as over-the-horizon communication. And in event of in a solar event, if a solar event happens, the ionosphere energizes and the capability of such a communication degrades or even subsides. Same with the loss of precision for the GNSS. GNSS in aviation is used for monitoring of the altitudes, such as RVSM, reduced vertical separation monitoring. It is used for landing aid, such as systems like GLS, and it is also used as a alternative navigation side to side with an inertial system. And third risk is increased radiation dose rate for crew and passengers, especially in polar flights. So what does the Global Center do in a word? It gathers data, pre-processes it, and decides whether it should issue advisories or not. The exact thresholds of all parameters are decided within the special work group that is appointed by the ICAO. Today we have 4 global centers that rotate, and each center has approximately this scheme. So they get data, they process it, they see any threshold breaks, and they issue advisories. So what are data sources? Data sources are almost the same among all global data centers, but in Russia, we use images of the sun in various pictures. We use particle sensors and magnetometers aboard several space vehicles. We use variometers. We use network of ionospheric sounders and a vast network of GNSS receivers. We also utilize planetary geomagnetic indices by Potsdam GFZ, by NOAA, and we have our own K-Moscow index. We also use the SSN solar spot number parameter, and often look for NOAA and LIL model. So all this data is processed simultaneously in real time and is stored in our databases. That's short-term storage databases. We don't accumulate very large amounts of data. We often look for 2 or 3 weeks of data. So the amount of data is about 100 gigabytes per day. And the data that is time series, I mean, particle counters, variometer, attenuation, X-ray radiation, and so on, all this data is stored in a very efficient influx database. It is created as a metric and analytical database for business and system administrators. But it appeared that this database is very suitable for geophysical time series data also. So the data that is not time series, so images and so on, we are storing it as files as everyone else on the planet do. Also we do some sort of processing. For example, we acquire enormous amount of data from GNSS receivers. We acquire pseudo ranges, carrier phases, and the things that are called raw measurements, and we process it to get total electron content. So we don't just store the data, we also do processing. So, and all this processing results and raw data is displayed with an instrument called Grafana to the workstations of duty officers, where they can decide whether they should issue advisories or call the duty scientific worker to solve some ambiguities and issue or not issue the advisory. So this is a very little part of that the duty officer sees during their work. So you might notice sun images, particle counters, and X-ray with thresholds displayed, and so this is the most recent screenshot. You may see that we have AP in the right lower corner of the screenshot. We have planetary index stepping into the threshold area. So it is not yet the space weather phenomena that should be translated to the airman yet, but this is a situation that should draw attention. So this is how it works. So that wrap up, we realize data harmonization with separate simple mechanisms, and it allows us to make a maintainable way to manage this large amount of non-uniform data. the exact system design allows the duty officers and duty scientists to review the retrospective data and to make further decisions with that features in mind. And it allows deep analysis of the events that have already occurred some time ago. Additionally, we are very happy with the open source project in FASc that manages it's very good solution. It appeared to be good solution for geophysical data streams for short-term storage. It's not for long-term storage, but short-term storage. And it's very stable, it's very fast, and it was a very good solution. And also the most data-intensive task, the processing of GNSS measurements, are also performed with help of the FASc, and also with our proprietary code that we developed with specialists from Roshydromet. Well, thank you. This was my short speech about the Global Space Weather Center. I'm open for question.
Okay, thank you. Any questions? I apologize for some interruption of my internet connection. So no questions. Okay, let's go.
Yes.
Is it possible to develop such kind of an real-time monitoring for the weather station on the Earth system? Because you talk on the space weather monitoring. Is it possible to have such kind of system can be deployed on the Earth, especially on the surfaces?
I mean, I got the question about whether you can deploy the system, but where do you want to deploy it?
Yeah, they'll be using on the land system, like land meteorological. They use the automatic weather stations.
Oh yes, the same concept. I believe the same concept could be used to gather, pre-process, and present the real-time operative data of whatever physical parameter you may imagine, hydrological or geotectonical, and whatever. The key for this. For the use of this concept is how exactly do you want to work with the presentation. So you can get rapid images, rapid graphs. You may also have automation that will alert you that some of the parameter exceeds some threshold. But the key is the rules that your duty officers will react to this. So if there is a long-term opinion of how the exact geophysical parameter should be acting within the specific thresholds, so then there is a possibility to build a reaction system that will help emergency services and so on. So without this strict understanding of the numbers that would trigger the actions, I think that would be just a shiny graph or shiny image.
Thank you very much.
Thank you.
Okay. Any questions? No. Okay. Let's proceed. I see that Professor Soloviev Ghosh is ready for talk. Okay, Professor of Indian Institute of Technology will give a talk. Extreme precipitation and flood in a changing climate and their forecasts. Please, Professor. Please switch on your microphone.
Can you hear me?
Yeah.
Yes. Okay. Sorry about that. Thank you, and thank you for giving me the opportunity for talking about extreme precipitation and flood in a changing climate. So rather than going into much of introduction, I'm directly going into the topic. So if you're talking about extreme precipitation, why are you so much concerned about extreme precipitation, specifically in a changing climate? This is because we know, as per the classical thermodynamics, with per degree centigrade warming, the water vapor carrying capacity of the atmosphere increases by 7.5%. And such increase is reflected in terms of extreme precipitation. So extreme precipitation is globally increasing at a rate of 7.5% per degree centigrade warming. And this is what is really something of concern. Now, if you are looking at the IPCC Year 6, which was released August, and I was one of the lead author of this IPCC Assessment Report 6, and where it was clearly stated that globally there has been an increase in extreme precipitation. This is about extreme precipitation. And if you look into this, some sort of a global figure, and if you look into the South Asia, you can see this is South Asia. There has been an increase in extreme precipitation. Now, extreme precipitation is a variable which is very difficult to model. I'll come back to that, why it is very difficult to model. But before that, I'd like to mention is that because there is lack of availability of data, lack of evidence, we cannot really attribute very strongly or very confidently to human activities. But there has been an increase in extreme precipitation, that's for sure. And warming is probably one of the reasons. So now let us try to understand why extreme precipitation is very difficult, whereas extreme temperature is not that difficult. So IPCC, again, this is from our chapter for which I was the lead author. So this is one of the facts which we have designed, that if you look into the mean temperature and extreme temperature, you can see the signs are almost same. Everywhere it is increasing and the signs are kind of very similar. But if you look into the mean change in precipitation and extreme change in precipitation, they are entirely different. And that makes it really challenging, because for low precipitation, there will be one kind of change. There is high precipitation, there is another kind of change. And it's very difficult to model this precipitation change. And that makes it really challenging to understand what exactly is happening to precipitation. This is true for climate projections, this is true for weather forecasts, or this is true for any kind of predictions. So that makes it really challenging. Now, so how can we know that what exactly is happening? So I was talking about extreme precipitation is increasing at a rate of 7.5% per degree warming. And this is known as scaling. This specific term is scaling that is used for this thing. Now, how can we really compute the scaling factors, the extreme precipitation scaling factor? So there are different ways to really find out the scaling factors. One of the technique is known as binning technique, where you are actually taking care of precipitation and temperature pair, or if you are interested in finding out the scaling for stream flow, you can pick up QT, which is stream flow and temperature pairs, and then do a scatter plot, and then divide the temperature into multiple bins, and then find out if you're going from one bin to another, how much mean change is taking place, and fit a regression line or something, and then get the scaling. So that's one of the way, which is known as binning technique. But for that, we should have quite a number of data points, because we are essentially talking about extremes. The other option is that you can have temperature and you can have precipitation. So this is known as quantile regression. In quantile regression, what you can do is that, so it's very similar. So I think before that, I'll just give you a simple example. Let's say if you have some balance and some like customer lifetime value, or maybe if you're considering the salary and the expenditure. So the people who have the same salary, their expenditure may be different. There are a few people who spend a lot, there are a few people who doesn't spend. So, and we are only interested in the extremes. In the same way, for the same temperature, you can have extreme precipitation, you may not really result into extreme precipitation. So we are really interested for a given temperature, what is the value of extreme precipitation? So for that, what we need to do is that we need to go for a quantile regression. And let's say if you are really interested in extremes, we need to go for 95th quantile regression or 99th quantile regression to understand how, and to understand the slope, and to understand that how 99 percentile precipitation is changing with temperature. So that was the method that is used. So these are the two methods which can be used. So what we tried to do, this one we published in Geophysical Research Letter very recently with one of my master student who is now at PhD at Max Planck. So what we did here is that we have the daily precipitation extremes over the Asian region. We are actually focusing on those regions where the streamflow data is available from a global portal. So that we have made sure. So because the data should be available from the same source. So we have taken three regions. One is region 3, one is region 2, you can see, and this is region 1. Region 1 is more on the tropical region. And when we computed the daily precipitation extremes, the scaling of daily precipitation extremes, so these are essentially the daily precipitation extremes value. And you can see at a subtropical region, the quantiles are slightly lower compared to the tropical region, which is quite expected. But if you are considering the scaling, you can see that in the subtropical region, if you are considering these regions, you can see that the scaling is positive. It's around 5 to 7%. But if you're coming to tropical region, it's very interesting that it has having a negative scaling. So there are specific reasons which I'll come back. But it is important that we have a negative scaling. But if you jump to streamflow temperature sensitivity, you will find that everywhere there is a positive scaling which is very close to 7.5%, and sometimes they are higher also. So streamflow is increasing everywhere. With temperature, extreme streamflow is increasing everywhere, but daily precipitation is not really showing. I'm talking about only extremes. Now, if you carefully look into this figure, the tropical region has a very high temperature, which is around more than 25 or 22. So on the extreme days, we have found the temperature, it is always more around 25 to 30. But in the subtropical regions, the temperature is quite low on these extreme precipitation days. So we further did some analysis. We tried to find out how the extreme precipitation is varying with temperature. Now, if you look into this figure, this is the daily precipitation extreme intensity, and this is the temperature. You can see the curves. It keeps on increasing, and then at a value of 22 degrees centigrade, 22, 23 degrees centigrade, it starts dropping. There is a dropping of extreme precipitation curve. It is happening for daily precipitation for all the three regions. This is region 1, region 2, and region 3. But if you remember, in the tropical region, the temperature is high. It's always greater than 22. So you are getting a negative scaling because there is a drop. We are actually this side of the curve, because of which we are getting a dropping. But this side, there is an increase, and because of which you are getting a positive scaling over the extratropical region. Now if you look into the 3-hourly extreme, so what we then did is that we went to 3-hourly extreme precipitation rather than talking about daily extreme precipitation. And for that, we have used the satellite data which is available, the TRMM data. And in the 3-hourly extreme precipitation, if you consider region 1 is more or less increasing, region 2, there is a drop after 25, 26 degrees centigrade, and region 3 is continuously increasing. So 3-hourly extreme precipitation is not getting affected. So I'll come to streamflow, but before that, I'd like to explain why is it happening. Because let's say for a whole day, if the temperature is quite high, your water vapor carrying capacity is high. So to saturate the air with the moisture for the whole day, you need a lot of moisture. And sometimes this lot of moisture may not be available, so there is a drop at a higher temperature. But for 3-hourly, for a shorter duration, if you need to keep the atmosphere saturated to result into extreme precipitation, that's available. And so 3-hourly extreme precipitation doesn't see a much of a drop in the scaling curve, but daily extreme precipitation actually sees a drop. Now, if you are looking at streamflow, they are not. So whenever we have picked up a streamflow, whatever available data is there, it's more or less actually following sort of 3-hourly extreme precipitation, or it keeps on increasing. So if you're considering, let's say, region 1, if you consider daily extreme precipitation and daily extreme streamflow, there is a diametric kind of patterns, and we're trying to understand why is it happening. So then we try to look into what exactly is happening for small catchments versus the large catchments. So in the small catchments, which is less than 1,000 square kilometer, and large catchments we are considered greater than 1,000 square kilometer. Now, what we are finding in a small catchments, your three-hourly extreme precipitation results into a huge stream flow, because for smaller catchments, it results into flash flood. Like urban catchments, this results into flash flood immediately after the rainfall. And so for smaller catchments, these small short duration rainfalls are really very, very important, and that shows a scaling. But when the area is greater than 1,000 square kilometer for larger catchments, then the 3-hourly is not important, the daily is important. So when you plot the flow temperature scaling rates, the percentage increase versus the area, catchment area, you'll find that for smaller catchment area, your scaling is quite high for stream flow. But for for the higher catchment areas, the scaling value is low. So it says for smaller catchments, the shorter duration precipitation is very important, and that results into flash flood, and sometimes that has a very high scaling factor. So we have to be very, very careful about the small catchments, specifically the urban catchments. So now I'll go back a little bit into 2006, when there was a very famous paper which came in Science by Goswami et al., where it was mentioned that, you know, if you're looking into the extreme precipitation over India, there has been a significant increase in extreme precipitation, specifically over the central India. So we looked into this matter a little more, and we tried to understand what exactly is happening to the spatial variability. That means how the rainfall, extreme precipitation pattern of one region is becoming more and more different from other region. So that means increase in spatial variability. This one we published in Nature Climate Change in 2012. And we showed that it's not only the extreme precipitation amount, it's spatial variability. That means the similarity of extreme precipitation is getting reduced. So this similarity between two stations are actually increasing over India. And such an increase of extreme precipitation could be because of the local factors, because for a global factors, normally we'll expect the spatial pattern will be very similar. If it is increasing, that means local factors are playing a major role. And one such local factor is urbanization. So there are multiple local factors like land use, land cover change, water management, aerosols, but we are just focusing on the urbanization, this one for this today's talk. So how can urbanization really affect the extreme precipitation? One thing is that, of course, urban regions are warm. So because of urban heating, it can hold more moisture, resulting more rainfall. The second one is the urban heat island effect. So there is a temperature difference between urban and non-urban regions, and that results into wind circulation and more rainfall. The third one is the pollution. The aerosol at the cloud condensation nuclei, that results into more rainfall. And the fourth one, which is not at all touched, or not very well touched, which is urban structures. In an urban region, there are buildings, there are roads, there are slum areas, and all of them really contribute to the extreme precipitation. For example, let's say if you consider the air is moving, there is no urban region, it has the entire area to flow. The air with moisture is flowing. But let's say if you're considering the condition where you have two rows of building and in between a road, then air cannot really flow through building. Of course it can flow, but it cannot flow with its high velocity. So it is kind of forced to flow through the road in between the buildings. That results into decrease in the cross-section area and increase in instabilities, increase in velocities, instabilities, and wake diffusion, and that results into more instabilities and generation of pockets of rainfall. So we wanted to test this. So we wanted to test this with a regional model. So we have used the weather research and forecasting model, which is a regional model which have run at we have run it for the Mumbai region, but we have considered a large scale forcing at 27 kilometer, then 9 kilometer, and then 3 kilometer, and over Mumbai we have considered 1 kilometer resolution. So we have considered three cases. One is no urban canopy. So it's just the radiation which is considered, the radiation effect is being considered. The second one is that in the urban region, we have considered entire urban region is just a single layer of building. That's it. No road, nothing. This is single layer urban canopy model. Then we have considered the multi-layer urban canopy model, where we are considering buildings, road in between, we are allowing drag and wake diffusions and everything. So and also the radiation impact. So there is a change in the urban planetary layer, boundary layer. Now, when we have started running it with 4 extreme events that took place in 2014. So we have considered the multiple station data which are available for Mumbai. And if you look into the observed rainfall, it is 96.30. Let us look into the first event. And if you're considering no urban canopy, if you do not consider urban canopy, it is giving only 64.48 average rainfall. If you're considering single layer, all are building, it's increased little bit, 68. But if you are considering multi-layer urban canopy, it is very close to 96.30. So multi-layer urban canopy is actually capturing the rainfall. Now let us look into the spatial variability within the urban region. Those who stay in the urban region, they probably know that if, let's say, if you are driving in an urban region from one part of the city to another part of the city, you'll get a lot of spatial variability. Like in some pockets, you'll get heavy rainfall, some pockets there is no rainfall, and so on and so forth. So what is the reason behind this spatial variability? What we are finding is that if you carefully look into this figure, you can see the blue line. You can see this blue line. Blue line represents the observation that represents the spatial variations across the stations. The PDF of spatial variations, PDF representing spatial variations. Now, if you are using no urban canopy model, this is the red, which shows a very low spatial variability. If you use single layer urban canopy model, it is showing a little bit of shift, but no increase in the spatial variations. If you are using multi-layer urban canopy model, you can see it's very closely matching with the observations, and it shows a higher spatial variability. So I'll quickly tell you what exactly is happening. In the urban region, let's say if you have, I've already mentioned that there are certain pockets which are being generated because of the building, roads, and etc. And in those small regions, what happens? More rainfall really takes place. These are essentially the major pockets of rainfall. And if such pockets are there at multiple places in the city, it will try to have a higher tail and more spatial variability. So impacts of urbanization will result into an increase in spatial variability of rainfall, which you can see from these curves. The multi-layer urban canopy model with green curves has a higher spatial variability. And if you look into the observed data, you will find that if you go beyond 10 kilometers, if there is a difference, distance between the station is higher than 10 kilometers, for more than 50% of the stations, the correlation between them, it gets decorrelated. That means the correlation becomes less than the statistically significant correlation coefficient. And that's why for urban region, we need more and more number of stations. And this is the science behind it. Now, what we tried to do is that I'll just give you a slight overview about this. So, in 2015 in Chennai, there was a huge flood. And after that flood, during that flood, a lot of people died. I think around 500 people died, and there was a huge loss. And after that, the principal scientific advisor to the government of India, then Dr. Chidambaram, came to IIT Bombay, and he met many of us. And then he requested me to lead a project where 8 institutions were participating, and there were 30 scientists who were involved in developing India's first real-time end-to-end urban flood forecasting system. Before that, there was no existence of end-to-end urban flood forecasting system for the entire city. So I was quite fortunate to have an excellent scientist who really worked for this problem. So this is a kind of challenging problem, because if you're considering the urban region, the urban rainfall are quite challenging. The urban regions are building roads, drainage, we need fine resolution, DEM, etc. We have a coastal city. Chennai is a coastal city, so there is a tidal forcing. There is a storm surge from Bay of Bengal. In the upstream, there is a Chennai watershed, which has its own characteristics. There is a reservoir. So there are a lot of things. It's a kind of a quite complex thing. So if you're considering the framework, there are multiple components which are used, like rainfall components. So what we did, we have considered from National Center for Medium Range Weather Forecast, we have taken the rainfall, the rainfall forecast, and then we did statistical downscaling with quantile regression to get for next 3 days forecasting. And also we did little bit of radar data assimilation for nowcasting. We have considered the coastal conditions. This was done by in COIS. So the tidal and bathymetry data was used, and tide and surge forecasts were made. The hydrology condition was taken care by IIT Madras. So where upstream hydrology, upstream of the Chennai upstream watershed has been taken care, and there are a lot of stations, the water gas stations which were being installed, the sensors have been installed to understand. And then finally, the flood modeling for the entire city, which was done by one of my colleagues, Professor Shubhankar Karmakar. He developed the entire flood model at a very fine 2-meter resolution for the entire city, and which considered different terrain condition, the leader survey, leader data, which was done by Anna University, and finally we went for inundation mapping. So for the precipitation, we have taken the 44 ensembles which are available from National Center for Medium Range Weather Forecast. We have considered the station level data, and we did quantile regression. And this is the performance of flood model. So we have to mention, I need to mention that there was no flood data which are properly available. So immediately after the 2015 flood, the IIT Madras and NCCR, National Center for Coastal Research, their team went everywhere in the Chennai city, and they did a lot of crowdsourcing. They take the water, water mark at different walls, and based on that, they have got a few flood points. And based on the flood points, we have got the observed flood inundation. And then we ran the model, which was ran at a very fine resolution, so it takes a long time. And we found that for 80% of the cases, the error is within 1 meter. And disaster mitigation agencies were quite happy with this kind of, less than 1 meter flood in error. So we went with that. But there was a challenge. Now we have to run the flood model at a very fine resolution. It takes a long time. And we really do not want that, by the time the flood model will give forecast, the flood will start. So what we tried to do is that, to be on safe side, we tried to create a flood data bank. So we have considered different return period levels for the rainfall, different storm duration, different past condition, different kite condition. We have considered 800 cases. With 800 simulations we have made ready, so that as soon as the forecast we are getting, we just check with the flood data bank and find out which is the closest scenario. And for that, immediately we are generating the results. So it goes like this: every day 3 p.m. So everything is automated. We have automated everything. And this is now operational by National Center for Coastal Research. So National Center of Coastal Research is now maintaining it. So at 3 p.m. Indian Standard Time, the meteorological forecasts are released from NCMRWF. Immediately in 2 hours, all the data has been being generated. The tide forecasts come from INCOIS. The upstream hydrological forecasts are being ready automatically, and the past condition is being generated. And at 5 p.m. it's ready to check at the data bank, and immediately it gives the flood inundation from the data bank. What will be the flood inundation for day 1? What will be the flood inundation for day 2? What is the flood inundation for day 3?
2 minutes.
So So let's say this is the forecasted rainfall, and for different percentile, for different quantile, it will look for the lookup table and find out the flood inundation level. Now let's say if it shows a flood inundation, so we need updates every 6 hours or every 12 hours and so on. We do not really want the real-time system to start if there is no flood forecast. If there is no chance of forecasting flood, then we are not really interested in the flood model to really run and then losing the CPU time or losing the computing time. So what we are checking, if 95th and 99th percentile says that there will be a flood inundation for next 3 days, then we'll consider from NCMRWF the deterministic forecast, which updates every 6 hours. And if it is needed, we are doing a radar data assimilation, and finally it is being run to get the updates at every 6 hours. If there is no flood inundation for the next 3 days, then we will not really running the real-time simulations. And typically a dashboard looks like this. So let's say this is the initial condition day. These are the forecast day. 80th percentile says no flood, 85 says no flood, 90th says these are the maps. And in fact, if you want, you can click on the maps and you can go even into the building level. So we have made sure that even at a building level, we'll show the 3D visualization of which I'm not showing here. Of course, there is a video, but I'm not showing because of the time constraint. But even at a building level, what is the inundation level? How many floors? What part of the floor will be inundated, and so on and so forth. And based on that, evacuation decisions can be made. So that was something which has been done in a record time of 1.5 years. So for summary, of course, I'm just quickly saying that, yes, it's not just global change, global and local changing factors, both needs to be considered in extreme rainfall and flooding patterns. And based on that, we need to come up with a better forecasting system with some out of the box thinking, because a routine thing may take a long time, and we have to think of a speedy forecasting system. Thank you for your attention. Thanks.
Thank you, Professor. So there are no time for questions. And the last presentation will be given by Professor Varun Dutt from Indian Institute of Technology, Mandi. He is an expert in the landslide risk assessment and management. The talk is low-cost landslide monitoring and warning through predictive analysis. Please.
Yes, thank you, Victor. And I think you should be able to see my slides and you should be able to hear me.
Yes.
Thank you. Okay, so good morning, good afternoon, and good evening to people around the world, and good morning as well if some of you are in that zone. So we'll be presenting today low-cost landslide monitoring and warning. This is something which we have developed at IIT Mandi. This is the IIT of the north in the Himalayan mountains. This is a work with taken over with. I'm working as an associate professor with my colleague KV Uday, who is a civil engineer at the School of Engineering. So this work has also been funded by district and state and national disaster management authorities in particularly in Kinnor, in Mandi, and in Kanga. So just to motivate the problem quickly, landslides, of course, is a big problem. This happens to be the Kotropy landslide, which you may have heard in news in 2017, took away 46 lives. It's actually the largest landslide in my district here in Himachal Pradesh, Mandi. And unfortunately, India happens to be the global landslide capital of the world with more than 130 million USD of losses and also 200 deaths per year on average. So the idea was to, 2017, my colleague and I got together. We said, what can we do? And we found that there were no warning, monitoring, low-cost technologies available. So we thought of developing a system which could monitor, warn, and to do the next level, maybe predict movements ahead of time. So there are two objectives of my talk. One is to do with how we came up with a low-cost landslide monitoring system, which can be deployed on hills for mass deployed on hills, and we can collect data in the cloud and do some analytics. And the second part of my work is going to be on some statistical and deep learning algorithms which we have developed on data collected from the system and elsewhere. So coming to the first one, which is the low-cost landslide monitoring system, just to motivate, there are a bunch of technologies available. We did a little review and we found that GPS, LIDAR, and satellite-based technologies are available, but they have issues related to resolution, cost, and some of these problems. So the idea was, how can we make a technology which could be applicable for developing countries, particularly India, which do not have funds in plenty to spend on disaster management. So here we actually came up with a contribution, and this is actually a landslide early warning system, and it has three parts to it. One part of it is a bunch of sensors which go into the soil for monitoring. Another part of it is the predicting and warning parts. So I'll come to it one by one. So for the, this looks like the architecture of the system. Of course, this flowchart from computer science looks great, but just to make you aware, the system actually has a bunch of sensors and it sleeps all the time, most of the time. We motivated it from the Hindu mythology, Kumbh. And actually, whenever there is soil movement or there is significant event like rain, it wakes up and it starts collecting data. So it's actually a low-powered system and it runs on solar power. And it basically, because of this, we were able to reduce the cost down. Of course, we did some innovations in bootloaders and of the microcontroller and others. So here we have actually some parts to the system. One is the data acquisition part, where we are collecting data for weather parameters, rain particularly, as well as soil parameters. And we are then processing this data in a cloud database. Processing involves doing thresholding, checking the values of which we have got from the sensors, cleaning, and then even machine learning, and then doing some kind of prediction and warning ahead in time. So these are the kind of sensors we have in the system. So the main core sensor is an accelerometer, which is deployed in the soil for measuring soil accelerations. And this accelerometer can give us velocity profiles as well as displacement profiles. Then we also have a tipping bucket grain gauge, a temperature humidity sensor, barometric pressure sensor, capacitive soil moisture sensor, which measures soil moisture by volume, and an ambient light sensor and a stress sensor. So this is a picture of the landslide monitoring system. As you can see, it's a solar powered system with a rain gauge here. And this box contains a bunch of weather sensors with wires going into the soil, collecting 4 different values of the soil. One is soil movement, soil stress, soil moisture, and soil temperature. So these are the ranges of different values. As you can see, we are in the mountains. So we have perfected the system for negative to positive temperatures. And the accelerometer actually has a gyroscope built in, which can measure very fast rotations as well as large changes in accelerations. So moving ahead, so this is how the schematic looks like. So think of, we have a house here, right in the valley of a mountain, which can be prone to landslides. So we deploy the system right up on the mountain, and then this system connects to the cloud using GSM technology if it's available. If nothing is available to connect to the internet, then we may use technologies like LoRa to take the signal from the system to a place which is having internet. So once the data is sent from the system into the cloud, we do analytics, thresholding, and develop intelligent warnings, which can be triggered on mobile phones, as well as can light up beacons, which are next to houses or roads to alert traffic of impending movements. So this is examples of the system. This is a picture of the microcontroller board. And this is where I started off telling you about the Chotropy landslide. This is a Chetavani pole, basically a warning pole, which is wirelessly connecting 300 meters using LoRa to the system, which is right somewhere here on the slide. And it's warning the traffic that if the lights and hooters go off, do not cross. This is the kind of message we get from the system when there are movements of significant magnitude. The question is, how do we generate alerts? How do we generate actionable warnings? So this is a message trace, SMS message trace from a system deployed in Nainital, Uttarakhand. And as you can see that there are 6 messages received here over a period of 1 hour, and they go from small movements down to moderate movements. So we look at 2 things. We look at the frequency of movements. We look at the intensity of movements. And typically, we use a Z-score to calculate how large the movement is for the intensity. And then combining the 2 together, we generate an actionable alert for the district government, for the society, for the people living there. So recently, we have actually started going deeper into the hills to look at causal factors. So for that purpose, we have deployed subsurface systems, which can go up to 15 to 20 meters inside the soil. This is a deployment where we have done a borehole of about 15 to 20 meters, and then we have perfected this system with a flexible PVC casing. And these points are the sensor nodes, and this system goes in and then allows you to develop a movement profile, subsurface movement profile over time. So this is actually some deployments which we did in Mandi districts of the subsurface system by a drilling rig. These are the set of sensors which go inside the soil. This is how it looks like. And at the end of the day, you get cumulative displacement profiles, which tell you how the soil is moving as a result of different forces acting on it. This data is also visually available on a website, which is public, and this gets logged every 10 minutes. So you get the temperature variables, the weather variables, the rain, as well as the acceleration, force, and soil temperature and moisture. So just to discuss, this is the subsurface system. It is capable of generating warning. It's low cost, and it's actually useful. We have deployed it in a number of locations. The second objective of my talk is to come to a statistical deep learning algorithm on some of the data we have collected from the system, as well as outside from other systems which were there. So just to motivate, we are talking about displacement trajectory over time. It's a time series. So when we talk about time series, the bell rings that we should go to methods which are statistical in nature. So some of the methods which are statistical in nature are ARIMA, which are autoregressive, seasonal autoregressive, but there are some other methods which are deep learning, which are long short-term memory, and some other approaches which are based on nearest neighbor and decision trees. So looking at the literature, we got some data from a lab in Defense Research Development Organization, which had deployed a very expensive system for capturing soil movements using inclinometers in this Chamoli, Uttarakhand, Badrinath area. It's right here in India. And basically, this consists of an inclinometer, which is put subsurface, and it gives you the tilt angle of the inclinometer over a period of time. So what we did was they had 5 boreholes, and for each borehole, we tried to analyze the data of the tilt angle over weeks, and we tried to identify those sensors which had the maximum movement shown per borehole. And we came up with 5 different time series for the 5 different boreholes. So we started looking at all the different methods available, moving average, the lazy methods, nearest neighbor, and information gain, decision tree methods, as well as deep learning methods. This is a contribution which was recently published in a high impact journal. This is a bidirectional stacked LSTM model. Of course, I'm not going to go into detail because of time, but the idea is that this model has a bidirectional LSTM feeding into a stacked LSTM and then generating predictions. So how do we generate predictions? So we create movement packets for models. These movement packets look like this. Basically the movement, the packet number, the borehole, and the depth of the node in the borehole. And these movement packets could be shuffled or not shuffled. And these packets basically can go with some look back period, which is like, let's say 3 time periods back or n time period back. And then these packets are put in, and their predicted value is compared to the actual value. So this kind of methodology is followed for calibrating different models. We also tried calibrating different parameters for different models, like for k nearest neighbor approaches, the k value, similarly for decision tree and some other algorithms. So these are traditional algorithms which are available in machine learning literature. We've also looked at certain parameters, hyperparameters of LSTM models. Here, the BS LSTM has parameters of the bidirectional model, the stack model, including the dense layer. So, and also the statistical models, which have autoregressive, differencing, and moving average terms, both in seasonal and non-seasonal. So looking at the results, when we compare them, of course, these are training results across different boreholes, the root mean square error in the degree angle. And you can see that lazy methods seem to perform well, but there are closely followed by deeper methods. But when we started testing this on newer data sets, we found that the deep learning methods seem to perform better than the statistical approaches, at least in our data set. So these are the movement trajectory profiles from the statistical model, which is the second best model. As you can see, the orange curves are basically the real movements, and the dotted lines are the predictions, and they are fairly accurate. And this is actually the movement profiles and the predictions from the BS-LSTM model, which again seems to perform very well. So we've actually recently deployed a system in the heritage railway track from Khalkha to Shimla at a place called Dharampur. And this system actually started logging values, and we took the BS-LSTM model and we said, how well will it predict this movement? So just to show you, this is actually movement recorded over the last 1 year, the orange trajectory, and the model is actually very accurately able to predict soil movements with almost close to 0 root mean square error. These are some of the pictures of the system deployments where we have deployed the system. So just to discuss this part, we have found that soil movements can be predicted by deep learning methods, particularly recurrent models like LSTMs and an ensemble of LSTM models. Also statistical models and some other models perform reasonably well. So just to summarize, what are the future works in this domain? of course, we are now moving to the hourly level, gathering and trying to predict movements at the hourly scale. We are also planning to expand deployments across different districts in Mandi, including Kangra and Kinnaur in Himachal Pradesh. And of course, we have tried some of these algorithms, but most of the data sets have been univariate. Now the emphasis is moving on if we can combine weather parameters with soil movements and other such parameters to make these models multivariate and multi-value. That's about it. These are our contact information, and thank you for your patience.
Thank you, Professor. Any questions? You may start from these questions for this presentation, and because it is a final speech scheduled today, and we may start the panel discussion. The presentation.
Victor, can I ask a question? Yeah, so thank you. And my question to the current speaker only. So, hi, Professor Barun. I just went through your talk, and I just wanted to understand whether you are actually evaluating the landslide or the soil stability.
Yeah, that's a very good question. Can I go ahead and answer, Victor?
Yeah, this is Manas here. You can answer.
Yeah. So, can you hear me, Manas?
Yeah, I can.
Yeah. So basically, the question is very good. So recently, what we've been doing is we are focusing on the soil stability part with my colleague, and we are focusing on monitoring and predicting soil movements. And some of these soil movements may have signatures, particularly related to the frequency and the intensity of movements, which may tantamount to landslides. So the idea is to go from soil movement prediction to landslide prediction, so long we get several such signatures where we can actually learn over such signatures. So we have some landslide experiences in our data set, but they are not sufficient to say that every soil movement would be a slide. But you find that there are a lot of small soil movements which happen on a day-to-day basis at landslide sites, but they don't need to landslides. So that's kind of the higher level goal in a few years, hoping to have more landslides, of course, safe landslides, to train such models at the landslide scale. Yeah.
Okay. Thank you. And the reason why I asked that question is just to ensure that when you talk about landslide, usually the geology also plays a major role. And I believe currently in your monitoring, that is not being captured. So I'm not sure, but that's what I got a feel. That's why I asked this question. Thank you so much.
Yeah, so just to answer the second question, sir, that's very good. We are actually, the work which I presented doesn't include geology, but recently we have actually done two things. We are combining geology, lithology, as well as satellite-based, INSAR-based analysis and developing better models. This, of course, is evolving work. We recently submitted it to a journal. And when it comes out, of course, I'll be making my next presentation, including those works. But your thought is right there, that to predict movements, we need other multi attributes, which are of the geology, lithology, and other kinds. Thank you.
Thank you so much.
Okay, the next question I see the right hand, Dr. Perumal.
Yeah, thank you, Varun. I think the same question Professor Manas asked. In fact, you wanted to understand basically the slip surfaces when you are going for the warning system. You do not know exactly the interface between the soil cover and whatever the bedrock. So unless until you have such kind of information, I think the early warning system, in which direction it will move, that will be very, there will be a lot of uncertainty will be there on that aspect.
Yeah, so just to answer that question, how we are reducing the uncertainty is by doing ground penetrating radar surveys or resistivity surveys of that area first, and then looking at the potential points where such deployments can take place. So the deployment, subsurface deployment I showed, I didn't show you results of resistivity and ground penetrating radar, but that's one way of doing it. There's another way of doing it is that when you deploy these sensors, you find that there is an interesting, at least subsurface sensors. If these sensors, if the line of sensors intersects the failure plane, what happens is that a set of sensors which are close to the failure plane report more movement, and the sensors above report more movement, of course, if the whole mass moves, compared to sensors below the failure plane. So this intersection of the failure plane with the sensor chain of sensors actually allows us to approximate the location or the depth of the failure plane. So this system can also be used for that purpose. We have actually done this for the Chamoli sensor deployments, which we didn't do, but we found that the slip surfaces are likely to close to the locations where the sensors are showing maximum movement. That's the slip surface. Thank you.
Thank you, Arun. Dr. Victor, if you allow me, can I ask one last question to Subimal?
Yes, please. Yes, please.
Hello.
Yeah, please ask.
Subimal, yeah, I need one clarification. You talked about the spatial distribution of rainfall relating the urban canopy or urban concrete kind of a distribution. This is what you mentioned. But we get variation in the spatial distribution of rain in the Himalayas, but we don't have any kind of an urban colonization. So what is your thought on that? Then you talk about the scaling relationship with the extreme precipitation with the different area set. That's quite logic. But when you compare on the same scaling factor, especially the cloud burst, it generally happens in Himalaya. So how do you relate this? This is the second observations. And the third observation I wanted to know from you, most of the modelings are related to say 50 years or 100 years or less than that using the TI data. So in what way these modeling going to be helpful to predict or say the extreme event is going to happen or some kind of a climate change is going on, some kind of a big threat to the human society. Please comment on this issue.
Well, I think I'll start with the first question, which is talking about the spatial variations. You are quite right, actually. Himalayan region has a very high spatial variability. Of course, urban scale is much smaller compared to the Himalayan scale. But if you look into the Himalayan orography, you can see there are different, mountains. The elevation keeps on changing, right? The elevation changes quite fast. And I mean, in an urban region, what's happening? There are building layers, suddenly road, and again another building layer, again another road, again another slum area. So what happens? That results into, in the generation of certain pockets where a lot of extreme rainfall is happening, and this generation of pocket is because of the sudden generation of instabilities and wake diffusion and so on. At a larger scale, exactly the same thing is happening. I mean, you have very correctly mentioned in the Himalayan region, exactly, because it's not a smooth area. It's an area where the elevation is changing quite fast. And because of that, there are a lot of instabilities which are getting formed, and that results into a lot of pockets of rainfall, heavy rainfall.
That's true. That's like you are relating with the relief rain. Basically, we get all of a sudden relief rain in Himalayas.
Yes, exactly. So that's the thing. So that's I mean, they are quite similar, only the scales are different. And because of that, when you are going for Himalayan region, you have to really go for very fine resolution modeling to have a better, forecast performance. So that's your first question. The second question was related to cloud burst. So cloud burst is an entirely different thing, but I'll just try to say that what exactly does it mean by 7.5%. So I'll just give you a very simple example. Let's say if you have a very thin plastic packet full of water. This example I give it to my students also. So if you put a small hole, the water will take a long time to drain out. And let's say if you want to find out what is happening within 10 seconds, you will find some amount of water. And that will not really give you, so if you take that amount will not represent the water carrying capacity of the entire plastic. But let's say if the entire plastic gets burst and entire water falls down, that water is actually talking about the water carrying capacity. So when I'm talking about 100-year return level or 50-year return level, when you're talking about this kind of heavy rainfall events, we are essentially interested in the extreme event where the entire moisture is falling down as precipitation, and that actually you are measuring. So that's something because of which that follows 7.5%. Now let's say if you're considering the cloud burst means it's not only the saturated, it's a very kind of super saturated condition, and the entire water moisture is actually falling down. So what we'll get, cloudburst is a very, very rare event, but you may get Clausius clapeyron or slightly higher than Clausius clapeyron, which is just because of the super saturation condition. So that's the way we look into the scaling part. And I'm sorry, the third question I didn't get. You're talking about some data, but in between the voice broke and I could not really hear properly. If you please repeat that question.
Yeah, I'm sorry for that. Actually, you are comparing the time series data of instrumental arena, and you are coming up with different models, trying to project that is an extreme event or something like that. So in order to understand the variability of the weather or any kind of an system, you need to have the long time series data. This is what my concern is, that because most of the IPCC climate report, all these things, they take say 50 years or 75 years of data and try to come up with a very big model. So do you guys really consider this, some of the older data sets, say of 1,000 years or 2,000 years, using the geological input?
Well, so there are a few things now. So let's say if you're talking about 2,000 years or 3,000 years of data set, then we are really interested in the paleoclimate. So paleoclimate is altogether a different thing. And when you're talking about Anthropocene, what is exactly is happening over 100, 150 or 200 years, where the irreversible climate change is taking place, that's a different thing. So if you are really interested in understanding this over the last 100 years or last 150 years, when the irreversible climate change is happening, if you're really interested in understanding this impact, then I believe 150 or 200 years data is even more than sufficient. Even last 50 to 100 years data would be sufficient for this kind of climate change analysis. But if you really need to find out if there are irreversible change or not, whether that say changes have really happened earlier or not, then it comes a long-term data set need. And both of them are being considered in a proper way. And the second thing is that, IPCC has different assessments. It's not, IPCC is not really developing any models. Models are developed in the different labs. What IPCC does, IPCC considers the scientific literature, and based on the peer-reviewed scientific literature, IPCC gives an assessment to different changes. So let's say, if I'm saying, if you remember, my first slide was on changes in extreme precipitation. It says that in South Asian region, there is a high confidence that extreme precipitation has increased over the last 50 years. But because of lack of available data, it cannot be directly attributed to, human changes or anthropogenic changes. So this is the way it is mentioned. So there is low confidence statement, medium confidence statement, high confidence statement, depending on literature agreement, disagreement, data availability, and so on. There is a defined methodology which is actually available with IPCC, based on which the assessments are being made.
So there is one question now from Dr. Moredo. Dr. Moredo, kindly go ahead. You've raised your hand. Please switch on your video also, those who are discussing.
Thank you, Subhamal.
Thank you so much. Thank you. It was a very nice question. Thank you.
Yes, I had a question to Dr. Varun regarding what kind of predictors his group used as input to the LSTM model. What was the predictor data set? Or was it just a previous state of sensors?
Yeah, so thank you for this question. So right now we have the models which I presented are using univariate time series, but we are predicting movement where we are taking prior movement of certain hours or weeks in account or days in account. But in addition, we are also taking the depth of the borehole, at what depth it is, and the location of the borehole. But most recently, we have also worked on taking a number of soil geotechnical parameters for soil for machine learning, and these parameters, some of them are measured dynamically from the system, whereas some of them which are say the particle size of the soil, the gravel content in the soil. So my colleague Uday is actually takes the soil sample in the lab and then does tests on these samples. And we have about an inventory of about 30 different parameters, geotechnical, including lithological and other parameters, geological parameters, which we can input into the model. And most recent work has led to developing deep learning models which have these parameters as input. But before we do the input into the model of these parameters, we also try to see the correlation or feature engineering of the parameters with respect to movement. And then we select some top N parameters to input into the models. So this is kind of the answer I would like to give, more holistic. So we are looking at other parameters beyond the movement parameters itself.
Thank you. So these are mainly static parameters, so not dynamically measured. I wonder if you ever used the measured soil moisture values in the specific borehole for predicting the soil movement. Was this clear?
Can you repeat for Dr. Varun? Dr. Varun?
Yes, I was.
I got the question.
Okay.
I got the question. Actually, somehow I got muted. So your question was on dynamic parameters. So just to give you an idea, our system which we deployed and we perfected has parameters which are measured dynamically, and the soil parameters which we measure dynamically from the system include the soil moisture content, which is volumetric moisture content, then soil temperature, soil stress, which is through piezo sensor, and then soil movement. So these are the soil parameters which are measured dynamically every 10 minutes in the place where the sensor is deployed in the soil. In addition, we have dynamic weather parameters, which includes temperature, relative humidity, barometric pressure, light intensity, and rain. Why light intensity? Because oftentimes we found in hills, there are areas which are in shadow side. So evaporation of water, which pours as rain, doesn't take place as fast and might cause movement of soils or slides. So this is the quick answer. If you have any follow-up, please let me know, sir. Thank you.
Okay, thank you very much.
Okay, maybe somebody have the questions or comments or amendments, brief amendments. I understand that you are very tired during the so fruitful day, but many presentations. So in this connection, I think we may finish our panel discussion. So
I'm very thankful for the organizers and for all participants that shared their talks today. They are very outstanding talks. I liked a lot of them. I liked in some areas I'm not an expert, but I was very happy to hear that the topics were very well explained on a very high level. So even not being an expert, I was very happy to get the point very clearly. So when regarding the topics on urban flooding, on flood protection systems, and hydrological and surge modeling, it was on a very high level. I'm very happy to get acquainted with the distinguished colleagues from India, and hope that we will collaborate in future. Thank you very much.
Thank you, Vsevolod. Thank you very much. So to finalize the first day of our webinar, actually I have nothing to add except pronouncing my words of gratitude to all participants for their brilliant way to present their research. And I would like to remind you that you may exchange letters using emails that are stipulated in the program. And I also would like to remind you that tomorrow we continue with 2 more sessions, and I'm pleased to invite you to join us tomorrow at 10 morning Moscow time and 12:30 Indian time. To join us, you may use the link for the second day that is stipulated in the program. Thank you, everybody, and goodbye.
Thank you.
Perhaps Dr. Shishir say a few words?
No, I wanted to say the same thing, that tomorrow also everyone is invited. And
yeah, I want to add, Shishir, I don't know, my
please,
camera is not okay.
Yeah.
See, the two things that tomorrow's session, actually, my colleague will participate. Okay, and also the second thing, a small tip is that, you should manage so that the timings are okay for both sides. It's kind of really late now, isn't it?
So,
webinar,
yeah,
timings are okay for both sides.
Yeah. Timings are being met like that only.
Where it is 8 o'clock now.
Okay. Actually, the thing is that when we start, it is around 10 o'clock in Moscow. We cannot start before that because before 10 the offices are not open. And in case people have problem in giving presentations at 6 o'clock, 7 o'clock in India, we requested them and they agreed to it. So those people who have agreed.
The problem, what happens now, Shishir, the panel discussion gets diluted towards the end. For the session, the panel discussion got diluted because,
Yeah, that is, you are right, madam. But as Ms. Inna
it's
said,
just a suggestion. I am not blaming anyone. I'm just giving a suggestion. Okay.
This happens when you speak to US, you have to speak in the night. So this is only 2.5 hours difference. Professor Menon, you had some points, sir?
No, I just wanted to compliment you and the Russian Academy of Sciences International Cooperation for bringing together such a group of eminent experts. And we see a lot of commonalities in terms of both approaches and also the technologies. And there's a lot of potential for international cooperation, especially looking at the data points, the data sets which are actually available for collaborative research. There is a lot of opportunities. So it will be very good if you can also formulate a few recommendations in specific areas, especially in seismology and also in flood management, flood monitoring, landslide monitoring. What are the kind of areas where collaboration is possible, and institutions which can work with Indian institutions from Russia? It would be good to understand those areas. And in fact, the presentation which was made by Dr. Sridevi Jade on the potential of GNSS and also various other opportunities, whether it is actually the fourth paradigm in terms of looking at the opportunities going beyond the computations and also looking at evidence-based work. I think that will be very useful. So if we can actually look at certain specific areas in geology, because earthquakes, actually some of the presentations by the Russian experts showed that some of the areas in which need more explorations, more studies, and a collaboration between India and Russia would actually be very, very formidable and very challenging. Thank you.
Yes, these are very.
I would like to add. See, actually, we have a lot of GNSS data which no one has, and on the GNSS side of it, we never collaborated with Russian. So that is also something. The data is so important. Like
yes, madam. So you are kindly requested to find. You are kindly requested to find partners from this seminar, and we will help you to find more partners beyond this. Russian Academy of Science is here, and the moderators are also here. They will find some more partners for you, and you can make a concept note and send it to us.
Especially on the Shishir, especially on the data intensive part of it, we should be able to.
Yeah, got
it.
Yeah. So now we also have some other recommendations, as Dr. Perumal mentioned, from Wadia Institute, and there is a lot of commonality with your work and some work which being done in Russia. So Dr. Perumal, I will request you also to kindly formulate some engagements. And same is the case with Dr. Morido, who spoke on the urban flooding and urban flood management. And your synergy, if I may request you to find some synergy with Professor Kapil Gupta and his work at IIT Bombay, then these are the exchanges which can take it forward, and we will find some ways of, if you have some substantial projects, there are going to be some bilateral research calls also within next 2-3 months, and they are going to be India-Russia bilateral research calls supported by Department of Science and Technology on Indian side and Department of Biotechnology on Indian side, and the Ministry of Science and Higher Education on the Russian side. So these research calls are also there. Otherwise, besides these research calls also, we can have some separate projects supported by the sponsoring organizations, Emercon or NDMA on Indian side. So kindly formulate these projects, and we will try to see how we can progress this. Professor Menon, sir,
yes.
Is that right?
Yes, thank you very much. We should look forward to seeing some of the recommendations. We will also share some notes by email, and then we can consolidate that by tomorrow evening.
Yes.
Thank you.
Professor Sridevi, Dr. Sridevi, we have tried to manage the time, but if you have any more suggestions, kindly write to us. We will take into account whatever you say.
I'll do that. And tomorrow, Dr. Patra will participate because he's working on AI and earthquakes.
Yes.
Tomorrow I won't be participating.
Thank you very much. I especially thank the moderator, Professor Viktor Novikov, for being so patient with all the participants and speakers, and also to our first moderator, Professor Vinod Menon. And a very, very special thanks to Russian Academy of Science, the SINA Department of International Cooperation. And many thanks to all the distinguished speakers. Look forward to meeting you tomorrow. Out of your busy schedule, try and encourage and participate in the conversation and deliberations tomorrow also. Thank you very much.
Thank you. Thank you very much.
Thank you. Goodbye.
See you tomorrow.
So just one last point. I didn't see many tsunami-related works, but I'm very much I have so much idea like how the Russian, especially regarding the modeling, how there have been so many different models, and we were earlier had a collaboration with scientists. So as part of this, if we could add, like maybe tomorrow, if we have if you already know somebody, so that would be great. Like for the recommendations, if you could add this point also.
Certainly, you can make a small summary of recommendation from your side, and we will try to find a partner with the help of Russian Academy of Sciences. Is it fine, Madam Ms. Inna?
Yes, sure.
Thank you.
Thank you. Thank you, sir.
Thank you. Goodbye.
Goodbye. Good night.
Bye. Good night. Ciao.